From the earliest moments of the Big Bang to the boundless potential of future space exploration, the universe has unfolded in ways that are both awe-inspiring and deeply humbling. Over billions of years, it has evolved from an unimaginable singularity, a point of infinite density, into the vast and intricate cosmos we see today. As scientists peer back in time, they unravel the mysteries of cosmic inflation, the birth of the first stars, and the formation of galaxies in an ever-expanding dark universe. What we observe is just a snapshot, a fleeting glimpse into the infinite expanse of the cosmos that has existed and will continue to exist far beyond our comprehension. Looking forward, the possibilities for cosmic exploration are limitless. The coming era of space exploration could unveil the enigmatic nature of dark matter and dark energy, phenomena that make up the majority of the universe, yet remain largely undetectable. We may probe the deepest secrets of black holes, testing the very boundaries of known physics and discovering the true nature of these celestial giants. Perhaps most thrillingly, we may find evidence of life beyond Earth, either within our own solar system or on distant exoplanets, fundamentally altering our place in the universe. As we embark on this grand journey, we turn our attention to the very building blocks of the universe, the stars. Stars are born from the depths of vast clouds of dust and gas, known as molecular clouds, which are primarily composed of hydrogen, the most abundant element in the universe. Over time, certain regions within these clouds experience a collapse under their own gravity. This collapse is often triggered by external events such as a nearby supernova explosion or the collision of two molecular clouds, which injects pressure into the system, causing parts of the cloud to contract and form dense regions. As the cloud collapses under its own gravity, it begins to heat up, with the temperature at the core rising exponentially. The pressure builds, and a dense core forms at the center of the collapsing region. This core is known as a protostar. Imagine it as an ember growing in intensity within a fire. The core continues to become hotter and denser as more material from the surrounding gas cloud is drawn in by the gravitational pull. As the temperature at the core rises, it eventually reaches a critical threshold where nuclear fusion can begin. Nuclear fusion is the process by which hydrogen atoms fuse together to form helium, releasing an immense amount of energy in the process. This energy acts as a counterbalance to the force of gravity, halting the collapse of the protostar and marking the birth of a true star. At this stage, the star achieves a delicate balance between the outward pressure from the energy produced by nuclear fusion and the inward pull of gravity. This equilibrium is what keeps the star stable, allowing it to shine for millions or even billions of years. During their lifetimes, stars undergo a complex series of transformations, gradually burning through their hydrogen fuel and fusing it into heavier elements. As they age, their internal dynamics change, leading them to enter different stages of their life cycle. The lifespan of a star is primarily determined by its mass. Massive stars burn their fuel much more quickly than smaller stars due to the higher temperatures in their cores, which accelerate the fusion process. This rapid consumption of fuel means that a massive star might burn brightly for only a few million years, whereas smaller stars, like our Sun, can shine for tens of billions of years. The process of nuclear fusion within a star's core is the engine that powers it. It is here, in the extreme conditions of temperature and pressure, that hydrogen atoms fuse into helium. The rate of fusion is directly proportional to the temperature and pressure inside the star, both of which are determined by the star's mass. Larger stars have higher core temperatures and greater pressure, which leads to faster fusion rates. As the star ages and its hydrogen fuel is exhausted, the core contracts and heats up further, initiating the fusion of heavier elements. For smaller stars like our Sun, this process primarily involves the fusion of hydrogen into helium, a process that occurs over billions of years. As the hydrogen fuel in the core runs out, the star begins to swell, becoming a red giant. During this phase, the star fuses helium and other heavier elements, leading to the creation of elements such as carbon, oxygen, and iron in its core. Eventually, the outer layers of the star are ejected, leaving behind a dense, hot core known as a white dwarf. Over the course of billions of years, the white dwarf will cool, becoming a faint and dim remnant of its former self. Massive stars, however, burn through their fuel at a much faster rate. These stars not only fuse hydrogen into helium, but also undergo a series of fusion reactions that create heavier elements like carbon, oxygen, and eventually iron. This process results in an incredibly energetic release of radiation, making these stars shine with immense brightness, albeit for a relatively short period. When a massive star reaches the end of its life cycle, it can no longer sustain fusion in its core. The core collapses under the force of gravity, triggering a catastrophic explosion known as a supernova. A supernova is one of the most violent and energetic events in the universe. It is a powerful, luminous explosion that marks the death of a star. During this event, a massive amount of energy is released, and heavy elements such as iron and gold are scattered throughout space. These elements are essential for the formation of planets and life itself. The explosion of a supernova is not just a brief flash of light, but a complex, multi-stage event that leaves behind remnants like neutron stars or, in the most extreme cases, black holes. The fate of the star's remnants depends on its original mass, with the most massive stars collapsing into black holes. While both massive and smaller stars share a common origin, their life cycles take very different paths. The mass of a star plays a critical role in determining how it will evolve. Massive stars burn bright and fast, living short but intense lives that end in explosive supernova. Smaller stars, in contrast, live long and stable lives, slowly transforming into white dwarfs as their outer layers are gently shed. This stark contrast in the life cycles of stars not only shapes the stars themselves, but also has profound implications for the evolution of galaxies and the universe as a whole. The death of a star, whether through a supernova explosion or the slow shedding of outer layers in a planetary nebula, plays an integral role in the cosmic cycle of matter and energy. A supernova, for example, is not just the end of a star's life, but the beginning of a new phase in the cosmic story. The heavy elements created during the explosion are spread across space, enriching the interstellar medium and providing the raw material for the formation of new stars, planets, and, potentially, life. A planetary nebula, on the other hand, represents a quieter, more gradual transition. In stars like our Sun, the outer layers are ejected in a series of stellar winds, creating beautiful, glowing clouds of gas and dust. The core of the star remains behind, eventually cooling and forming a white dwarf. Over billions of years, the white dwarf will continue to cool and fade, but its legacy lives on in the elements it has created. The death of a star is thus not an end, but a transformation. It is part of a cosmic cycle that drives the ongoing evolution of the universe, from the birth of stars to the formation of planets and the eventual emergence of life. As we look to the future, the exploration of this cycle, and the profound processes that govern the lives and deaths of stars will continue to reveal new insights into the nature of our universe. Whether we are peering into the past to understand the origins of the cosmos, or gazing into the future to uncover the secrets of dark matter and black holes, the journey of discovery is only just beginning. The stars, with their brilliance and their death throes, remind us of the vastness of space and the infinite possibilities that await us. When massive stars reach the end of their life cycle, the universe witnesses one of its most spectacular and violent events, the supernova. These cosmic fireworks mark the dramatic conclusion of a star's journey. However, the process leading up to such a cataclysm is anything but ordinary. As a massive star exhausts the nuclear fuel in its core, the once stable equilibrium between the inward pull of gravity and the outward push of radiation begins to unravel. This causes the core to collapse under its own immense weight, triggering an intense series of reactions that reverberate through the star's structure. The collapse of the core results in an astonishing increase in both temperature and pressure, setting the stage for an explosive chain reaction. As the core reaches an extreme density, it ignites a succession of rapid, violent nuclear reactions. The outer layers of the star are violently expelled into space, propelled outward at speeds that are unimaginable. The result is a brilliant flash of light, so intense that it can briefly outshine an entire galaxy, broadcasting its ferocity across vast cosmic distances. This explosion is not only one of the most powerful events in the universe, but also one of the most transformative. In the wake of the supernova, a tremendous amount of energy is released into space. This energy plays a critical role in the dispersal of elements into the cosmos, enriching the interstellar medium, the vast space between stars, with the raw materials necessary for the formation of new stars, planets, and potentially life. The supernova acts as a cosmic forge, producing elements heavier than hydrogen and helium, such as carbon, oxygen, nitrogen, and iron, that are crucial for life as we know it. These elements are scattered across space, contributing to the molecular building blocks of the universe. Supernovae are classified into different types, each distinguished by the mechanisms that drive them. One of the most well-known types is the Type 1 supernova, which occurs in binary star systems. In these systems, a smaller star siphons material from its companion until the larger star reaches a critical mass. Once the star exceeds this limit, it becomes unstable, eventually leading to a catastrophic explosion. On the other hand, Type 2 supernovae are typically the result of massive stars reaching the end of their lives. When these stars exhaust their nuclear fuel, their cores collapse, triggering the explosive event. Regardless of the type, all supernovae mark the end of a star's life, but they also initiate the birth of something new, a cosmic cycle of creation and destruction that shapes the evolution of the universe. The remnants of a supernova can give birth to neutron stars or even black holes, depending on the mass of the original star. As the explosion sends shockwaves through the surrounding space, the expelled material, rich in newly formed elements, spreads throughout the universe. This material may eventually clump together under the influence of gravity, eventually coalescing into new stars and planetary systems. Thus, the death of one star serves as the catalyst for the birth of many others, ensuring that the cosmic cycle of life continues. Supernovae are not just the death throes of stars. They are the crucible for the creation of new stars, planets, and the very elements necessary for life itself. The process by which these stars transform from the dazzling explosion of a supernova into something as enigmatic as a black hole or neutron star is both fascinating and mysterious. A supernova explosion begins when the core of a massive star collapses under the immense force of gravity. The energy released is so intense that the star's outer layers are expelled at speeds up to 30,000 kilometers per second. This rapid expulsion creates a shock wave that reverberates throughout the surrounding space, propagating through the gas and dust that exist between stars. During this explosion, the temperatures soar to billions of degrees, high enough to trigger nuclear reactions that synthesize new elements. Lighter elements, such as hydrogen and helium, fuse together to form heavier elements like carbon, nitrogen, and oxygen. This process of fusion, which mirrors the way blocks are stacked together to form a larger structure, continues until the core becomes dense enough to initiate the formation of even heavier elements, including gold and uranium. The process is known as neutron capture, and it results in the creation of a vast array of new, unstable elements that are quickly scattered throughout space. This chain of reactions ensures that the elements required for life, as well as the precious metals that we use on Earth, are formed in the final moments of a star's life. As the star's outer layers are expelled, the universe is enriched with these newly created elements. This ejected material, rich in heavy elements, spreads throughout space, adding to the interstellar medium. Over time, the gas and dust created by the supernova begin to gather, and the gravitational forces at play cause these materials to collapse further. Eventually, this collapse leads to the birth of new stars. The cycle is both destructive and creative. When a massive star dies in a violent explosion, it seeds the cosmos with the very elements that will form the next generation of stars and planets. This cycle of stellar life, death, and rebirth illustrates the dynamic and ever-changing nature of the universe. In the aftermath of a supernova explosion, the remnants of the star, now a colorful nebula of gas and dust, continue to evolve. These remnants are some of the most captivating objects in the universe, offering a glimpse into the process of stellar evolution. By studying the light emitted by these remnants, astronomers can learn a great deal about the dynamics of the explosion and the materials involved. Telescopes capable of observing light across different wavelengths, such as visible light, infrared, and X-rays, allow scientists to gather a more complete picture of the remnants of supernovae. In the visible spectrum, the remnants often appear as brilliant, colorful clouds. These clouds are composed of various gases, including hydrogen, which can glow with distinctive colors. In the infrared spectrum, cooler regions of the remnants emit heat, revealing compositions and structures that might otherwise be hidden from view. X-ray telescopes provide a unique insight into the high-energy processes at play in the remnants, particularly where the shock waves from the explosion collide with surrounding material. The combination of these observational techniques provides astronomers with a comprehensive understanding of the aftermath of a supernova explosion. The study of supernova remnants is not just about understanding the explosive death of a star. It is also about gaining insight into the processes that have shaped the universe. By observing how these remnants change and evolve over time, scientists can learn about the forces that drive stellar evolution and the ongoing processes of cosmic creation. Furthermore, measuring the distance to these remnants enables researchers to assess their size and the amount of material that has been dispersed into space. This information is crucial in understanding the scale of the explosion and the extent to which the supernova has affected its surrounding environment. Through the study of these cosmic phenomena, we gain a deeper understanding of the fundamental processes that govern the universe. We learn how stars are born, live, and die, and how their deaths contribute to the creation of the elements that make up everything around us. The remnants of supernovae are not just the echoes of past explosions. They are the seeds of future stars, planets, and life itself. While supernovae and their remnants provide profound insights into the life cycles of stars, there is another extraordinary end that some massive stars face: the formation of black holes. A black hole is a region of space so dense that its gravitational pull is so strong that not even light can escape. The creation of a black hole is the ultimate fate for stars with a mass several times that of our Sun. As a star's core collapses under its own gravity, it compresses to an infinitely small point known as a singularity. Surrounding this singularity is an invisible boundary known as the event horizon, the point beyond which nothing can escape, not even light. Black holes do not emit light, which makes them incredibly difficult to detect using traditional telescopes. However, their presence can be inferred by observing the way they interact with their surroundings. When a black hole is part of a binary system, for example, material from its companion star may be drawn toward it, forming an accretion disk. As this material spirals toward the event horizon, it heats up and emits intense radiation, allowing astronomers to detect the black hole's presence. A black hole is not just a cosmic disaster waiting to happen. It is the result of stellar evolution, a testament to the complex and fascinating life cycle of stars. The birth of a black hole represents the culmination of a star's life, a final transformation into a region of space where the rules of physics as we know them break down. The immense gravitational forces near a black hole warp space and time itself, creating one of the most mind-boggling and awe-inspiring phenomena in the universe. While we may not fully understand everything that occurs inside a black hole, the study of these enigmatic objects continues to reveal new insights into the nature of the universe and the forces that govern it. Black holes, those enigmatic giants of the cosmos, have intrigued scientists for decades. Despite their inherently invisible nature, they leave behind powerful clues that enable researchers to piece together their elusive existence. However, understanding these cosmic phenomena requires more than just theoretical musings or mathematical calculations. It demands ingenuity and creativity in observation, as these mysterious objects don't emit light and are hidden deep within the fabric of space-time. Yet, over time, scientists have discovered remarkable ways to detect their presence and measure their influence on the surrounding universe. Among the most effective methods scientists have devised is observing the behavior of nearby stars and gas clouds that are caught in the intense gravitational pull of a black hole. When a star is in close orbit around a black hole, it exhibits rapid and unpredictable movements, which, when carefully tracked, provide essential insights into the mass and nature of the black hole. These erratic motions are not just random. They follow precise patterns governed by the laws of gravity. By carefully measuring the velocity of these stars and their orbital characteristics, scientists can deduce the size and mass of the black hole exerting its gravitational pull. Essentially, these stellar movements act as cosmic markers that allow scientists to infer the black hole's hidden mass, even if they cannot directly observe the black hole itself. In addition to the behavior of stars, scientists have turned their attention to the material surrounding black holes. This material, composed mostly of gas and dust, spirals inward toward the black hole, forming what is known as an accretion disk. As this matter gets closer to the black hole, it accelerates and heats up to extreme temperatures, often reaching millions of degrees. The intense friction and compression cause the gas to emit powerful radiation, especially in the form of X-rays. These X-rays are not just random bursts of energy, but highly structured emissions that carry crucial information about the black hole's characteristics. By studying this radiation, scientists can indirectly detect the black hole's presence and analyze its properties. This method has been instrumental in uncovering the nature of black holes that are light years away, providing compelling evidence of their existence even when the black hole itself remains hidden from view. Recent technological advancements have made it possible to observe black holes in ways that were previously unthinkable. One such breakthrough came from the Event Horizon Telescope, a global network of radio telescopes that spans the Earth. In 2019, this network achieved a historic feat by capturing the first ever image of a black hole's shadow. This shadow, which is essentially the silhouette of the black hole against the luminous gas of the accretion disk, provided direct visual evidence of a black hole's existence. The image was a momentous achievement in astrophysics, not just for its technical marvel, but because it offered tangible proof of something that had previously only existed in theoretical models. The Event Horizon Telescope's success marked a turning point in our understanding of black holes, allowing us to glimpse the very edge of these cosmic giants and revealing the mysterious depths of space-time. At the heart of every black hole lies the event horizon, a boundary that marks the point of no return. This unseen line represents the threshold beyond which nothing, neither matter nor light, can escape the black hole's gravitational grip. It's at this critical juncture where the laws of physics as we know them begin to break down. Space and time become distorted, and strange effects emerge for any observer watching from a distance. Time can stretch and slow, creating bizarre phenomena such as time dilation, where an observer might perceive events as unfolding at an incredibly slow pace near the event horizon. These peculiar behaviors challenge our basic understanding of reality, forcing scientists to rethink long-held assumptions about how space-time functions. The event horizon is more than just a theoretical boundary. It is a crucial feature that scientists study to understand the mechanics of black holes. It provides valuable insights into the black hole's size, rotation, and its interactions with the surrounding matter. Observing the behavior of light and energy as it approaches the event horizon helps scientists unlock mysteries about the black hole's properties. For instance, by studying how matter behaves under the extreme conditions near the event horizon, scientists can gather information about the black hole's rotation speed, which in turn informs us about its internal structure. The event horizon, in essence, serves as a cosmic laboratory for testing the limits of physics under extreme conditions, where the fabric of space-time itself is stretched and twisted beyond recognition. Another critical area of black hole research involves measuring their mass. This might seem like an impossible task, given that black holes themselves do not emit light. However, scientists have developed clever techniques to determine their mass indirectly. One of the most effective methods is observing the motion of nearby stars or gas clouds. Much like how we can determine the weight of an object by observing how it affects the motion of other objects, the gravitational influence of a black hole can be inferred by studying the way nearby stars or gas behave. When a star orbits a black hole, it moves in a particular way that depends on the mass of the black hole. If the star is moving at high speeds, this indicates that the black hole is very massive. Scientists can apply the laws of gravity to these observations. The strength of gravity from an object dictates how quickly nearby objects will move. By measuring the speed of orbiting stars and the distance between them and the black hole, researchers can calculate how much mass the black hole must have to exert such a gravitational influence. This method is highly effective, especially when combined with other techniques, like studying the light emitted by hot gas as it spirals into the black hole. The gas, which is accelerated to incredible speeds, emits X-rays as it heats up. By analyzing these X-rays, scientists can gain further insights into the black hole's mass and other characteristics, such as its spin and the rate at which it is accreting matter. In recent years, another groundbreaking method for studying black holes has emerged: gravitational waves. These are ripples in space-time caused by the acceleration of massive objects, such as two black holes merging. As these waves travel through space, they carry with them information about the objects that generated them, including their mass and other properties. By studying these gravitational waves, scientists can learn more about the black holes involved in the event, such as their size, spin, and how they interact with each other. Gravitational waves have become an essential tool in black hole research, offering a new way to observe these invisible objects and their behavior. Black holes, despite their seeming simplicity, come in a variety of sizes and forms. The most commonly recognized types are stellar black holes, supermassive black holes, and intermediate black holes. Each of these categories has its own unique characteristics, and each provides a different perspective on the nature of black holes. Stellar black holes are the most common type and are formed when massive stars reach the end of their life cycle and undergo a supernova explosion. This catastrophic collapse compresses the star's core to a point where gravity becomes so intense that not even light can escape. Stellar black holes typically have masses several times that of our Sun, but their gravitational influence is immense. These black holes can often be detected by the light emitted when they pull in surrounding gas and debris, which forms the accretion disk. Supermassive black holes, on the other hand, are far larger and more mysterious. These giants can have masses ranging from millions to billions of times that of the Sun. Supermassive black holes are thought to reside at the centers of most galaxies, including our own Milky Way. The origin of these supermassive black holes remains one of the biggest puzzles in astrophysics. It is likely that they formed through the merger of smaller black holes and the accretion of vast amounts of gas and dust over billions of years. These supermassive black holes are so powerful that they play a significant role in shaping the structure of their host galaxies. Their gravitational influence can affect the orbits of stars and the overall dynamics of the galaxy, driving the formation and evolution of galaxies themselves. Intermediate black holes are a less common, yet equally fascinating category. These black holes, as their name suggests, have masses that fall between stellar and supermassive black holes. Although their existence was once purely theoretical, recent observations suggest that intermediate black holes may form from the merger of stellar black holes in dense star clusters. These black holes could be crucial in understanding how black holes evolve over time and how they influence the growth of galaxies. Together, these different types of black holes provide critical insights into the workings of the universe. Studying their formation, growth, and interactions with their surroundings can help us understand how galaxies evolve and how the fundamental forces of nature shape the cosmos. Through these methods, whether it's observing stars, analyzing X-rays, detecting gravitational waves, or even capturing images of black holes, we continue to push the boundaries of what we know, unraveling the mysteries of some of the most extraordinary objects in the universe. The vast and mysterious cosmos holds secrets that challenge our understanding of physics, time, space, and the very nature of reality. Among these cosmic enigmas, black holes stand as some of the most captivating and perplexing objects in the universe. While most of us are familiar with the concept of black holes, regions of space where gravity is so intense that not even light can escape, there are more elusive and theoretical black holes that stretch the boundaries of our imagination. One such type is the primordial black hole, which is thought to have formed shortly after the Big Bang. These theoretical black holes could be incredibly small, and their masses could vary greatly, but their existence remains speculative. Scientists are still searching for definitive evidence to confirm that these ancient objects really exist. Primordial black holes, if they do exist, would be relics from the early universe, potentially offering a glimpse into the conditions that prevailed just after the Big Bang. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes could have emerged from fluctuations in the density of the early universe, leading to regions where gravity was strong enough to collapse matter into these compact objects. Their study could provide valuable insight into the evolution of the cosmos during its earliest stages. However, their elusive nature means that the hunt for primordial black holes continues, with each observation potentially bringing us closer to understanding their true role in cosmic history. In addition to primordial black holes, the study of other types of black holes offers a wealth of information about the universe's fundamental workings. Each type of black hole, whether stellar, supermassive, or intermediate, sheds light on the processes of star formation, the evolution of galaxies, and the behavior of matter and energy under extreme conditions. For instance, supermassive black holes, which lurk at the centers of most large galaxies, are believed to play a key role in the formation and growth of galaxies. Their immense gravitational pull influences the motion of stars and gas within the galaxy, and their growth may be intimately tied to the evolution of the galaxy as a whole. As scientists continue to observe these cosmic giants, our understanding of the universe continues to evolve, revealing deeper layers of complexity and wonder. A black hole, with its immense gravitational field, has the power to warp both space and time in ways that challenge our classical understanding of the universe. To grasp this, imagine space as a stretched rubber sheet. When a heavy object, like a black hole, is placed on the sheet, it creates a deep indentation, warping the fabric of space. This distortion represents the gravitational influence of the black hole. With the greater the mass of the object, the more space itself is bent and curved. The more massive the black hole, the greater its distortion of the surrounding space, and the more profound its gravitational pull. Time, too, is affected in a similar manner. In the presence of a black hole, time itself slows down. To illustrate this, think of time as a river flowing steadily. As the river approaches the event horizon of a black hole, the boundary beyond which nothing can escape, the flow of time slows dramatically. If an observer were positioned at a safe distance from the black hole, they would perceive events unfolding near the black hole much more slowly compared to their own experience of time, which remains unaffected by the black hole's gravitational influence. This phenomenon, known as time dilation, occurs because the intense gravitational field near the black hole stretches the fabric of space-time, causing time to run slower the closer one gets to the event horizon. From the perspective of an outsider, as an object falls toward a black hole, it appears to move slower and slower, seemingly freezing at the event horizon before fading from view, as the light it emits struggles to escape the overwhelming gravity. However, for the object itself, whether it's a person, a spaceship, or any other object, this effect would not be noticeable at first. They would continue to fall inward without any immediate sensation of slowing down, passing through the event horizon, and into the black hole's interior. Beyond the event horizon, the environment becomes so extreme that the known laws of physics break down, and our understanding of space and time no longer holds. As one crosses into the black hole's interior, the concept of time and space becomes even more alien. The closer you get to the singularity, the point of infinite density at the very center of the black hole, the stronger the effects of gravity become, eventually reaching a point where they are so powerful that time and space merge in strange and unpredictable ways. This region, known as the singularity, is where matter is crushed into an infinitesimally small point, and where current theories of physics, including general relativity and quantum mechanics, break down completely. The singularity remains one of the greatest mysteries in modern physics, as it presents a place where our understanding of the universe is no longer applicable. One of the most intriguing aspects of black holes is the question of what lies beyond the event horizon. The event horizon marks the point of no return. Once something crosses this boundary, it is thought to be lost forever to the black hole. However, the true nature of what happens inside a black hole is still a subject of great speculation. One popular theory suggests that inside the event horizon, matter is compressed into an infinitely small point, the singularity. In this scenario, the laws of physics as we know them would no longer apply, and both time and space would be distorted to such an extent that they cease to behave in predictable ways. This suggests that the interior of a black hole is vastly different from the reality we experience in our everyday lives. Another fascinating possibility is the concept of wormholes. Some scientists speculate that black holes could serve as portals or tunnels that connect different regions of space or even entirely different universes. In this theory, a wormhole could act as a bridge, allowing for the travel between distant parts of the universe or to alternate dimensions entirely. This idea, while highly speculative, suggests that black holes might not be the destructive objects we traditionally think of, but instead could be gateways to other realms of existence. If this theory were to be confirmed, it would revolutionize our understanding of space, time, and the structure of the cosmos. Additionally, the question of what happens to information that falls into a black hole has given rise to the famous black hole information paradox. According to the principles of quantum mechanics, information cannot be destroyed. However, if something falls into a black hole, it seems to disappear beyond the event horizon, seemingly lost to the universe forever. This creates a fundamental contradiction with the laws of quantum theory. Researchers are actively exploring whether information might be preserved in some form at the event horizon, possibly encoded in the radiation emitted by the black hole itself. This idea, known as the holographic principle, suggests that there may be a deeper layer of reality that we have yet to understand, a layer that could hold the key to reconciling the paradox and advancing our understanding of quantum mechanics. In recent years, some scientists have proposed even more radical ideas, suggesting that black holes could be gateways to parallel universes or alternate dimensions. If this were the case, it would dramatically alter our understanding of the cosmos, implying that the universe is far more interconnected and multifaceted than we currently imagine. These ideas challenge the boundaries of conventional science and push us to rethink the very nature of reality itself. Beyond the realm of black holes, astronomers are also exploring the vast expanse of exoplanets, planets that exist outside our solar system and orbit stars other than our sun. The discovery of exoplanets has opened up a new frontier in our quest to understand the universe, revealing that planetary systems may be far more common than previously thought. In fact, every star in the sky could potentially host its own planetary system, making the search for habitable worlds an exciting and ever-expanding field of study. Exoplanets come in a wide variety of shapes, sizes, and compositions, and studying them has revealed much about the diversity of planetary systems. The methods used to discover and study exoplanets have evolved significantly over the years. Early methods relied on detecting small changes in starlight caused by a planet passing in front of its star, a technique known as the transit method. When a planet transits its star, it blocks a small amount of light, causing a temporary dimming that can be detected by telescopes. This technique has led to the discovery of thousands of exoplanets. Another method for detecting exoplanets is radial velocity, which looks for the wobble of a star caused by the gravitational pull of an orbiting planet. As a planet moves around its star, the planet's gravity causes the star to move slightly in response. This motion causes shifts in the star's light spectrum, which can be detected by spectrometers. These techniques, along with newer methods like direct imaging, where astronomers capture images of exoplanets by blocking out the light from their parent star, continue to expand our knowledge of distant worlds. As technology improves, scientists are increasingly able to probe deeper into the conditions of exoplanets, with the ultimate goal of determining their potential for habitability. To assess whether a planet might support life, scientists look for planets located in the habitable zone of their star, a region where conditions are just right for liquid water to exist. This zone, often referred to as the Goldilocks zone, is neither too hot nor too cold, making it a prime candidate for life as we know it. In addition to the habitable zone, scientists also examine the atmosphere of an exoplanet. A planet's atmosphere can help regulate temperature and protect its surface from harmful radiation. By analyzing the light that passes through an exoplanet's atmosphere, scientists can determine its composition and look for signs of gases that might indicate the presence of biological activity. If a planet's atmosphere contains oxygen, methane, or other gases associated with life, this could be an important clue that life might exist on that planet. The geology of an exoplanet is another important factor in determining its habitability. A planet with a solid surface and active geological processes, such as volcanism and plate tectonics, might have the conditions necessary for a dynamic ecosystem capable of supporting life. Finally, scientists also consider the type of star the exoplanet orbits. Stars that burn steadily and have long lifespans offer planets more time to evolve and potentially develop life. As scientists continue their search for habitable exoplanets, they are uncovering a wealth of new worlds, each with its own unique characteristics. Some exoplanets, like the hot Jupiters, are gas giants that orbit very close to their parent stars, resulting in scorching temperatures and extreme weather conditions. These planets are so hot that their atmospheres could potentially melt metal. On the other hand, there are exoplanets that lie within the habitable zone of their stars, where liquid water could exist, an essential ingredient for life as we know it. The search for exoplanets and the study of black holes are just two of the many ways scientists are expanding our understanding of the universe. With each discovery, we move closer to answering some of the most profound questions about the nature of existence, the potential for life beyond Earth, Mute, and the mysteries of the cosmos. The universe, with its vastness and complexity, remains an awe-inspiring frontier for human exploration and discovery. However, despite its enormous potential for supporting life, we are still only beginning to unravel the complexities of the atmospheres and conditions of distant worlds. The exploration of exoplanets, planets that orbit stars other than our Sun, has revealed an array of environments far beyond our imagination, pushing the boundaries of what we consider possible in planetary science. These faraway worlds offer a unique lens through which to observe the nature of planets, the behavior of atmospheres, and the conditions that might harbor life. Among these fascinating discoveries, there exists a planet whose surface is almost entirely consumed by molten lava. It presents an otherworldly landscape where rivers of molten rock flow relentlessly across the land. The constant volcanic activity on this planet paints a vivid picture of the intense geological processes occurring in real time, showcasing the dynamic nature of celestial bodies. As we witness the geological activity on such a world, we're reminded of how planets can remain active over billions of years, constantly reshaping themselves through volcanic eruptions, earthquakes, and shifts in the tectonic plates. Then, there's an exoplanet residing within a binary system, a collection of two stars orbiting each other. This binary system hosts multiple planets, each in complex motion, demonstrating how planetary bodies can interact gravitationally, tugging on one another as they orbit their respective stars. This intricate dance through space reveals the complex forces at play in the universe, shedding light on how planets form, move, and interact in ways we're just beginning to understand. By observing these planetary movements and gravitational influences, scientists gain crucial insights into the processes that govern the formation of planetary systems. Lastly, we encounter a planet whose atmosphere is so dense and laden with strange gases that it holds an air of mystery. Studies suggest that it might even have clouds made of precious gems, raining down glittering stones across its surface. This phenomenon, if true, gives us a peek into the extraordinary diversity of planetary environments that exist beyond Earth, highlighting how each planet's unique composition can create environments utterly alien to our own experience. The exploration of such planets pushes the boundaries of what we know about chemistry, geology, and the potential for life in the universe. It invites us to imagine life forms that could thrive in conditions far outside of what we consider normal. These discoveries, whether they reveal worlds covered in lava, complex planetary interactions, or atmospheres filled with gem-like clouds, serve as stepping stones in our growing understanding of the universe. Each new planet discovered offers a piece to the ever-expanding puzzle of our cosmic neighborhood, offering us a glimpse into the extraordinary possibilities that lie far beyond Earth. As we study these distant worlds, we are constantly reminded of how little we truly understand about the vastness of the universe and the myriad environments that could exist out there. Exoplanets come in a wide range of sizes, compositions, and orbital characteristics. Some of them are gas giants, vastly larger than Jupiter, while others are small, rocky planets similar in size to Earth or Mars. This diversity is one of the most intriguing aspects of exoplanet discovery. Unlike the planets within our solar system, which can be categorized into two main groups, rocky planets and gas giants, exoplanets demonstrate an even greater variety, offering a glimpse into planetary systems that don't fit neatly into these traditional classifications. Many of these exoplanets exist in extremely close orbits around their stars, subjecting them to scorching temperatures that would make them inhospitable to life as we know it. However, other planets follow more erratic elliptical orbits, where they swing dramatically closer to their stars before retreating to the cold reaches of space. This variance in orbits creates a host of unique environmental conditions, from extreme heat to intense cold, resulting in atmospheric compositions and potential for life that we can only speculate about. Additionally, exoplanets that fall into the category of super-Earths, planets that are larger than Earth but smaller than the gas giants, present even more intriguing possibilities. These worlds may have thick, dense atmospheres, and in some cases, they could even harbor liquid oceans. The potential for water on these planets has sparked speculation about their habitability, as water is considered one of the fundamental building blocks for life. The discovery of such worlds challenges our understanding of what planets need to support life, and highlights how the diversity of exoplanets pushes the boundaries of planetary science, making it clear that the universe is teeming with worlds that defy traditional definitions. In order to better understand the atmosphere of these distant exoplanets, astronomers use several fascinating techniques to gather information. One of the most important methods is called spectroscopy. Imagine shining a beam of light through a prism and watching it break into a rainbow. Similarly, when light from a star passes through the atmosphere of a planet, it is altered in distinct ways, leaving behind a unique pattern, almost like a fingerprint. By studying these spectral patterns, scientists can determine what gases make up the planet's atmosphere. They can detect elements like carbon dioxide, hydrogen, and even the presence of water vapor, offering crucial insight into the planet's potential to support life. Another technique that has proven invaluable is the observation of planetary transits. This occurs when an exoplanet crosses in front of its star from our viewpoint here on Earth. During a transit, some of the star's light passes through the planet's atmosphere, and certain wavelengths of light are absorbed by the gases present. By carefully analyzing the light before, during, and after the transit, astronomers can gather detailed information about the atmosphere's composition and density, as well as potential weather patterns. This method has proven to be one of the most effective ways to study exoplanets at a distance, providing a wealth of data that helps shape our understanding of these distant worlds. Direct imaging also plays a critical role in exoplanet research. In this method, astronomers attempt to capture images of the planets themselves, carefully filtering out the overwhelming light from their parent stars. Using advanced instruments and techniques, they are able to isolate the faint light reflected from the planet's surface or atmosphere, providing valuable insights into its atmospheric conditions and surface features. While this method is challenging, it has already yielded impressive results, allowing scientists to study exoplanets in unprecedented detail. Finally, astronomers also rely on data from space telescopes equipped with specialized sensors. These instruments are capable of detecting subtle changes in the light emitted by a star caused by the gravitational pull of an orbiting planet. This gravitational tug can offer clues about the mass and size of the planet, helping scientists to infer details about its atmosphere and surface conditions. The continued development of these technologies is opening up new avenues of exploration, enabling astronomers to gather data on exoplanets that was once thought to be beyond our reach. The search for exoplanets not only expands our understanding of planetary science, but also ignites our curiosity about life beyond Earth. Just as an ocean is filled with countless islands, each exoplanet represents a potential world that could host life. By studying the diverse environments of these distant planets, scientists can explore what conditions might allow life to thrive elsewhere in the universe. Some exoplanets are similar in size and temperature to Earth and sit within what is known as the habitable zone, the region around a star where liquid water could exist. These Earth-like planets are prime targets in the search for life, as water is essential for all known life forms. The discovery of such worlds stirs excitement about the possibility of finding life beyond our planet, encouraging further exploration of these distant worlds. However, exoplanets also come in a variety of other forms. Some are gas giants, much larger than Earth, while others are icy, frozen worlds. These diverse planets challenge our assumptions about what kinds of conditions are necessary for life, prompting scientists to consider broader definitions of habitability. Could life exist in the dense atmospheres of gas giants? Could it survive on icy moons or frozen planets? The discovery of such diverse environments forces us to reconsider what life could look like beyond Earth, opening the door to a broader understanding of the possible forms life might take. Exoplanet studies also provide valuable insights into the chemistry of distant worlds. By analyzing the light that filters through a planet's atmosphere, scientists can detect specific gases that may indicate biological processes. For example, the presence of gases like oxygen and methane, when found together, could suggest the presence of life, as these gases are often associated with biological activity on Earth. The ability to detect such biosignatures from light alone represents a major breakthrough in the search for life beyond our planet. Perhaps most intriguingly, the search for exoplanets raises profound philosophical questions. If the universe is filled with planets capable of sustaining life, what does this mean for our understanding of our place in the cosmos? Could we be part of a vast, interconnected network of life forms spread across the galaxy? As more and more exoplanets are discovered, the possibility that we are not alone becomes ever more plausible. This realization has spurred new research and technological development, pushing the limits of human exploration and discovery. In recent years, scientists have increasingly focused their efforts on identifying planets in the habitable zone of distant stars, places where life might not only exist, but thrive. The search for intelligent life among the stars has become a central goal for astronomers and astrobiologists. With billions of stars in our galaxy alone, many of which are likely to have planets, the chances of finding a world capable of supporting life are growing with each discovery. The search for intelligent life is further complicated by the need for specific conditions to exist. For instance, the size of the planet is crucial. Planets too small may not have the gravitational pull needed to retain an atmosphere, while planets too large may not allow for stable Earth-like environments. The composition of the atmosphere is equally important, as it must contain the right balance of gases to support life and protect against harmful radiation from the star. The age of a planet also plays a critical role. Planets that are too young may not have had time to develop complex life, while ancient planets could have already hosted advanced civilizations, or conversely could have undergone environmental changes that rendered them uninhabitable. In the search for extraterrestrial intelligence, scientists are developing new technologies to detect signs of advanced civilizations. These technologies aim to identify unusual atmospheric compositions, signals, or other signs of industrial activity that might indicate the presence of intelligent beings. The quest for technosignatures, indicators of technological processes, has become one of the most exciting frontiers in the search for life beyond Earth. As we venture deeper into the cosmos, one of the most profound questions that continues to emerge is encapsulated in the Fermi paradox. If intelligent life is so common in the universe, why have we not yet detected it? Theories attempting to explain this paradox abound. Some suggest that intelligent civilizations are exceedingly rare, while others propose that advanced societies might self-destruct before they can communicate with other life forms. Another possibility is that extraterrestrial civilizations may intentionally avoid contact, choosing not to engage with less advanced species. Although we have yet to make definitive contact with extraterrestrial intelligence, the search continues to captivate scientists and the public alike, spurring technological advancements and expanding our understanding of life in the universe. Future telescopes and space missions promise to bring us closer to answering some of the most profound questions of all time, potentially unlocking the mysteries of the cosmos and revolutionizing our understanding of life beyond Earth. The study of dark matter is more than just an inquiry into a curious phenomenon. It is an exploration into the very fabric of reality itself. What is this elusive substance composed of, and why does it appear to make up so much of the universe's mass? Every clue uncovered in the pursuit of understanding dark matter brings us closer to unraveling not only the mystery of this invisible force, but also to grasping the broader underlying structure of the cosmos. Dark matter's secrets hold the potential to revolutionize our understanding of the universe and the forces that govern its existence. The significance of dark matter is so profound that it has become a cornerstone of modern astrophysics, sitting at the very heart of questions that challenge the boundaries of human knowledge. The enigma of dark matter persists primarily because it is invisible. We cannot see it with any telescope or detect it through conventional means. Yet, despite its elusive nature, astronomers and physicists have found compelling evidence for its existence. The most profound clues come from the way galaxies behave. Observations reveal an odd phenomenon. The outer regions of galaxies, those farthest from the dense cores, rotate much faster than expected. If the motion of stars and gas in these outer regions were governed solely by the visible matter at the center, we would expect the stars to move more slowly. However, the outer stars spin at speeds that suggest there is much more mass within galaxies than what we can observe. This unseen mass exerts a gravitational pull that is detectable, though it remains completely invisible to conventional instruments. It's a mass that doesn't emit light or energy, and thus it remains hidden in plain sight, creating one of the most profound mysteries in the field of astrophysics. Similarly, when astronomers study galaxy clusters, they notice something equally puzzling. The gravitational forces that hold these massive structures together are far stronger than what can be accounted for by the luminous matter alone, the stars, gas, and visible objects that we can detect with telescopes. The dynamics of galaxy clusters suggest the presence of additional invisible mass that must be contributing to the overall gravitational pull. This unseen matter, like dark matter, has been hypothesized to be the missing ingredient that holds galaxy clusters intact, preventing them from flying apart as they would if only visible matter were present. Yet another crucial piece of the dark matter puzzle comes from the phenomenon of gravitational lensing. When light from distant galaxies passes through massive objects, such as a galaxy cluster or another large concentration of mass, its path is bent by the gravitational field of that object. The degree of bending depends on the mass of the object causing the curvature. This effect, known as gravitational lensing, has allowed astronomers to infer the presence of invisible mass. The amount of bending observed in light from distant galaxies suggests that more mass is present in galaxy clusters than can be directly seen. This mass is most likely dark matter, which doesn't emit, absorb, or reflect light, but still interacts gravitationally with the objects around it. Taken together, these observations provide a compelling case for the existence of dark matter. It suggests that there is an invisible substance lurking in the universe that interacts with normal matter through gravity. This substance plays a key role in shaping the structure and behavior of the universe, influencing the dynamics of galaxies, clusters of galaxies, and the very formation of the cosmic web. But even though dark matter is thought to make up approximately 27% of the universe's mass energy content, scientists still do not know exactly what it is made of. The hunt for dark matter is ongoing, and it is one of the most exciting and vital quests in modern science. Various experimental methods are being employed to detect and understand this mysterious substance. A prominent approach involves the use of large underground laboratories. These laboratories are situated deep beneath the Earth's surface, where the sensitive equipment used to detect dark matter is shielded from cosmic rays and other forms of interference. In these subterranean facilities, scientists use detectors made of materials that might interact with dark matter particles. The idea is that when a dark matter particle collides with an atom in the detector, it could generate a small flash of light or cause a tiny movement in the atom. These minute signals, if detected, could be evidence of dark matter's existence. Another method of searching for dark matter involves high-energy particle colliders, such as the Large Hadron Collider. In these powerful machines, particles are accelerated and smashed together at velocities close to the speed of light. The hope is that in these extreme conditions, new particles might be created, some of which could be dark matter particles or related phenomena. Scientists carefully analyze the aftermath of these collisions, searching for unexpected results that could indicate the presence of dark matter. Beyond these direct detection efforts, astronomers also use observational techniques to study the large-scale behavior of galaxies and cosmic structures. While dark matter cannot be observed directly, its gravitational influence on visible matter allows scientists to infer its presence. The rotation of galaxies and the behavior of galaxy clusters offer critical insights into how dark matter interacts with the visible universe. Through such observations, astronomers hope to uncover more clues about dark matter's nature and role in the cosmos. In addition to the search for dark matter, another profound mystery is dark energy. Dark energy is thought to be responsible for the accelerated expansion of the universe, a phenomenon that was first observed in the late 1990s. To grasp the concept of dark energy, imagine the universe as a balloon that is steadily inflating. The more you blow air into the balloon, the faster it expands. This is a good analogy for the universe's expansion, except that instead of air, dark energy is thought to be the force driving this acceleration. Although it makes up about 70% of the universe's energy content, dark energy cannot be directly observed. Its existence is inferred from the motion of galaxies and the cosmic microwave background, the faint glow left over from the Big Bang. The exact nature of dark energy remains elusive. Several theories have been proposed to explain it. One of the most prominent is the cosmological constant, originally introduced by Albert Einstein as part of his general theory of relativity. This theory posits that dark energy is a constant energy density that fills space uniformly. In this model, dark energy acts like a kind of tension in the fabric of space itself, pushing galaxies apart in a consistent manner throughout the universe. This model fits well with many observations, making it a strong contender for explaining dark energy's role. Another hypothesis is known as quintessence, which proposes that dark energy is not a constant but a dynamic field. Quintessence suggests that the energy density of dark energy could fluctuate over time, influencing the rate of expansion in varying ways across cosmic history. This theory envisions dark energy as something akin to a fluid that evolves, changing as the universe expands. Whether it is constant or dynamic, the presence of dark energy is critical to understanding the universe's future. If the accelerated expansion continues, it could eventually lead to a scenario where galaxies drift further and further apart and stars fade from view, leaving behind a cold and dark universe. Both dark matter and dark energy represent immense challenges to our understanding of the universe. Dark matter, invisible and detectable only through its gravitational effects, makes up a significant portion of the universe's mass, yet remains one of the greatest mysteries in science. It is this unseen mass that keeps galaxies from flying apart as they spin at incredible speeds. On the other hand, dark energy, a mysterious force behind the accelerated expansion of the universe, is an equally perplexing component of the cosmic landscape. It propels galaxies apart, causing the universe to stretch ever faster. Together, these phenomena represent a fundamental gap in our current models of physics. Traditional theories of gravity, based on the work of Newton and Einstein, struggle to account for these phenomena. These models predict certain behaviors based on the visible matter we can observe. But dark matter and dark energy imply that there is far more to the universe than what meets the eye. The presence of invisible mass and mysterious forces suggests that our understanding of space, time, and gravity is incomplete. As a result, scientists are beginning to look beyond the established theories, exploring innovative new concepts that could better explain the nature of the universe. This ongoing search to understand dark matter and dark energy not only pushes the boundaries of science, but also challenges our philosophical understanding of reality itself. It forces us to confront the idea that the universe is far more mysterious than we can fully comprehend. These phenomena highlight the limits of our current knowledge and demonstrate how much remains to be explored in the vast, uncharted realms of the cosmos. Some researchers are venturing beyond traditional explanations to investigate alternative models that might modify our understanding of gravity itself in an attempt to explain the phenomenon of dark energy. These novels propose that the current laws of gravity, which are based on Einstein's theory of general relativity, may need adjustments when applied to vast cosmic scales. They suggest that gravity could behave differently in the far reaches of space and time, particularly in the expansive regions where dark energy's effects are most pronounced. This adjustment in the gravitational framework aims to account for the universe's accelerating expansion without relying exclusively on the mysterious force of dark energy. In the world of theoretical physics, there are even more unconventional and mind-bending possibilities being explored. Some theories propose the existence of additional dimensions beyond the familiar 3 of space and 1 of time. In these models, the universe we experience could be just a tiny fraction of a far larger and more complex reality. These extra dimensions might interact with our universe in such a way that they produce phenomena similar to what we observe as dark energy. In other words, the effects of these hidden dimensions could create a force that influences the expansion of the universe, pushing galaxies further apart over time. As researchers continue to gather data from ever more sophisticated telescopes, experiments, and observational techniques, they strive to refine these theories. Each new discovery adds another piece to the puzzle, bringing scientists closer to understanding the true nature of dark energy. The quest to unravel this cosmic riddle is an ongoing endeavor, and with every new observation, the hope is that we will inch ever closer to unveiling the underlying forces that govern the cosmos. The answers that emerge could not only change how we perceive the universe, but also offer profound insights into the deepest questions of existence. Dark matter and dark energy stand as two of the most enigmatic and elusive components of the universe. They are critical to understanding the structure and fate of the cosmos, but their true nature remains shrouded in mystery. To visualize the impact of these unseen forces, imagine the universe as a colossal balloon. While it is expanding, it is also being pulled in different directions by invisible forces that we cannot directly observe. Dark matter acts like the scaffolding of the universe, providing the gravitational glue that binds galaxies and galaxy clusters together. Even though dark matter itself is invisible, its gravitational effects are unmistakable, and it shapes the very structure of the universe. One of the ways we can infer the presence of dark matter is by observing how galaxies rotate. Without the presence of dark matter, galaxies would spin at speeds so high that their stars would be flung out into space, unable to stay bound to the galaxy's center. Yet galaxies continue to rotate in a stable manner, implying that there's a hidden mass, dark matter, providing the extra gravitational pull necessary to hold them together. In contrast to dark matter, dark energy represents the force responsible for the accelerated expansion of the universe. This mysterious phenomenon behaves like a repulsive force, pushing galaxies away from each other and causing the universe's expansion to speed up over time. This expansion began shortly after the Big Bang and has been continuing ever since. Dark energy seems to grow stronger as the universe ages, dominating the expansion as the universe moves toward the distant future. Scientists have come to refer to dark energy as a form of cosmic repulsion, an influence that opposes the attractive force of gravity and is key to understanding the universe's long-term fate. Understanding dark matter and dark energy is essential not only for grasping the current state of the universe, but also for predicting how the cosmos will evolve in the future. Scientists are working tirelessly to uncover the true nature of these phenomena, as their discoveries hold the key to answering some of the most profound questions about the universe's destiny. Will the universe continue expanding forever, growing colder and emptier as dark energy continues to drive the acceleration? Or could the gravitational influence of dark matter eventually cause the expansion to slow down and reverse, leading to a dramatic collapse back into a singularity? Every new piece of data we gather about dark matter and dark energy brings us closer to unlocking the answers to these cosmic questions. The pursuit of these answers has the potential to radically reshape our understanding of existence itself, fundamentally altering our view of the universe's past, present, and future. Galaxies, the grand and intricate collections of stars, gas, dust, and dark matter, are central to the structure of the universe. The formation of galaxies began in the early universe, when tiny fluctuations in the density of matter led to the gravitational clumping of gas and dust. Over time, these clumps grew larger and denser, gathering more material through the force of gravity. Picture the process as pouring honey onto a flat surface. The honey forms blobs that eventually connect, forming larger pools. This is analogous to how galaxies start to take shape as the gas and dust come together, often becoming hot and collapsing into stars. These early stars are born in clusters, burning brightly for millions of years, and creating heavier elements through the process of nuclear fusion. As these stars reach the end of their lives, they explode in supernovae, scattering their newly created elements back into space. This process enriches the surrounding gas, making it ready for the formation of a new generation of stars. Over billions of years, galaxies evolve and change. They can merge with other galaxies, forming larger structures, much like two rivers joining together to form a larger one. These mergers can trigger new star formation as gases mix and compress, fueling the birth of new stars in the process. The interconnectedness of galaxies in the universe creates a complex and ever-evolving web, where each galaxy's gravitational pull can influence the formation and development of neighboring galaxies. As galaxies evolve, their shapes change as well. Some transform into spiral galaxies, characterized by their swirling arms of gas, dust, and stars, all revolving around a central bulge. Our own Milky Way is an example of a spiral galaxy. Others evolve into elliptical galaxies, which have a more rounded shape and typically contain older, dimmer stars with little new star formation. These elliptical galaxies can range from nearly spherical to more elongated shapes. Then there are irregular galaxies, which don't fit neatly into any specific category. These galaxies are often chaotic in appearance, lacking a distinct form, and may contain regions of active star formation. Irregular galaxies often arise from gravitational interactions, such as galactic collisions, which can distort their shape. Finally, there are lenticular galaxies, a blend between spiral and elliptical types. They have a central bulge like elliptical galaxies, but also feature a disk structure like spiral galaxies, though they lack the distinct spiral arms. Each of these galaxy types exhibits different characteristics not only in their shape, but also in the stars and processes taking place within them. As scientists continue to study these cosmic structures, they gain valuable insights into the evolution of the universe itself. Observing galaxies in various stages of development, from young, actively forming galaxies to older, mature ones, helps us understand how the forces of gravity, pressure, and star formation have shaped the cosmos over billions of years. Galaxies evolve in response to dynamic forces, reflecting the ongoing interplay between gravity, gas, and stellar birth. The universe's vastness is reflected in the incredible diversity of galaxies it contains. Each galaxy is unique, offering a distinct glimpse into the cosmic landscape and the processes that drive its formation and evolution. This diversity holds the key to understanding not only the history of the universe, but also the complex dynamics that govern its future. At the heart of understanding the universe's gravitational framework is the concept of space-time curvature. According to Einstein's theory of general relativity, massive objects like stars and planets warp the very fabric of space-time. Imagine space-time as a vast, flexible sheet stretched across the cosmos. When a heavy object, such as a planet or a star, sits on this sheet, it causes the fabric to bend or curve. The greater the object's mass, the deeper and more pronounced the curve. This curvature of space-time alters the paths of objects, drawing them toward the massive body, much like how a marble is drawn toward a bowling ball sitting on a curved surface. This is the essence of how gravity works, according to Einstein. But the curvature of space-time doesn't just affect the movement of objects with mass. It also impacts the flow of time itself. Near a massive object, time passes more slowly than in regions farther away. This fascinating phenomenon is known as time dilation and reflects the deep interconnectedness of space and time. They are not separate entities but are intertwined, forming a dynamic system that responds to the presence of mass. The curvature of space-time shows us that gravity is not a simple force pulling objects together. It's a complex warping of the very geometry of the universe, influencing both the motion of objects and the passage of time in its vicinity. Astronomers, armed with the understanding of space-time curvature, have an invaluable tool at their disposal: time dilation. This concept allows scientists to study distant cosmic events in a completely new way. Time dilation occurs because the flow of time is affected by both gravity and velocity. The faster an object moves, or the stronger the gravitational field, the more time can stretch or compress. When astronomers observe objects that are incredibly far away, such as distant stars or galaxies, they are essentially looking back in time. Light from these objects takes millions or even billions of years to reach us, so when we observe them, we are seeing them as they were long in the past. But time dilation also plays a role in the study of more dynamic and rapidly changing phenomena, such as supernovae or jets from black holes. When a supernova explodes, for example, the explosion unfolds at an incredible speed. If the explosion is moving away from us at a significant fraction of the speed of light, the light from the event becomes stretched, making it appear as though the event is taking longer than it actually did. By measuring the differences in how long these events appear to take, scientists can infer the speeds at which these cosmic phenomena are occurring and gain insights into the effects of gravity on them. In this way, time dilation offers astronomers a unique window into the past and a deeper understanding of the forces at play in the universe. It is one of the many ways in which general relativity continues to shape our exploration of the cosmos, revealing the hidden intricacies of space, time, and gravity. Time dilation is more than just a theoretical curiosity. It serves as a vital tool for astronomers striving to understand the vastness and complexity of the universe. Through this phenomenon, scientists can determine the distances between celestial objects, offering an unprecedented insight into the structure of galaxies and cosmic clusters. Time itself, it turns out, is not a constant across the universe. Its passage is affected by gravitational forces. As light from distant stars and galaxies travels through space, it interacts with these gravitational fields, stretching and compressing as it moves. This alteration provides astronomers with invaluable data, enabling them to measure the vast expanses of space with an accuracy that was once thought impossible. The concept of time dilation reaches beyond just the practical realms of measurement. It reveals a deeper truth about the universe. Space and time are not fixed, immutable concepts, but are deeply interconnected, forming the very fabric of our existence, known as space-time. This understanding is a relatively recent development, a product of the revolutionary breakthroughs in physics that began with Einstein's theory of relativity. For centuries, time was perceived as an unchanging and absolute constant, ticking away at the same rate everywhere in the universe. Space was similarly thought to be an empty, infinite expanse, independent of the forces that shape it. Yet, as our understanding of gravity and the nature of light grew, we came to realize that space and time are not separate entities, but are inextricably linked. This shift in our perception of the universe represents just the beginning. As technology advances and new discoveries emerge, our understanding of space and time will evolve. In particular, the study of black holes, gravitational waves, and quantum mechanics could drastically reshape our conception of how the universe works. These phenomena suggest that gravity, far from being just a force that pulls objects together, is capable of bending the very fabric of space-time, altering the flow of time itself. Black holes, in particular, offer a profound example of this. The immense gravitational pull of a black hole warps space and time around it, creating conditions where time slows down relative to regions far away from the black hole. This raises intriguing questions about the fundamental nature of time and the potential for time to behave differently in various parts of the universe. The ongoing research into quantum mechanics further complicates our understanding. This field, which explores the behavior of particles at the smallest scales, suggests that both space and time may not be as solid and unchanging as we once thought. Instead, they may be more fluid, capable of bending and stretching under certain conditions. This realization could lead to a complete rethinking of our understanding of cause and effect, potentially unveiling a universe far more dynamic and interconnected than we could have imagined. Technological advancements are also poised to revolutionize our exploration of space. Powerful telescopes and sophisticated computer simulations are already allowing us to peer deeper into the cosmos than ever before. As we explore regions of the universe that were once beyond our reach, we may uncover new mysteries, such as the nature of dark matter and dark energy, that challenge everything we thought we knew about space and time. These discoveries could reveal not only the composition of the universe, but also the fundamental forces that govern it. In the future, robotic missions to distant planets and even human exploration beyond our solar system will provide new perspectives on how time is experienced in different gravitational environments. Such experiences may offer unprecedented insights into the way time flows differently in space and how it affects the physical processes that sustain life. These advances hold the potential to unlock profound new insights about the nature of time, space, and existence itself. As we continue to explore the frontiers of science, the next few decades may bring breakthroughs that fundamentally change our understanding of the universe. From our present vantage point, these shifts in understanding may seem far away, but they are already on the horizon, waiting to transform the way we think about everything from the smallest subatomic particles to the most distant galaxies. The next phase of human exploration promises to reveal truths that could alter our very conception of reality. Nebula, vast clouds of gas and dust, are among the most stunning features in the universe, and they play an essential role in the life cycle of stars. These cosmic nurseries are the birthplace of stars and planetary systems, offering the raw materials necessary for the creation of new celestial bodies. Nebulae form in a variety of ways, but one of the most common processes involves the death of massive stars. When these stars exhaust their nuclear fuel, they explode in a dramatic event known as a supernova. The force of the explosion scatters the star's material into the surrounding space, enriching the gas and dust with heavy elements and creating a nebula. In addition to supernovae, nebulae can also form from the shedding of material by aging stars. These stars, particularly those that have become red giants, expel their outer layers into space as they approach the end of their life cycles. This material cools and spreads out, eventually forming what we call a planetary nebula. These nebulae are not the birthplace of planets, as their name might suggest, but they are critical in the broader process of star formation. Another crucial source of nebulae is the accumulation of gas and dust from the interstellar medium, the diffuse matter that exists between stars. This material serves as the foundation for new stars, and when it gathers together in sufficient quantities, it can collapse under its own gravity, forming the dense clouds that eventually give birth to new stellar objects. Nebulae are thus not just beautiful sights to behold. They are essential to the ongoing process of stellar evolution. Without nebulae, the universe would lack the diversity of stars and planetary systems that we see today. Quasars, one of the brightest and most powerful objects in the universe, are another crucial piece of the cosmic puzzle. At their cores, quasars harbor supermassive black holes surrounded by accretion disks of gas and dust. These accretion disks, which are heated to extreme temperatures by the gravitational forces at play, emit vast amounts of radiation, including X-rays. The energy output of a single quasar can be so intense that it can outshine entire galaxies. The study of quasars offers a unique window into the early universe. Many quasars are located at vast distances from Earth, meaning we observe them as they appeared billions of years ago, not long after the Big Bang. By studying the light emitted by quasars, scientists can learn about the conditions of the universe when it was still in its infancy. This light passes through the intergalactic medium, the vast expanse of space between galaxies, providing clues about the composition and density of the early universe. Quasars thus serve as cosmic beacons, illuminating the dark expanse of space and offering insight into the formation and evolution of galaxies. Pulsars, a type of neutron star, represent another class of objects in the universe. These dense remnants of massive stars undergo a supernova explosion, leaving behind a core that is so dense that it is compressed into a small, incredibly compact object. The mass of a pulsar can be greater than that of the Sun, yet it is only about as wide as a city. What makes pulsars so intriguing is their rapid rotation. As a pulsar spins, it emits beams of electromagnetic radiation from its magnetic poles. If these beams are oriented toward Earth, we detect them as regular pulses of radiation, much like how a lighthouse beam is only visible when it is pointed toward you. Some pulsars rotate so quickly that they complete multiple rotations per second, emitting pulses at a rhythmic pace. By studying the timing of these pulses, astronomers can learn about the pulsar's rotation speed, magnetic field strength, and even the environment surrounding it. The discovery of pulsars was a groundbreaking achievement in astrophysics, providing new insights into the behavior of neutron stars and the forces shaping the cosmos. Cosmic rays, high-energy particles that travel through space at nearly the speed of light, are yet another critical aspect of our understanding of the universe. These particles, primarily protons and atomic nuclei, originate from a variety of sources, including supernovae, active galaxies, and even our own sun. As cosmic rays travel through space, they interact with the matter they encounter, impacting everything from planetary atmospheres to human technology. One of the key roles of cosmic rays is in the formation of new elements. When cosmic rays collide with atoms in Earth's atmosphere, they trigger nuclear reactions that result in the creation of elements like carbon and nitrogen, key components in the chemistry of life. This process contributes to the chemical diversity that forms the foundation of organic matter and supports life as we know it. Cosmic rays also play a role in understanding the magnetic fields that pervade the universe. By studying how these particles interact with various regions of space, scientists can uncover the hidden forces that shape stars, galaxies, and even the large-scale structure of the universe itself. Each of these cosmic phenomena, from time dilation to nebulae, quasars, pulsars, and cosmic rays, offers a unique glimpse into the universe's vast complexity. Together, they form an intricate web of interactions and processes that continue to shape the cosmos. As we develop new tools and techniques for exploring the universe, our understanding of these phenomena will deepen, leading to discoveries that may one day transform our understanding of space, time, and the very nature of existence. Cosmic rays, often perceived as enigmatic and distant phenomena, hold a significant influence over our planet's climate. These rays, composed of high-energy particles from outer space, interact with Earth's atmosphere in complex ways that may affect weather patterns and even cloud formation. When these particles collide with the gases in the air, they ionize the molecules, creating charged particles known as ions. These ions act as nuclei around which water vapor can condense, forming clouds. It's this very interaction that connects cosmic rays to the creation of clouds, a pivotal aspect of Earth's weather systems. This process, while subtle, has spurred an ongoing investigation into how changes in the intensity of cosmic ray flux might influence long-term shifts in climate, offering a potential pathway to understanding climate change from a cosmic perspective. The study of cosmic rays extends beyond their atmospheric effects and into the very fabric of the universe itself. These rays, in addition to their role in climate dynamics, are key players in the synthesis of elements, processes fundamental to the formation of matter as we know it. By exploring cosmic rays, scientists delve deeper into the mysteries of cosmic phenomena, unraveling the complex interactions that shape the universe. The study of cosmic rays serves not just as a window into our own atmosphere, but as a portal to better understanding the vast and dynamic cosmos. Through these rays, we gain insight not only into the origin and evolution of elements, but also into the broader interwoven fabric of cosmic forces that dictate the behaviors of celestial bodies and the nature of space itself. Among the most violent and powerful explosions in the universe are gamma-ray bursts, extraordinarily intense flashes of energy that result from catastrophic cosmic events. Detecting these bursts requires a combination of cutting-edge technology and expert knowledge of cosmic occurrences. Instruments equipped to measure high-energy radiation are deployed in space, constantly scanning for these intense emissions that last anywhere from a fraction of a second to several minutes. These gamma-ray bursts send out a burst of energy across immense distances, often detected as brief flashes of light in the gamma-ray spectrum. The energy emitted during these bursts is mind-boggling in its scale and its intensity, offering a unique glimpse into some of the most violent phenomena known to science. The causes of gamma-ray bursts are often linked to two major events in the life cycle of massive stars. One leading cause is the collapse of a massive star at the end of its life cycle. When a star exhausts its nuclear fuel, it can no longer support itself against the pull of gravity. The core collapses and the outer layers of the star explode in a supernova. If the collapsing core is sufficiently massive, it can lead to the formation of a black hole. The matter that falls into this black hole is heated to such extremes that it produces powerful jets of energy, resulting in a gamma-ray burst. The second major cause of these bursts occurs when two neutron stars, a type of incredibly dense stellar remnant from an exploded star, collide. As these neutron stars spiral toward one another, their gravitational attraction draws them closer until they merge, releasing an enormous amount of energy, which can also lead to the emission of gamma rays. Both of these cosmic events are cataclysmic transformations that, when occurring, can be detected across vast distances, sometimes light years away. By studying these bursts, astronomers gain a better understanding of the origins of such extreme phenomena and their far-reaching impact on the cosmos. Through the examination of the gamma rays emitted and the light that follows them, they can gain valuable insights into the processes behind the violent deaths of stars and the formation of exotic objects like black holes. These studies reveal how the universe evolves on the largest scales and how these powerful events shape the galaxies and structures we observe today. Another fascinating celestial phenomenon that draws the interest of astronomers is the magnetar, a special type of neutron star. Neutron stars are already incredibly fascinating due to their extreme density, but magnetars take things even further with their magnetic fields, which are 1,000 trillion times stronger than the magnetic field of Earth. This remarkable intensity profoundly affects their behavior. Neutron stars themselves are born when a massive star runs out of fuel and explodes in a supernova. What remains after this explosion is an ultra-dense core that collapses into a neutron star. Despite the extraordinary density of a neutron star, about the mass of the Sun, squeezed into a volume no larger than a city, magnetars go one step further, exhibiting magnetic fields that dominate the surrounding space. These intense magnetic fields give rise to a variety of extreme phenomena, including powerful bursts of X-rays and gamma rays, much more energetic than anything typically observed from regular stars. These emissions are not random, but instead are related to the decay of the magnetar's magnetic field, which releases immense amounts of energy. This energy is so intense that it can be detected across vast distances of space. While neutron stars are generally stable in terms of their emissions, magnetars are unpredictable, exhibiting sudden and dramatic outbursts of energy that can vary wildly in terms of timing and intensity. The study of magnetars provides astronomers with a unique look into the nature of magnetism in space and the ways in which these fields shape the behaviors of celestial bodies. The merger of two black holes represents one of the most energetic and awe-inspiring events in the universe. When two black holes orbit one another and eventually collide, they release a burst of energy in the form of gravitational waves, ripples in the fabric of space-time that travel outward, carrying the signature of these cosmic events. The study of black hole mergers, particularly through the detection of gravitational waves, has opened up an entirely new field of astrophysics, enabling scientists to observe phenomena that were once thought to be completely invisible. By analyzing these waves, physicists have an unprecedented opportunity to test the predictions of general relativity, Einstein's groundbreaking theory of gravity. Black hole mergers provide an opportunity to see how gravity operates in its most extreme form, under conditions where the laws of physics are pushed to their limits. Moreover, black hole mergers hold the key to understanding the formation and evolution of black holes themselves. By studying the resulting black holes and their properties, scientists can gain insight into the complex life cycles of these enigmatic objects. Additionally, these mergers provide a valuable opportunity to learn more about the larger structure of the universe, particularly in terms of the distribution and density of dark matter. The impact of these mergers stretches far beyond the black holes involved, influencing the very fabric of the universe itself, and offering a new perspective on the origin and evolution of the cosmos. With each new observation, scientists are able to piece together a more complete picture of the universe, one that challenges existing models and refines our understanding of the fundamental forces that govern reality. For astronauts, living in space is an entirely different experience from life on Earth. The absence of gravity is perhaps the most immediate and challenging difference. In the weightless environment of space, astronauts float freely, making even basic tasks such as eating, sleeping, and moving more complicated than they would be on Earth. To adapt to this weightlessness, astronauts undergo extensive training both before and during their missions. They learn how to control their movements in zero gravity, ensuring that they can maneuver in their confined space without floating uncontrollably. Daily activities in space require specialized equipment like food that is prepackaged and carefully designed to prevent spillage. Drinking also presents a challenge, with astronauts using straws connected to pouches to drink liquids, since there is no gravity to pull the liquid down into their mouths. In space, the human body also undergoes significant changes due to the lack of gravity. Muscles and bones weaken over time because they no longer need to support the body's weight. To counteract this, astronauts engage in daily exercise routines using resistance machines and stationary bicycles to maintain muscle strength and bone density. They also monitor their diets closely to ensure they stay hydrated and maintain their nutritional balance. These physical challenges are compounded by psychological factors, such as the isolation and confinement of space missions. Being thousands of kilometers from home, with limited communication with loved ones and no physical contact with familiar surroundings, can take a mental toll on astronauts. As a result, they are carefully selected for their psychological resilience, undergoing extensive evaluations and training to help them cope with the stresses of space life. Regular communication with support teams on Earth helps mitigate some of the emotional strain, but the isolation remains a significant challenge. In addition to the psychological difficulties of space life, astronauts must also adapt to the unique conditions of microgravity. The effects of this low-gravity environment can be dramatic, including muscle atrophy and a decrease in bone density, which makes astronauts more vulnerable to fractures. Changes in the cardiovascular system can also occur, as the heart and blood vessels adjust to the reduced need for blood circulation in space. Upon returning to Earth, astronauts may experience a period of readjustment, as they reacquaint themselves with the force of gravity and the bustling environment of home. These challenges highlight the complexity of living and working in space, making space exploration not just a physical test, but a psychological and emotional one as well. Space exploration represents a remarkable endeavor, offering unparalleled opportunities to explore the mysteries of the universe. However, the unique challenges faced by astronauts, ranging from the physical effects of microgravity to the psychological stress of isolation, are profound and must be addressed to ensure the success of future missions. The ongoing study of space and its impact on human beings not only enriches our understanding of the cosmos, but also paves the way for the next generation of explorers to thrive in this challenging and ever-expanding frontier. In the vast expanse of space, where humanity's curiosity and ambition collide with the unknown, the quest to explore and settle on other planets brings with it both awe-inspiring opportunities and immense challenges. As we push the boundaries of our reach beyond Earth, we must confront not only the physical demands of space travel, but also the psychological, biological, and technological hurdles that come with living in an environment so radically different from our own. These challenges must be addressed with meticulous planning, innovative solutions, and perhaps most crucially, a deep understanding of how the human body and mind react to the unforgiving conditions of space. One of the most significant aspects of space travel is how the human body responds to microgravity, or the near weightlessness experienced in orbit. The fluid distribution in the body undergoes a dramatic shift in such conditions. Bodily fluids, including blood and water, tend to move upwards towards the upper body, particularly the face. This phenomenon often leads to a puffy appearance, which can be unsettling for astronauts, as their faces become visibly altered by the redistribution of fluids. This alteration doesn't just affect appearance, it can also have functional consequences. For example, astronauts often report changes in their vision, including blurred eyesight due to the pressure exerted by the fluids in the head. These visual disruptions may persist for a time after the astronaut returns to Earth, adding another layer of complexity to the long-term effects of space travel on the human body. Yet, the physical effects are only part of the story. Space missions, particularly those that involve long durations, can take a significant toll on astronauts' mental health. The isolation and confinement inherent in space travel are profound, as astronauts are cut off from their families, friends, and the world they know. With limited social interactions and a highly controlled environment, feelings of stress, anxiety, and even depression can arise. The psychological strain of being so far from Earth, with no immediate help or escape from the environment, can be challenging to manage. These mental health concerns must be taken into account when designing long-term missions to other planets, such as those destined for Mars, where astronauts may be isolated for months or even years at a time. Addressing these biological and psychological challenges is essential if we are to successfully embark on extended space missions. Engineers and medical scientists are working tirelessly to develop strategies and technologies that mitigate these effects. Ensuring astronauts can maintain both their physical and mental health throughout their missions is crucial to the success of human exploration of other worlds. One of the foremost goals of space exploration is to ensure the survival of human life on another planet. This ambition demands a suite of technological advancements, each more complex and intertwined than the last. First, there are the life support systems, essential technologies that must provide astronauts with breathable air, clean water, and nourishing food. In the closed, isolated environment of a spacecraft or a planetary habitat, traditional methods of resource consumption and waste disposal are no longer viable. The challenge, then, is to develop closed-loop systems that recycle and reuse vital resources without the need for constant resupply from Earth. Imagine a scenario in which every breath taken, every drop of water consumed, and every bit of waste produced is captured, purified, and reused. Such systems will be the cornerstone of sustainable life support on other planets, reducing reliance on Earth and ensuring that astronauts can survive without constant outside intervention. Another critical area of development is the production of food in space. Growing food in the harsh environments of other planets, where soil and traditional farming methods are unavailable, presents a significant hurdle. However, through innovations like hydroponics and aeroponics, which use nutrient-rich water or mist to nourish plants without soil, food production in space is becoming increasingly feasible. These methods not only provide food, but also contribute to the creation of a sustainable ecosystem by supporting oxygen production and absorbing carbon dioxide. Such systems could support long-term human habitation on planets like Mars, where astronauts would need to rely on locally produced resources to survive. These agricultural technologies could represent a key factor in ensuring that human life on other worlds is not only possible, but also sustainable. As essential as food and water are, astronauts will also need habitats to protect them from the hostile environments of distant planets. These habitats must shield them from extreme temperatures, radiation, and the dangers posed by dust storms. To meet these challenges, engineers are looking to advanced materials and designs inspired by the principles of physics and engineering to create living spaces that are not only durable, but also energy efficient. On Mars, where temperatures can dip drastically, these habitats must be capable of retaining warmth and maintaining a livable atmosphere despite the inhospitable surroundings. Similarly, these habitats will need to provide protection from the constant bombardment of cosmic radiation, which is far more intense on Mars than on Earth due to the lack of a thick atmosphere or magnetic field. Energy is another cornerstone of space exploration. On Earth, we rely on a variety of power sources, from fossil fuels to renewable energies like solar power. But in space, particularly on distant planets like Mars, sunlight is much weaker, and the availability of energy must be approached in new ways. Solar panels will need to be adapted for use on planets where the sun's rays are less intense or more diffuse. Furthermore, alternative power sources, such as nuclear energy, may offer a more reliable and potent solution for long-term energy needs. Even tapping into a planet's own resources, such as harnessing geothermal energy on Mars, could provide a sustainable energy source for colonies. Transportation technology is also a critical component of space exploration, both for moving people and supplies on other planets and for traveling to and from Earth. Rovers and other advanced vehicles will need to be designed to navigate the varied terrain of planets like Mars, where rugged landscapes and unpredictable conditions pose significant obstacles to movement. These vehicles must be capable of carrying astronauts safely across vast distances, while also being able to transport vital resources like food, water, and equipment. Systems for safely transporting cargo between Earth and the colony, as well as between colonies on different planets, will be crucial in ensuring that these missions are not only possible, but sustainable over the long term. Lastly, communication systems capable of operating over vast distances are essential for maintaining contact with Earth. On Mars, for instance, a round-trip communication delay could range from 13 to 24 minutes, depending on the planet's relative positions. This delay would make real-time communication nearly impossible, and it highlights the importance of autonomous systems that can function without immediate feedback from Earth. Despite these technological hurdles, maintaining a line of communication with mission control will be essential for the success of long-term missions. The dream of human settlement on Mars, or any other planet, is a tantalizing vision that has inspired scientists, engineers, and enthusiasts around the world. Various space agencies and private organizations are already working on plans to establish a human presence on the red planet with the goal of creating a sustainable habitat that would allow humans to not only survive, but also thrive in such a harsh environment. One possibility for achieving this goal is the deployment of advanced robotic teams that could prepare the Martian landscape for human arrival. These robots could build habitats, extract water from the soil, and even generate energy from the sun, creating an infrastructure that would support human life before astronauts set foot on Mars. Yet, settling on Mars is no small feat. The planet's atmosphere is incredibly thin, consisting mostly of carbon dioxide, and it is incapable of supporting human life without the aid of life support systems. Additionally, the lack of a magnetic field and a thick atmosphere means that the surface of Mars is constantly exposed to harmful cosmic radiation. Therefore, any human settlers will require highly advanced protective habitats to shield them from these dangers. These shelters must be built from durable materials capable of withstanding the Martian elements and protecting their inhabitants from radiation. Another significant challenge is transportation. Getting humans to Mars will require powerful rockets and spacecraft that can withstand the long journey through space. The trip could take several months, and maintaining life support systems over such a long period will require innovative solutions for food, water, and waste management. The spacecraft itself must be designed to handle the stresses of extended travel and ensure that astronauts remain healthy throughout the journey. Health, too, poses unique challenges on Mars. The planet's gravity is only about 38% that of Earth's, which means that astronauts would experience long-term effects on their muscles and bones. Muscle atrophy and bone density loss are serious concerns for anyone spending extended periods in reduced gravity. To address these effects, astronauts will need specialized fitness regimens and nutritional plans designed to mitigate muscle and bone loss. Similarly, the isolation of life on Mars could lead to significant psychological challenges, as astronauts may feel disconnected from their loved ones and isolated from the Earth. Mental health will need to be prioritized, with regular communication with Earth, social activities, and recreational spaces incorporated into the design of Martian habitats. Despite these considerable challenges, the vision of a human settlement on Mars is becoming more attainable with each passing year. As we advance technologically, we move closer to creating the infrastructure necessary to support human life on another planet. However, the idea of sending humans to live on Mars or any other celestial body also raises important ethical considerations. What rights will these settlers have? How will we ensure the preservation of any potential alien life forms, even if microscopic, that might exist on Mars or other planets? Furthermore, there are the moral questions surrounding the safety of the individuals who undertake these missions. What will be their responsibility, and how can we protect their well-being over long periods of space travel? These are just some of the ethical questions that humanity must confront as we look toward the future of space exploration and colonization. There are also social and economic implications to consider. If space missions are funded primarily by private corporations, will the benefits of living on Mars be accessible to everyone, or will only the wealthy few have access to the resources and opportunities offered by space colonization? The potential for new forms of inequality must be addressed, ensuring that the advancements in space exploration do not exacerbate the disparities that already exist on Earth. As we look ahead to the possibilities of human life on other planets, we must recognize the monumental task before us. The challenges are immense, but with each new innovation, each new mission, and each new step forward, we bring ourselves closer to realizing the dream of human settlement beyond our home planet. The path to Mars and beyond is a journey that will define the future of human civilization, shaping the legacy of exploration for generations to come. As humanity stands on the threshold of an ambitious and uncertain future, we must pause and reflect on the deeper motivations driving our exploration of the cosmos. What propels us to reach out to the stars? Is the push for colonization truly fueled by a desire to expand human knowledge and experience? Or is it perhaps an escape from the mounting crises we face on Earth? Is our drive to venture into the great unknown a reflection of our collective curiosity? Or are we, in some ways, attempting to outrun the problems that plague our planet? This introspection is essential as we prepare for what could be the next monumental chapter in human history. Looking to the stars, we must ensure our ambitions are anchored in a thoughtful consideration of ethics. Our responsibility extends far beyond the technical challenges we face, encompassing a duty to do no harm, to respect all forms of life, and to promote equity and fairness within our own species. As we take these colossal steps toward becoming a multi-planetary civilization, it's crucial to remember that our actions in space must reflect our highest values and principles. The pursuit of knowledge, while exciting, must not come at the expense of the well-being of our fellow humans or the ecosystems we encounter. Throughout the history of space exploration, we have witnessed an array of landmark achievements that have profoundly shaped our understanding of the universe and our place within it. One of the earliest and most iconic milestones was the launch of Sputnik, the Soviet satellite that marked humanity's first venture into space. This event, which occurred in 1957, not only initiated the space race, but also opened the door to an era of unprecedented scientific discovery. Sputnik's launch was a clarion call for the world, signaling the dawn of a new age where space, once an unreachable frontier, was now a domain for human exploration. Soon after, the human aspect of space exploration began to take shape. In 1961, Yuri Gagarin, a Soviet cosmonaut, became the first human to orbit Earth, demonstrating that it was indeed possible for humans to survive and function in outer space. This remarkable achievement ignited a spark of public interest in space travel, transforming it from a technical curiosity into a global aspiration. The very idea that humans could venture beyond the confines of Earth and live to tell the tale captured the imagination of people everywhere. The crowning achievement of the Apollo program, which culminated in the historic landing of humans on the moon in 1969, marked another monumental step forward in humanity's spacefaring journey. Neil Armstrong and Buzz Aldrin's footprints left an indelible mark on the lunar surface, symbolizing not only our ability to reach another celestial body, but also showcasing our potential to explore distant worlds. The moon landing demonstrated that the seemingly impossible could indeed be made real, and opened the door to further exploration beyond Earth's orbit. In recent decades, our focus has shifted to Mars, the red planet, which has long been a subject of intrigue for astronomers and scientists alike. Robotic missions, such as the Spirit and Opportunity rovers, have provided groundbreaking data about the Martian landscape, revealing tantalizing clues that suggest Mars may have once hosted flowing water. These missions have laid the foundation for the future exploration of Mars, fueling speculation about the planet's potential to support life in its distant past. More recently, the Curiosity rover has continued the exploration of Mars, sending back captivating images and conducting experiments that offer new insights into the planet's history. Through its instruments, scientists have been able to probe the Martian soil, search for signs of water, and analyze the planet's atmosphere, all of which continue to refine our understanding of Mars as a potential candidate for human settlement. Another cornerstone of humanity's ventures into space has been in the development and maintenance of the International Space Station, ISS. This unique laboratory orbits our planet and serves as a symbol of international collaboration, providing researchers from around the world with a microgravity environment in which to conduct experiments that would be impossible to replicate on Earth. The ISS has led to advancements in a variety of fields, from medicine and technology to basic biological research. It has helped us understand how the human body adapts to the unique conditions of space, providing invaluable data for future missions to distant destinations like Mars. Exploration of our solar system has also been propelled by robotic missions that have expanded our knowledge of the gas giants and their moons. The Voyager spacecraft, for instance, sent back detailed images and data from Jupiter, Saturn, and their moons, which revolutionized our understanding of these distant worlds. Voyager's mission, which has lasted for more than 4 decades, has provided a continuous stream of information, furthering our understanding of the outer reaches of our solar system. One of the most exciting recent developments has been the New Horizons mission, which brought humanity closer to Pluto than ever before. The spacecraft, which completed a historic flyby of the dwarf planet in 2015, delivered a wealth of fascinating data, providing insights into Pluto's atmosphere, surface composition, and its relationship with the other bodies in the Kuiper Belt. These achievements are not just technical marvels, they are proof of our limitless potential. As we continue to push the boundaries of space exploration, each new mission builds upon the successes and lessons of those that came before. The promise of returning humans to the moon and eventually sending crewed missions to Mars is a testament to the progress we have made and the exciting possibilities that lie ahead. These endeavors do not just expand our scientific knowledge, they inspire generations to look up to the stars and imagine what lies beyond the confines of our home planet. Technological advancements have also played a crucial role in transforming our view of the cosmos. The development of modern telescopes has dramatically expanded our ability to observe the universe, allowing us to peer deeper into space than ever before. These advanced instruments, which can detect a wide range of wavelengths, from visible light to infrared and ultraviolet radiation, enable astronomers to study celestial bodies that were once beyond our reach. The ability to observe across the entire electromagnetic spectrum has revolutionized our understanding of stars, galaxies, and other cosmic phenomena. One of the most significant breakthroughs in telescope technology has been the development of larger mirrors. A bigger mirror can collect more light, allowing astronomers to observe fainter stars and distant galaxies. To understand the importance of this, imagine trying to spot a candle flickering in the distance on a dark night. The more light you can gather, the clearer that tiny flicker becomes. Similarly, larger telescopes allow scientists to capture more light from distant objects in the cosmos, providing them with unprecedented levels of detail and clarity. Another key advancement in telescope technology is adaptive optics, a system designed to correct the distortions caused by the Earth's atmosphere. Just as looking through a fish tank can result in a distorted view if the water is moving, the atmosphere can blur the images seen through a traditional telescope. Adaptive optics help to clear this distortion, providing astronomers with sharp, focused images of distant stars and galaxies, allowing them to study cosmic objects with remarkable precision. Space-based telescopes, like the Hubble Space Telescope, have revolutionized our ability to study the universe. By positioning telescopes beyond the Earth's atmosphere, we are no longer limited by weather, light pollution, or atmospheric interference. The Hubble Space Telescope in particular has provided stunning images and critical data about everything from the life cycles of stars to the expansion of the universe itself. These observations have fundamentally changed our understanding of the cosmos. Modern telescopes are also equipped with sophisticated computer systems and imaging technologies that allow real-time data analysis. This has enabled astronomers to observe and track astronomical events as they unfold. For example, supernova explosions and asteroid behavior can be monitored more efficiently than ever before, providing scientists with the tools to make more accurate predictions and deepen our understanding of the universe. The International Space Station, with its unique microgravity environment, has become a vital research hub, offering insights into everything from human health to advanced materials science. The station provides scientists with a one-of-a-kind platform to study how living organisms, including humans, adapt to the conditions of space. This research is particularly important as we prepare for longer missions to places like Mars, where astronauts will face extended periods of isolation and exposure to harsh conditions. In addition to its role in advancing scientific knowledge, the ISS has also become a testing ground for technologies that could support future exploration missions. These innovations, ranging from life support systems to radiation shielding, are crucial for ensuring the safety and well-being of astronauts on long-duration missions. The research conducted on the ISS has not only advanced space exploration, but has also had far-reaching applications here on Earth, from medical breakthroughs to better understanding climate change. Perhaps one of the most significant aspects of the ISS is its role in fostering international collaboration. Scientists from around the world work together, sharing knowledge and resources in the pursuit of a common goal. This spirit of cooperation not only accelerates scientific progress, but also serves as a powerful reminder of the potential for unity in the face of global challenges. As nations come together to explore the cosmos, they reinforce the idea that knowledge, not conflict, should be humanity's guiding star. Robotic missions, too, are a vital part of our exploration of distant worlds. Unlike human missions, which require life support and safety measures, robotic spacecraft can venture to places that are inhospitable or far beyond the reach of current human technology. These missions are invaluable for gathering data about the composition, geology, and potential habitability of distant planets and moons. By sending robotic probes to explore these far-flung worlds, we are able to gather critical information without the risks associated with human travel. In addition to providing us with a wealth of data, robotic missions also serve as testing grounds for technologies that may one day support human exploration. For example, spacecraft that land on other planets can deploy rovers or conduct experiments that help scientists better understand the conditions of these alien environments. By sending robots to the far reaches of our solar system, we are not only learning about distant worlds, but also preparing for the future of human space exploration. These robotic explorers, alongside their human counterparts, are propelling humanity forward into the vast unknown, unlocking secrets of the cosmos that were once unimaginable. They help us push the boundaries of our understanding, revealing new possibilities for the future of space exploration. As we continue to learn from these missions, we move closer to the day when humanity will truly become a multiplanetary species, reaching for the stars with curiosity, hope, and determination. Robotic missions in space have transformed our understanding of the universe and our capacity for exploration. These technological marvels, capable of venturing to distant worlds, are equipped with an astonishing array of scientific instruments that elevate their potential. Through innovation, they enhance our ability to gather data, perform experiments, and analyze distant environments in ways that were once unimaginable. For example, Mars rovers that traverse the surface of the red planet are not merely tools of observation. They are mobile laboratories equipped with advanced chemical analysis tools capable of conducting real-time tests on Martian soil. These rovers collect invaluable data that not only enrich our understanding of Mars's geology, but also provide insights into the potential for life beyond Earth. The ability to test theories about life in extreme environments is one of the most exciting aspects of robotic exploration. By simulating the harsh conditions found on distant moons like Europa or on celestial bodies such as Titan, these missions allow scientists to experiment with the fundamental processes that may have given rise to life beyond our home planet. Through these experiments, we gain critical insights into how life might develop in other parts of the cosmos, far from the nurturing atmosphere of Earth. Robotic missions, therefore, serve not only as tools of exploration, but also as harbingers of a future where human presence in deep space could one day become a reality. These machines are breaking boundaries, advancing our scientific frontiers, and laying the groundwork for human exploration, ultimately helping us to better understand our place in the vast expanse of the universe. Looking to the future, the landscape of space exploration is set for an even greater revolution. A number of upcoming missions are poised to fundamentally reshape our understanding of the universe. One of the most anticipated endeavors is NASA's Artemis program, a mission that promises to return humans to the moon for the first time in more than 50 years. The mission's goals go beyond mere exploration. It is part of a larger plan to establish a sustainable presence on the lunar surface. This ambitious venture is designed to set the stage for future missions to Mars by testing technologies that will support deeper space travel. As part of this initiative, NASA plans to study the moon's resources, which could play a crucial role in supporting long-duration human missions to other planets. In addition to the Artemis mission, another monumental project is the James Webb Space Telescope, JWST, which represents a leap forward in our ability to observe the cosmos. Unlike its predecessor, the Hubble Space Telescope, JWST will primarily observe infrared light, allowing it to peer through dense clouds of gas and dust that obscure our view of the distant universe. This unprecedented ability will enable scientists to explore the early universe in greater detail, offering a glimpse into the formation of stars and galaxies. In addition, JWST may even help identify the atmospheres of exoplanets, bringing us closer to answering the age-old question of whether life exists elsewhere in the universe. With its powerful instruments, the JWST will undoubtedly provide answers to some of the most fundamental questions about the nature of the cosmos and our place within it. Another significant mission on the horizon is the Jupiter Icy Moons Explorer, or JUICE, a spacecraft designed by the European Space Agency to study 3 of Jupiter's largest moons, Ganymede, Europa, and Callisto. These moons are believed to harbor subsurface oceans beneath their icy exteriors, making them prime candidates in the search for extraterrestrial life. By examining the geological and environmental conditions on these moons, scientists hope to gain a deeper understanding of the potential for life in environments that are vastly different from Earth. The exploration of these distant moons is expected to yield critical information that could revolutionize our understanding of habitability and the conditions necessary for life to thrive beyond our planet. Private companies have also emerged as significant players in the realm of space exploration, fundamentally altering the landscape of how we approach space travel. Historically, space missions were the domain of government agencies like NASA and the Russian space program. But the advent of commercial enterprises has injected fresh ideas, new technologies, and a spirit of innovation. Companies like SpaceX and Blue Origin are pushing the boundaries of space travel, making it more affordable, accessible, and technologically advanced. SpaceX, founded by Elon Musk, has dramatically disrupted the space industry with its development of reusable rockets. This breakthrough innovation allows the same rocket to be launched multiple times, significantly reducing the cost of space travel and enabling more frequent missions. The ability to reuse rockets is a game changer, making it economically feasible to launch payloads into space at a fraction of the cost it once took. SpaceX has also made headlines by successfully relocating cargo to the International Space Station, demonstrating that private companies can now play a vital role in space research and collaboration with government agencies. Blue Origin, founded by Jeff Bezos, has taken a different approach by focusing on making space travel accessible to everyone, not just professional astronauts. The company's New Shepard rocket is designed for suborbital flights, offering civilians the opportunity to experience a few minutes of weightlessness. This growing emphasis on space tourism represents a shift in how we think about the cosmos, not just as a domain of scientific exploration, but as a potential destination for leisure and personal experience. In addition to its focus on space tourism, Blue Origin is working on developing technologies that could one day support human missions to the Moon and Mars, contributing to the broader vision of expanding humanity's presence beyond Earth. These private companies are also driving technological advancements at a pace that was previously unimaginable. The competitive atmosphere they foster has accelerated the development of new technologies, bringing the dream of interplanetary colonization closer to reality. SpaceX, for example, is working on its Starship program, which aims to facilitate human travel to Mars and establish a permanent human presence on the Red Planet. This ambitious vision of Mars colonization is inspiring global interest in space exploration, sparking new discussions about the future of humanity and the potential for interplanetary living. The advancement of space travel is also being shaped by the development of new propulsion technologies. Traditional rockets, which rely on chemical propulsion, are limited in both speed and efficiency. While they are capable of sending spacecraft into space, they require massive amounts of fuel, making them inefficient for long-distance missions. Advanced propulsion systems, such as ion drives and plasma propulsion, are changing the way we think about space travel. These systems use electricity to accelerate ions or plasma, creating a continuous, efficient thrust that allows spacecraft to travel farther and faster than ever before. With these systems, missions to distant planets like Mars or even the outer reaches of the solar system could become a reality. One of the most exciting developments in propulsion technology is nuclear thermal propulsion. By using heat generated from nuclear reactions, this technology can produce significant thrust and is far more efficient than traditional chemical engines. Nuclear thermal propulsion could revolutionize human space exploration, particularly for crewed missions to distant destinations. It would reduce travel times, minimize the risks of long-duration flights, and mitigate challenges such as exposure to harmful radiation and the psychological effects of isolation during deep space missions. As scientists continue to refine these advanced propulsion technologies, the prospect of sending humans to Mars, the outer planets, and beyond becomes increasingly plausible. The ultimate frontier of space travel lies in concepts like antimatter propulsion. Though still theoretical, antimatter has the potential to produce vast amounts of energy, potentially propelling spacecraft at speeds approaching the speed of light. If this technology comes to fruition, it could make interstellar travel a reality, allowing humanity to explore other star systems within a single lifetime. The possibility of traveling to distant stars and planets is a tantalizing prospect, one that could reshape humanity's destiny in the cosmos. As propulsion technologies evolve, the boundaries of human exploration will continue to expand, allowing us to venture deeper into space and make discoveries that were once confined to the realm of science fiction. The future of space exploration is being shaped by a diverse array of technological, scientific, and commercial innovations. With robotic missions, cutting-edge telescopes, ambitious lunar missions, and the emergence of private companies, humanity's reach into space is growing faster than ever before. These advancements are not just pushing the boundaries of science and technology, but are also fueling our imagination, inspiring us to dream bigger and bolder. As we continue to explore the cosmos, each new discovery brings us closer to understanding the mysteries of the universe, our place within it, and the potential for life beyond Earth. The next chapter in humanity's journey into space is unfolding before our eyes, and it promises to be nothing short of extraordinary. In recent years, private companies have become significant players in the space industry, driving forward groundbreaking advancements and fostering new collaborations that leverage both private capital and governmental expertise. This unique synergy between the private sector and government agencies has not only led to improved space missions, but has also expanded the possibilities of space exploration in ways previously unimaginable. These partnerships have had a particularly profound impact on larger scale projects, such as the construction of lunar bases and the facilitation of human missions to Mars. By tapping into the innovation and cost-saving technologies that private companies bring to the table, the space industry has entered a new era, one that holds the promise of greater accessibility, sustainability, and a more competitive environment for exploration. This transformation is not merely altering the way we explore the stars, but is actively shaping the future of humanity's endeavors beyond Earth. Space, though rich with potential and wonders, also harbors a myriad of risks, some of which pose existential threats to life on our planet. Among the most formidable dangers are asteroids and comets, celestial objects that often travel at extraordinary speeds, making collisions with Earth a constant concern. The potential consequences of such impacts could be catastrophic. From large-scale destruction to the potential extinction-level events that have historically been linked to cosmic collisions, most notably the extinction of the dinosaurs, these threats remain a significant focal point for scientific research and preparedness. Such impacts have the potential to trigger seismic shifts in the environment, disrupt ecosystems, and alter the course of life on Earth forever. Another critical risk associated with space exploration is solar flares, which are bursts of energy and charged particles emitted by the sun. These solar events can have far-reaching effects, especially when directed toward Earth. Solar flares are not just a threat to space explorers. They also pose a significant danger to the communications infrastructure we rely on daily. From GPS systems that guide our travels to the satellites that transmit television signals, solar flares can cause severe disruptions to these technologies, leading to widespread consequences. In extreme cases, powerful solar storms could disable entire electrical grids, leaving large portions of the planet without power, disrupting daily life and creating a cascade of challenges in every sector of society. In addition to solar flares, the threat of cosmic radiation is a constant presence beyond the protective shield of Earth's atmosphere. While our planet's magnetic field and atmosphere provide substantial defense against this radiation, astronauts venturing into space and even aircraft flying at high altitudes are not afforded the same protections. Cosmic radiation can penetrate their shielding and interfere with biological tissues, increasing the risk of serious health complications, including cancer. This added layer of danger underscores the complexities involved in planning long-duration missions to other planets or moons. Lastly, space debris represents a growing hazard in Earth's orbit. As humanity continues to launch satellites, spacecraft, and other equipment into space, remnants from past missions, such as discarded rocket stages, defunct satellites, and fragments from collisions are accumulating. These objects travel at speeds that can exceed tens of thousands of kilometers per hour, meaning that even small fragments of debris have the potential to cause severe damage to operational spacecraft, satellites, or the International Space Station itself. The increasing density of objects in low Earth orbit raises the risk of collisions, which could not only damage existing infrastructure but also create new debris, further exacerbating the problem. These threats, while daunting, are not insurmountable. Scientists and engineers have developed a variety of strategies to monitor and mitigate the risks posed by asteroids, comets, solar flares, and space debris. A primary method of asteroid detection involves the use of powerful telescopes and radar systems that scan the sky for objects that may pose a threat. When an asteroid is detected, its position is recorded over time to calculate its orbit and predict its trajectory. These models are continuously refined as more data is gathered, increasing the accuracy of predictions regarding potential impacts. Collaboration between international observatories and space missions plays a vital role in improving asteroid detection and tracking. When an asteroid is determined to be on a potential collision course with Earth, scientists assess the situation by evaluating the size, speed, and composition of the object. Several potential mitigation strategies are then considered, ranging from changing the asteroid's path to preparing for the impact in a way that minimizes damage. One of the most promising approaches to asteroid deflection is the kinetic impactor technique. This involves sending a spacecraft to collide with the asteroid at high speed, effectively altering its trajectory. The force of impact could nudge the asteroid onto a safer path, much like a player might gently tap a bowling ball to steer it toward a different lane. Another possible method is the gravitational tractor, in which a spacecraft would use its own gravitational pull to subtly change the asteroid's orbit. This technique would take longer to achieve results, but it presents the potential for a more controlled, non-destructive approach to asteroid deflection. For more extreme cases, scientists have also explored the idea of using nuclear devices to redirect an asteroid. This method, while potent, is often considered a last resort due to the potential risks and complexities involved. The explosion of a nuclear device near an asteroid could either break it apart or push it off course, depending on the size and proximity of the object. International cooperation plays a pivotal role in these efforts. Countries around the world are sharing data and resources to improve our collective ability to predict and respond to asteroid threats. By working together, we create a robust and multifaceted defense system that improves our chances of protecting Earth from cosmic hazards. Space weather, another significant phenomenon in space exploration, refers to the environmental conditions in space that are influenced by the sun's activity, such as solar flares and coronal mass ejections. These events release vast amounts of energy and charged particles into space, which can interact with Earth's magnetic field and atmosphere, leading to various effects on our planet. One of the most noticeable consequences is the disruption of communication systems, particularly satellite-based services. GPS navigation, television broadcasts, and even mobile phone signals can all be affected by space weather, making communication difficult or even impossible during severe solar events. The electrical infrastructure on Earth is also vulnerable to space weather. Geomagnetic storms induced by solar flares can generate electrical currents that flow through long power lines, potentially damaging transformers and other critical components of the electrical grid. In extreme cases, this could lead to widespread power outages, disrupting everything from transportation systems to healthcare services. The sudden surge of energy can overwhelm power systems much in the same way that a massive wave might flood a coastal city. Radiation from solar storms also poses a threat to the health of astronauts in space. While the Earth's atmosphere offers protection, it is not as effective at shielding those in space, where exposure to high levels of radiation could lead to long-term health problems. On the ground, the atmospheric shield protects us, but intense solar events can still affect our health, particularly in areas where space weather leads to beautiful though hazardous phenomena like the aurora borealis. Space weather also impacts navigation systems, as high-frequency radio signals, critical for aviation and maritime navigation, can be distorted or blocked. Imagine trying to use a compass during a thunderstorm. Space weather can throw pilots and sailors off course, potentially causing accidents or delays in critical operations. As we continue to make strides in space exploration, space debris remains a formidable challenge. The sheer number of satellites and spacecraft currently orbiting Earth increases every year, raising the risk of collisions that can create even more debris. This cascade effect is known as the Kessler syndrome, where the density of objects in low Earth orbit becomes so high that collisions between objects become common, making large parts of space unusable for future missions. This growing threat has led space agencies and private companies to develop sophisticated tracking systems capable of monitoring debris in real time. By predicting the paths of these objects, mission planners can devise strategies to avoid potential collisions, even if it means altering the trajectory of spacecraft, which requires additional resources and fuel. Ensuring that space remains a safe and viable environment for exploration will require continued innovation, careful planning, and international cooperation. As humanity ventures further into the cosmos, it is essential to remain vigilant and proactive in managing these risks. The more we understand space and the dangers it holds, the better prepared we will be to protect our planet and ensure the success of future missions. Whether it's monitoring asteroid trajectories, mitigating the effects of space weather, or cleaning up the growing mess of space debris, Our ability to address these challenges will ultimately determine how far we can go in our exploration of the final frontier. In the realm of space exploration, a significant challenge has emerged as debris in Earth's orbit increasingly threatens the safety and viability of missions. The growing risk of collisions with debris has made designing spacecraft that can withstand these impacts a priority. This shift in focus brings with it substantial engineering challenges and, naturally, increased costs. As the amount of space debris continues to grow, it has become evident that innovation is the key to finding solutions. Researchers and engineers have been brainstorming various strategies to address this issue, with some exploring ways to actively remove debris from orbit. Technologies like nets, harpoons, and other capture methods are currently being developed that could deorbit defunct satellites, reducing the risk of accidents in space. Moreover, the global nature of space exploration means that international cooperation is not just desirable, but absolutely essential. Space, after all, knows no boundaries. As humanity ventures further into the cosmos, we must collaborate to address the growing challenge of space debris. This international effort will be necessary to ensure the safety, sustainability, and longevity of our ventures beyond Earth. The future of space exploration, in fact, hinges on how effectively we deal with this debris problem. It will directly shape how missions are planned, designed, and executed, with solutions needing to be both innovative and practical. Whether it's satellite launches or deep space missions, effective mitigation of space debris is crucial, not just for protecting current operations, but also for ensuring the continued expansion of humanity's presence in the cosmos. The challenges posed by space debris extend beyond just the mechanics of spacecraft design. There's a broader question of how humanity will ensure its presence in deeper space. Safeguarding our missions and installations in space will involve developing new technologies, enhancing international policies, and fostering a more profound understanding of how debris interacts with different spacecraft. To protect future generations of astronauts, researchers are working tirelessly to create systems that can not only shield spacecraft from collisions, but also remove the debris that threatens future exploration efforts. Simultaneously, scientists have been grappling with another key aspect of space exploration: the sun's powerful influence on Earth, particularly its radiation and solar flares. As humanity continues to rely on satellites for communication, navigation, and scientific observation, understanding the sun's behavior becomes increasingly important. To study solar radiation and its long-term effects, scientists employ a multi-pronged approach that blends ground-based instruments and complex computer modeling. Satellites in orbit are the primary tools for real-time monitoring of solar activity. These instruments can track solar flares and sunspots, providing valuable data that researchers can use to observe how changes in solar radiation correspond with shifts in Earth's climate over time. This dynamic interaction between solar radiation and Earth's climate offers a fascinating glimpse into how cosmic forces shape life on Earth. Ground-based instruments also play a vital role in this research. These devices, positioned around the globe, measure the intensity of solar radiation reaching the surface. By collecting data over decades, scientists can detect trends that may point to long-term shifts in Earth's environment, whether those involve changing ecosystems or the impact of radiation on human activities. Perhaps even more intriguing, however, is the field of paleoclimatology, where researchers look at ancient records of the Earth's past to understand how solar radiation may have affected the planet long before modern technology was available. By studying ice cores, tree rings, and sediment layers, scientists can infer periods of heightened solar activity and their effects on Earth's climates throughout history. These insights are invaluable in predicting future changes and preparing for potential shifts in Earth's environment. Simultaneously, computer modeling plays a crucial role in simulating different scenarios based on existing data. These sophisticated models allow scientists to predict potential future impacts of varying solar radiation levels on Earth's climate. They help to explore how changes in solar conditions could affect temperature, atmospheric chemistry, and weather patterns over time. Combining direct satellite measurements with historical data and cutting-edge simulation techniques, researchers are piecing together the intricate puzzle of solar radiation's long-term effects on our planet. This knowledge will be essential in preparing for future climate scenarios influenced by solar activity, ensuring that humanity can continue to thrive in an environment that is constantly evolving. Turning towards the cosmos, the potential dangers posed by nearby supernovae are also a subject of increasing scientific focus. Supernovae are powerful explosions that mark the death of a massive star, releasing an immense amount of energy and radiation into space. If one were to occur too close to Earth, the consequences could be catastrophic. In response, scientists have begun closely monitoring the sky for signs of imminent supernovae. Advanced telescopes and observational techniques are used to track the locations and activities of stars that might go supernova, especially those in close proximity to Earth. An essential part of this effort involves identifying which stars are at risk of exploding in the near future. By studying the characteristics of these stars, including their size, age, and composition, scientists can predict which ones may soon enter the supernova phase. This process isn't just limited to observing their light emissions. It also involves using sophisticated models to predict how stars evolve and when they might undergo these violent transformations. Additionally, scientists have been working to educate the public and the scientific community about the potential risks posed by a nearby supernova. Such an explosion could emit harmful radiation and energetic particles that might disrupt our atmosphere and biosphere, potentially having severe consequences for life on Earth. To prepare for these possibilities, scientists are also studying ways to fortify Earth's atmosphere against potential supernova radiation. This includes enhanced monitoring of cosmic radiation levels and the development of better models to understand how Earth's atmosphere might respond to such extraordinary cosmic events. By combining efforts in monitoring, public education, and advanced research, scientists are making significant strides in ensuring humanity is prepared for any potential disruptions posed by supernovae, and in doing so are strengthening the planet's defenses against the unpredictable nature of space. Amid these efforts to protect Earth from cosmic threats, there's an ongoing search for extraterrestrial life, an endeavor that continues to fuel curiosity and drive scientific discovery. The primary goal of this search is straightforward: to uncover any form of life beyond Earth. This quest involves exploring environments within our own solar system, like Mars, or the icy moons of Jupiter and Saturn, where conditions might be favorable for life. However, the search also focuses on understanding the broader conditions necessary for life to emerge in the first place. To this end, scientists study Earth's extreme environments, such as deep-sea vents or polar regions where life can thrive despite harsh conditions. This research not only broadens our understanding of where life might exist elsewhere in the universe, but also reveals how life can adapt and survive under seemingly inhospitable conditions. Another essential element in the search for extraterrestrial life is the detection of biosignatures, distinctive chemical or physical markers that indicate the presence of life. Researchers are examining distant exoplanets, looking for signs of life in their atmospheres. Specific chemical signatures, such as oxygen or methane, might signal biological processes similar to those on Earth. The tools of choice for this work are powerful telescopes, which analyze the light emitted by these distant planets to identify the presence of these potential biosignatures. In addition to this, scientists are listening for radio signals that might be emitted by advanced extraterrestrial civilizations. The idea behind this search is grounded in the fact that radio waves, a type of electromagnetic radiation, can travel vast distances through space at the speed of light. By focusing on certain parts of the radio spectrum, regions that are relatively free from cosmic background noise, researchers hope to detect any signals that might be deliberately sent by intelligent beings. One of the most well-known frequency ranges for this search is called the water hole, which lies between the frequencies of hydrogen and hydroxy molecules, two of the most abundant substances in the universe. Radio telescopes, large dish-shaped antennas designed to capture radio waves, play a crucial role in detecting and analyzing these signals. Once a signal is detected, scientists assess whether it could be artificial by looking for specific characteristics, such as a narrow band of frequencies. If a signal appears to come from a particular direction and is repeated over time, it increases the likelihood that it might be a deliberate transmission, sparking excitement in the scientific community. However, this search is fraught with challenges. The vastness of space means that many signals could go unnoticed, and distinguishing between artificial signals and natural background noise can be difficult. Yet, despite these challenges, scientists are committed to the search, continually advancing technology and refining analysis techniques. Their hope remains that one day they will uncover evidence that we are not alone in the universe. As each new discovery is made, whether it's evidence of ancient riverbeds on Mars, the detection of organic molecules on moons like Europa or Enceladus, or the identification of exoplanets in habitable zones, the search for extraterrestrial life continues to inspire wonder and curiosity. These findings, along with the study of extremophiles, organisms that thrive in Earth's most extreme environments, continue to guide researchers. By understanding how life can survive in conditions such as high radiation levels or extreme heat, scientists are better equipped to explore similar conditions on distant planets and moons. As technology progresses and our understanding of life's adaptability expands, the possibility of finding life elsewhere in the universe seems increasingly likely. With each new clue, we move one step closer to answering one of humanity's most profound questions. Are we alone in the cosmos? Extremophiles, those remarkable organisms that thrive in the most hostile environments on Earth, offer more than just insights into the resilience of life. They provide us with crucial models for the kind of life that could exist on other planets, guiding the design of technology and exploration missions. The ability to replicate the extraordinary qualities these organisms possess, like surviving in extreme heat, cold, or radiation, could vastly improve our chances of detecting or even replicating life on distant worlds. As we probe deeper into the mysteries of astrobiology, these findings shape our approach to space exploration, encouraging missions to focus on planetary regions that share similar conditions to Earth's extremophiles' habitats. It's through this lens that we begin to understand not only the tenacity of life in the most unforgiving corners of our planet, but also the profound implications for life beyond our atmosphere. The potential discovery of extraterrestrial life would have far-reaching consequences for humanity, altering our worldview in ways we can only begin to fathom. For centuries, humans have wondered about their uniqueness in the grand, seemingly infinite cosmos, often pondering whether our existence is a rare exception or a common phenomenon. If evidence of life beyond Earth were found, this idea would be irrevocably challenged. It would be a profound moment, suggesting that life is not confined to our tiny planet, that it can emerge in diverse forms in the vast expanse of the universe. Such a revelation would force humanity to rethink its place in the cosmos, to acknowledge that we are not, in fact, the sole custodians of life. This newfound awareness could have profound cultural impacts. Philosophical and religious beliefs, deeply rooted in the idea of human exceptionalism, would be tested and potentially rewritten. Many belief systems might need to expand or adapt to incorporate the possibility of other sentient beings, with histories and cultures that may be vastly different from our own. The notion that we are the only intelligent life in existence has long shaped our understanding of ethics, morality, and the value we place on life. Should intelligent extraterrestrial life be discovered, humanity would face a new, complex conversation about rights, respect, and dignity, not just for our own species, but for others whose intelligence and history we might not fully understand. This shift could foster a sense of unity among humans on Earth. The realization that we are not isolated in the cosmos could diminish our divisions, as a shared identity within the greater cosmic community takes precedence over national, racial, or cultural distinctions. Rather than focusing on what sets us apart, we may find common ground in the vastness of the universe, a cosmic kinship that redefines what it means to be human. From a scientific and technological standpoint, the search for extraterrestrial life would likely spark an accelerated pace of innovation. New exploration missions would push the boundaries of current technology, striving to send more advanced spacecraft, telescopes, and rovers into the farthest reaches of our solar system and beyond. The discovery of life on other worlds could inspire technological feats we can hardly imagine today. As nations focus on these shared goals, international cooperation would become even more critical. Collaborative space exploration would unite the expertise, resources, and financial backing of multiple countries, making possible ambitious projects that no single nation could undertake alone. This collective effort, not just to explore the cosmos, but to understand the potential for life beyond our planet, could redefine global collaboration in science. It would bring together diverse cultures, fostering an environment where new ideas, theories, and methodologies could emerge. This cross-pollination of ideas could lead to breakthroughs that would revolutionize our ability to detect life elsewhere, enriching the entire field of astrobiology. Furthermore, joint missions would capture the public's imagination, sparking interest and excitement about the unknown. When humanity works together toward a shared goal in space exploration, it creates a sense of unity and purpose that transcends borders, reinforcing the collective nature of our journey into the cosmos. The discovery of extraterrestrial life would also challenge our ethical framework in profound ways. How should we treat life forms from other planets? If these beings exhibit intelligence, do they possess rights similar to human beings, or do we treat them as an entirely different category of existence? Would we respect them as equals, or would we impose our own understanding of life and intelligence upon them? These ethical dilemmas would require careful consideration, informed by our own history of interacting with indigenous populations on Earth. The mistakes of colonization and exploitation cannot be repeated on an interstellar scale. The principles of equality, respect, and dignity must guide humanity's approach to any new life forms encountered in space. There are also environmental concerns to address. If we were to discover microbial life on another planet, our actions could inadvertently threaten their habitats. We would need to consider the preservation of extraterrestrial ecosystems, much as we do here on Earth. The exploration of other worlds must be conducted with care and responsibility, ensuring that we do not contaminate or destroy fragile ecosystems in our search for knowledge. Ethically, our motivations for seeking extraterrestrial life must also be scrutinized. Are we driven purely by curiosity, or is there an underlying desire to dominate or colonize? The history of Earth's exploration and colonization should serve as a cautionary tale, ensuring that we approach this search with humility and respect, understanding that we are not the sole inhabitants of the universe, nor the rightful rulers of other worlds. The societal impact of such a discovery would reverberate across every facet of human life. It would change our perceptions of ourselves, challenging the notion of human supremacy and raising profound philosophical and religious questions. The discovery of extraterrestrial life would force us to reevaluate our place in the universe and our relationship with all forms of life, both terrestrial and extraterrestrial. Communication with extraterrestrial beings would also be a critical aspect of this dialogue. The question of how to reach out, what message to send, and how to ensure that our intentions are peaceful and transparent would require careful planning. A framework for communication must prioritize cooperation and mutual respect, ensuring that any interaction is founded on principles of peaceful exploration rather than conquest or exploitation. As we continue to search the stars for signs of life, we are not only expanding our understanding of the universe, but also confronting deep moral and ethical questions about our place within it. This quest is not just a scientific pursuit. It is a journey into understanding our responsibilities to each other, to life on Earth, and to any new forms of life we may encounter in the vast expanse of space. For centuries, humans have looked to the night sky for meaning. Ancient cultures gazed up at the stars, the planets, and the heavens, finding stories, wisdom, and purpose in their movements. The Egyptians, for example, saw the sun as a god, reflecting the cycle of life, death, and rebirth. They constructed monumental structures aligned with the sun, reflecting their deep connection to this celestial body. The Maya, with their intricate understanding of astronomy, linked the stars and planets to agricultural cycles and religious ceremonies. In Mesopotamia, early astronomers tracked the cycles of the moon and planets, creating one of the earliest forms of astrology to predict seasonal changes and guide the planting and harvesting of crops. The ancient Greeks made monumental strides in understanding the cosmos. Their philosophers and astronomers developed early models of the universe, striving to make sense of the apparent movements of the stars, planets, and sun. This early study of the heavens laid the groundwork for much of modern astronomy. In other parts of the world, such as Australia, indigenous cultures like the Aborigines used the stars as a map for navigation, intertwining their identity with the celestial landscape. For these ancient civilizations, the night sky was not simply a physical phenomenon. It was a spiritual and philosophical framework through which they understood their place in the world. The stars were deities, guides, and symbols of life's cyclical nature. They were the canvas for stories and the calendar for time. This cosmic perspective profoundly shaped their understanding of the world, giving them a sense of connectedness to something much larger than themselves. Today, as we look to the stars, we are faced with a new challenge: to understand not just the cosmos, but our relationship to it. Looking up at the night sky, we are reminded of our smallness in the grand scheme of things. This cosmic perspective encourages humility, as we are reminded that our struggles, while meaningful to us, are part of a much larger story. It fosters a sense of connection to something greater than ourselves, urging us to care for our planet and recognize our responsibilities as stewards of life, not just on Earth, but throughout the universe. The quest for knowledge about life beyond our planet is not merely about finding answers. It is about understanding our place in the grand cosmic story and recognizing that the journey itself is just as significant as the destination. Whether we find life beyond Earth or not, this search has the potential to transform us, to reshape our understanding of what it means to be human, and to unite us in the pursuit of something greater than ourselves. In the vast expanse of the universe, we are all connected, a single species on a small planet, striving to understand the mysteries of life, both here and beyond. Furthermore, contemplating the vastness of space can ignite profound existential questions within us. Are we truly alone in this infinite universe? What is the ultimate significance of our existence in this boundless expanse of stars and galaxies? These questions, while daunting, encourage a collective search for meaning beyond the limited confines of our immediate day-to-day experiences. As we begin to ponder the cosmic scale, we might find ourselves reconsidering what it means to be human in the grand scheme of the universe. Philosophically, this perspective pushes individuals to embrace broader and more inclusive concepts of unity, diversity, and the shared human experience. When we adopt this cosmic perspective, feelings of isolation and separation often fade into the background. Recognizing that we share this planet with billions of others, each living their own unique lives, full of their own hopes, dreams, and struggles, fosters a profound sense of kinship among us. And if there is life elsewhere in the universe, the potential for connection becomes even more profound. Instead of seeing ourselves as isolated, separate beings, the cosmic lens encourages us to see ourselves as part of a larger, interconnected community. It compels us to ask, what responsibilities do we have to one another, to life on Earth, and to any potential life that may exist beyond it? The cosmic perspective doesn't just expand our understanding of existence, it offers an opportunity to reshape our very outlook on life. It sparks questions that might have seemed distant or insignificant before, deepening our sense of humility and reminding us that our lives are but one brief spark in the vastness of time and space. This shift in perspective isn't merely theoretical. It has practical implications that guide our actions, decisions, and aspirations. As we continue to navigate life on this remarkable blue dot in the vast expanse of the universe, the cosmic perspective has the power to unite us in ways that transcend borders, differences, and divisions. By understanding our place in the cosmos, we might discover new ways to coexist peacefully, to protect the environment, and to build a future that reflects the interconnectedness of all life. Throughout history, humanity's fascination with the stars and the vastness of space has been a driving force behind a rich tapestry of myths and legends. Ancient civilizations, gazing at the night sky, did not merely see points of light scattered across the heavens. They saw meaning, stories, and gods. For instance, the ancient Greeks told elaborate tales of the heroes and gods represented by the constellations, figures like Perseus and Andromeda, whose stories illustrated themes of heroism, struggle, and triumph. These myths were not only narratives meant to entertain, but also served to explain the mysteries of nature and human existence. Similarly, many Native American cultures viewed the stars as ancestral spirits watching over the earth. The Milky Way, in particular, was often seen as a celestial river, symbolizing guidance and the journey of life. These stories helped humans feel connected to the cosmos, offering moral lessons and an understanding of their place in the universe. The myths surrounding celestial bodies were not just attempts to explain the unexplainable. They reflected humanity's ongoing quest to understand the universe. Venus, the bright morning star, was particularly significant. Across various cultures, Venus was seen as both a harbinger of war and a symbol of love and beauty. This duality of Venus represents our awareness of cycles, of nature, of human emotions, and of time itself. It reflects our understanding that the universe operates on scales far beyond our comprehension, yet is intimately connected to the human experience. As technology advanced and our understanding of the cosmos deepened, these ancient myths began to evolve. With the advent of space exploration, new myths emerged, this time surrounding the idea of extraterrestrial life. These narratives, largely shaped by our hopes and fears, tell of alien contact, advanced civilizations, and the possibility of life beyond Earth. Popular culture began to explore these themes, with films and literature depicting vast civilizations and the unknown. These new myths were not simply works of fiction. They were an expression of humanity's longing to understand its place in a universe that is so much larger than we are. The modern genre of science fiction, in particular, became a new form of mythology. These stories of brave astronauts venturing into the unknown, of exploration and discovery, echoed the ancient tales of heroes embarking on epic quests. In this sense, space exploration and the myths surrounding it can be seen as a continuation of humanity's ancient impulse to explore, to seek answers, and to understand. The more we venture into space, the more we realize that our yearning for knowledge and understanding is not new. It is as old as humanity itself. These myths, whether ancient or modern, provide a window into how we interact with the cosmos. They reflect not only our awe and wonder at the universe, but also the deep existential questions we have about life, existence, and our future among the stars. Space exploration has left an indelible mark on modern culture, shaping not only our scientific understanding, but also our creative expressions. The quest to reach the stars has inspired artists, writers, filmmakers, and musicians to delve into themes of exploration, humanity, and the unknown. In literature, the genre of science fiction blossomed alongside advancements in space travel. Authors imagined faraway worlds and civilizations, exploring profound questions about existence, technology, and the future of humanity. These narratives, often shaped by our hopes and fears, continue to influence how we think about the universe and our place in it. The visual arts have also embraced the cosmos. Artists have long used the imagery of stars, planets, and galaxies to evoke a sense of awe and wonder. Whether through abstract paintings or detailed representations, the vastness of the universe serves as a canvas for creative expression. Space-themed exhibitions in galleries and museums showcase works that capture the beauty and mystery of outer space, inspiring people to contemplate the larger questions of life and existence. The swirling stars and blue swirls in abstract paintings, in particular, draw directly from the beauty of the cosmos, creating a visual dialogue between art and science. Film and television have played a significant role in popularizing space exploration. Movies like Star Wars, Interstellar, and 2001: A Space Odyssey do more than entertain. They provoke thought about the nature of time, space, and humanity's future. These stories resonate with audiences around the world, sparking interest in real scientific endeavors and encouraging future exploration. Through these films, the possibility of space travel no longer seems like a distant dream, but a tangible reality that might one day be within our grasp. The stories of brave astronauts venturing into the unknown, of exploring alien worlds, echo humanity's timeless quest to understand the mysteries of the universe. Moreover, music has been deeply influenced by the themes of space exploration. Composers and musicians have long been inspired by the vastness and mystery of the cosmos. From classic scores accompanying documentaries about space to modern electronic music that evokes the atmosphere of otherworldly landscapes, the sounds of space resonate through our culture. Music, much like art and literature, serves as a bridge between science and emotion, capturing the feelings of awe, wonder, and curiosity that space exploration evokes. The influence of space exploration also extends into education and technology. As public interest in space grows, science programs for children integrate these concepts into their curricula, fostering a generation that is curious about science and technology. Space exploration has become a central part of modern culture, not just as a field of scientific inquiry, but as a driving force for creativity and innovation. It encourages us to dream, to imagine a future that extends beyond our planet, and to push the boundaries of what is possible. Space has always been a source of wonder and curiosity, filled with enduring mysteries that continue to captivate human imagination. Among the most captivating of these is the enigma of dark matter. While we can see the stars and galaxies scattered across the night sky, most of the universe is made of invisible material that cannot be seen or detected through traditional means. This dark matter, however, interacts with regular matter through gravity, shaping galaxies and holding galaxy clusters together. The fact that most of the universe is composed of something we can't see or fully understand sparks endless questions. What is dark matter, and how does it affect the universe in ways we cannot perceive? These questions challenge our understanding of reality itself, suggesting that there is much more to the cosmos than meets the eye. Equally fascinating is the mystery of dark energy. This mysterious force seems to be responsible for the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. The existence of dark energy raises profound questions about the future of the universe. Will it continue to expand indefinitely, or will it one day collapse back in on itself? This uncertainty forces us to confront the origins and the future of everything we know. What is the ultimate fate of the universe? These questions, driven by the unknowns of dark matter and dark energy, are as much a part of the human experience as the myths and stories we have told throughout history. They remind us that, in the vastness of the cosmos, we are still only scratching the surface of understanding. The vast expanse of the universe has long been a source of endless fascination for humankind. One of the most captivating phenomena in this cosmic frontier is the concept of black holes. These mysterious regions of space hold an almost magnetic allure, drawing in the curious minds of scientists and dreamers alike. The gravitational forces at play within a black hole are so intense that they can warp the very fabric of space and time, rendering them as cosmic enigmas. Not even light, the fastest thing in the universe, can escape their grasp. The idea of what happens inside a black hole remains one of the greatest intellectual challenges in modern science. What becomes of the objects that cross the boundary of a black hole, known as the event horizon? Do they vanish into oblivion, or could they open doors to parallel universes, alternate realities, or realms we cannot yet comprehend? Are these celestial objects nothing more than cosmic traps, or do they serve as portals to untold realms of existence? These questions stir the imagination and encourage scientists to push the boundaries of our knowledge while captivating the public's fascination with the unknown. However, black holes are just the tip of the iceberg when it comes to the mysteries of the cosmos. The quest to understand life beyond Earth remains one of humanity's most enduring pursuits. The possibility that life exists elsewhere in the universe, whether in the form of simple microorganisms or even more intelligent beings, challenges our fundamental understanding of life itself. To explore this idea, scientists have begun looking for extreme environments on Earth as analogs for potential life-sustaining conditions elsewhere in the cosmos. One particularly intriguing location is Europa, one of Jupiter's moons, where beneath its icy surface, scientists suspect there may be a subsurface ocean capable of harboring life. These investigations on Earth serve as a critical foundation for the search for extraterrestrial life, offering crucial insights into how life could potentially exist in the harshest and most inhospitable corners of the universe. Alongside the search for life beyond Earth, one of the most profound and mind-bending questions we grapple with involves time itself. What is time, and how does it function in the context of the universe? Is time a simple linear progression, or is it a more complex and mysterious force? The concept of time travel and the exploration of alternate realities have been key subjects of theoretical physics for years, inviting us to imagine possibilities that could stretch the very limits of our current understanding. If time is not linear, how does that reshape our understanding of the universe? Could we one day break free from its traditional boundaries and experience existence in ways we cannot yet fathom? These questions touch upon the very nature of reality and our perception of existence, sparking the imaginations of both scientists and philosophers alike. Space, with all its mysteries and complexities, serves as a timeless mirror for humanity, reflecting both our past and our future, while connecting us to something much greater than ourselves. The questions about time, space, life, and the cosmos remind us of our smallness in the grand scheme of the universe, but they also drive us toward exploration and discovery. Each unanswered question about the universe beckons us to delve deeper, ensuring that our quest for knowledge will continue for generations to come. The allure of space is not just about the answers we may uncover, but also about the profound questions themselves. Our drive to explore and understand the cosmos will persist, inspiring future generations to continue reaching for the stars. Religious and spiritual beliefs have often intertwined with humanity's understanding of the cosmos, providing a framework for interpreting the vastness of the universe and our place within it. From ancient civilizations to modern-day spiritual practices, the heavens have served as a source of awe, wonder, and reverence. Many early cultures viewed celestial bodies like the sun, moon, and stars not only as physical entities, but also as deities or divine symbols. Their movements were observed closely as they guided agricultural practices, informed the creation of calendars, and played a central role in the formation of mythologies and spiritual teachings. In these early traditions, the cosmos was not just a physical realm, but a reflection of a higher order, a divine structure that governed the universe and human existence alike. Some spiritual belief systems propose that the universe follows a divine plan, with each star, planet, and galaxy holding particular significance in the grand scheme of creation. This belief fosters a sense of connection between individuals and the cosmos, suggesting that humans are part of an interconnected web of existence. The movements of celestial bodies, with their precision and regularity, serve as a constant reminder of the greater order that governs the universe. In many religious traditions, the heavens are depicted as a realm of peace, harmony, and divine presence, in stark contrast to the earthly realm, which is often seen as a place of struggle and imperfection. This duality between the heavens and the earth has inspired rituals, prayers, and ceremonies designed to invite the divine into human affairs, underscoring the belief that the cosmos is not only a physical reality, but a spiritual one as well. In Eastern philosophies such as Hinduism and Buddhism, the cosmos is often seen as an expression of cycles of life, death, and rebirth that mirror the cosmic cycles of the seasons, the phases of the moon, and the movements of the stars. These cyclical concepts emphasize the interconnectedness of all life and the ongoing flow of existence. The cosmic dance of creation, preservation, and destruction, reflected in the endless cycles of nature, is understood as a profound symbol of the unity and continuity of the universe. Through this lens, humanity's place in the cosmos is seen as part of a larger, continuous cycle of transformation and evolution. In contemporary times, some spiritual movements have sought to bridge the gap between science and spirituality, incorporating scientific concepts such as the Big Bang Theory and the vastness of the universe into their spiritual frameworks. This fusion of science and spirituality allows for a broader exploration of the nature of existence and consciousness. In these modern belief systems, the cosmos is not only a physical space, but a canvas for exploring the mysteries of the mind and the nature of reality itself. By drawing upon both the discoveries of science and the wisdom of spiritual traditions, These movements seek to answer some of humanity's most profound questions about the universe, existence, and the meaning of life. The cosmos, in all its vastness and mystery, has always served as a powerful symbol within religious and spiritual practices. It offers a context for understanding existence, morality, and the divine, inviting believers to reflect on their place within the universe. The mysteries of the cosmos evoke a sense of wonder, curiosity, and reverence, inspiring individuals to seek a deeper understanding of themselves and their relationship to the universe. Whether through the lens of science, spirituality, or a combination of both, the cosmos continues to serve as a profound backdrop for contemplating life, existence, and the mysteries that lie beyond our earthly experience. The exploration of space represents a fundamental human drive to understand the unknown, a desire that has been with us for millennia. Since ancient times, humans have looked up at the sky, wondering about the vastness beyond our planet. This curiosity has propelled us to seek answers, pushing the boundaries of our knowledge and igniting our imagination. It is an innate human trait to explore and venture into the unknown. Just as our ancestors crossed oceans and discovered new lands, space exploration is an extension of that same adventurous spirit, but on a grander scale. It is about venturing into the uncharted territories of space, discovering new worlds, and unlocking the mysteries of the universe. Beyond the thrill of exploration, space exploration also holds the potential to answer some of humanity's most pressing questions. Where did we come from? Are we truly alone in the universe, or are there other forms of life out there? These profound questions fuel scientific research and spark the imaginations of future generations of scientists, dreamers, and thinkers. As we study celestial bodies such as planets, stars, and galaxies, we not only learn more about the universe, but also about ourselves. Our understanding of the cosmos allows us to see Earth from a new perspective, one that highlights our planet's place within the larger context of the universe. Furthermore, space exploration has led to a multitude of technological advancements that have had a profound impact on life on Earth. Many innovations that benefit our daily lives, such as satellite communication, GPS technology, and advances in materials science, were developed as a direct result of the challenges of space exploration. These advancements have opened up new possibilities for solving pressing problems here on Earth, including climate change, resource management, and the development of sustainable energy sources. Ultimately, space exploration represents humanity's collective ambition to expand our horizons, to learn more about the mysteries that surround us, and to improve ourselves as a species. It symbolizes hope, unity, and the relentless pursuit of knowledge that defines what it means to be human. Each step we take into the cosmos brings us closer to understanding not only the universe, but also our place within it, sparking a sense of wonder and possibility that will continue to inspire future generations. The planets of our solar system each present unique characteristics that make them fascinating in their own right. Beginning with the inner planets, we find small, rocky worlds that orbit close to the sun. Mercury, the planet closest to our star, has an atmosphere so thin that it barely exists, causing extreme temperature fluctuations between scorching heat and freezing cold. Venus, often called Earth's twin due to its similar size, is shrouded in a thick toxic atmosphere that traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system. Earth, our home, stands out as the only planet known to support life. With a breathable atmosphere, a perfect balance of water, land, and temperature, Earth offers the ideal conditions for life to thrive. Mars, the red planet, is known for its rusty surface caused by iron oxide and its stunning features, including the largest volcano and the deepest canyon in the solar system. Moving outward into the outer planets, we enter a realm of gas giants and ice giants. Jupiter, the largest planet, is a swirling mass of clouds and storms, with its great red spot, a massive storm larger than Earth, raging for centuries. Saturn is famous for its breathtaking rings, which are composed of ice and rock particles, and are the most intricate and extensive in the entire solar system. Uranus is unique in that it rotates on its side, giving it a distinct blue color due to methane in its atmosphere, and creating extreme seasonal changes. Lastly, Neptune, with its deep blue hue, is known for its ferocious winds and storms. Its moon, Triton, has geysers that eject nitrogen gas, hinting at intriguing activities beneath its icy surface. Each planet tells a story of vast environments, diverse atmospheres, and unique features that make our solar system an endlessly fascinating place to explore. These worlds, each with its own character and mystery, invite us to look deeper, to ask more questions, and to dream of the endless possibilities that lie ahead in our exploration of space. Meanwhile, the Moon, Earth's constant companion, exerts a profound influence on our planet. Its gravitational pull is responsible for the tides, the rise and fall of sea levels that create essential ecosystems along our coastlines. These tidal movements are not mere curiosities. They play a vital role in distributing nutrients in the ocean, helping to support marine life. The ebb and flow of the tides also create unique habitats like tidal pools where diverse species thrive. The Moon's influence is felt not just in the oceans, but in the very rhythms of life on Earth, shaping our planet's environment in ways that are fundamental to sustaining life. In the grand expanse of the universe, the Moon's quiet presence is a reminder of the interconnectedness of all things, a symbol of the delicate balance that sustains life on our planet. As we continue to explore the vastness of space, the mysteries of the cosmos will continue to captivate us, offering endless opportunities for discovery and wonder. The Moon's role in stabilizing Earth's axial tilt is pivotal to the delicate balance that maintains our planet's climate. This stability ensures that Earth's tilt remains consistent over time, an essential factor for sustaining a reliable climate that can support life. Without the Moon's gravitational influence, Earth's axial tilt could fluctuate wildly, swinging from one extreme to another, resulting in drastic shifts in climate patterns. Such erratic variations could be catastrophic, making it exceedingly difficult for life forms, including humans, to adapt. This constancy provided by the Moon enables predictable seasons, which are fundamental for the rhythm of life on Earth. From the blossoming of flowers in spring to the migration of animals during fall, the steady passage of seasons is intricately tied to the Moon's gravitational pull. Beyond just stabilizing the climate, the Moon also plays a critical role in shaping the behavior of nocturnal animals. Many species rely on the natural light that the Moon provides during the night for essential activities such as navigation, hunting, and mating. For instance, certain animals use the lunar cycle to time their reproductive behaviors, such as the spawning of specific fish species, which often occurs in response to the phases of the Moon. Similarly, predators may take advantage of the cover of night to hunt, their activities synchronized with the lunar phases. The moonlight's gentle glow subtly influences the biological clocks of creatures around the world, linking their behavior to the phases of the Moon. This lunar rhythm is so ingrained in the natural world that it affects entire ecosystems, with life forms adapting their activities to the ever-changing phases of the Moon. The Moon's presence, however, is not only significant in the animal kingdom. For centuries, human civilizations have found inspiration and guidance in its light. From ancient agricultural societies to modern cultures, the Moon has been a powerful influence on human activities. Farmers, for instance, have long relied on the lunar cycles to determine the best times for planting and harvesting crops, with many still adhering to traditional lunar calendars to maximize crop yields. Communities across the globe have celebrated festivals and events that align with the full moon, marking it as a time of renewal, spiritual significance, and communal gathering. In this way, the moon has become more than just a distant rock in the sky. It has become an integral part of the cultural fabric that binds human history together. But the moon's influence is not limited to Earth. Its gravitational pull extends into the vastness of space, shaping the oceans in ways that most people rarely think about. The tides, for example, are a direct consequence of the moon's pull on Earth's waters. The ebb and flow of the oceans, vital to marine life and ecosystems, are driven by this celestial connection. The moon's impact extends well beyond the natural world, touching human activities from the earliest agricultural practices to the complex tides of cultural and spiritual life. It is hard to imagine Earth without this silent, unwavering companion that guides the cycles of life, climate, and culture in ways we often take for granted. Shifting focus to the asteroid belt, we move into a vast region of space located between the orbits of Mars and Jupiter. This expanse is home to countless rocky bodies known as asteroids, which vary dramatically in size from small pebbles to enormous objects hundreds of kilometers across. Despite their large number, most asteroids are relatively small, with only a few reaching sizes comparable to that of a dwarf planet. These small bodies are remnants of the early solar system, leftover building blocks that never coalesced into full-fledged planets. The composition of these asteroids provides valuable insights into the conditions that prevailed during the solar system's formation. Some asteroids are rich in metals such as nickel and iron, while others possess a clay-like or carbon-rich composition, hinting at the variety of environments in which they formed. The orbits of these asteroids are generally stable and predictable, though some do follow more eccentric paths, moving closer to the sun or further away in a manner that can sometimes seem erratic. Despite their abundance, the asteroid belt is not densely packed. There is considerable space between individual asteroids, which significantly reduces the likelihood of collisions, though they do occur occasionally. Many asteroids also exhibit unique surface features such as craters, grooves, and fissures, which provide clues about their history and the forces they have encountered, such as solar radiation and collisions with other objects in space. Some asteroids even have moons, demonstrating that even relatively small bodies in the solar system can host complex systems. Studying the asteroid belt is not just about understanding the past, but also looking forward to future possibilities. Some asteroids contain valuable resources, such as rare metals and water, making them prime candidates for future space exploration. Scientists are keen to explore these celestial bodies in search of materials that could be used in space travel or even in the development of off-planet colonies. The asteroid belt, with its vast and varied collection of objects, offers a window into the early solar system and the potential for future resource exploration. Comets, another fascinating class of celestial objects, stand out from other members of our solar system. Often described as dirty snowballs, comets are composed mostly of ice, dust, and rocky materials. What sets comets apart is their spectacular behavior as they approach the sun. The heat from the sun causes the ice in the comet to vaporize, creating a glowing cloud of gas and dust known as a coma. This coma, in turn, can form a tail that extends away from the sun, creating a breathtaking visual display in the night sky. The tail, made of gas and dust particles, always points away from the sun thanks to the pressure exerted by the solar wind. This striking feature is one of the defining characteristics of comets and differentiates them from other objects like planets and asteroids, which do not exhibit such dramatic displays. Comets typically follow highly elliptical orbits, meaning they travel in elongated paths that can take them far beyond the outer planets before returning to the inner solar system. These orbits are much more eccentric than those of planets, which tend to have nearly circular orbits. Some comets only visit the inner solar system once in a lifetime, returning after many years or even centuries. The origin of comets lies in two main regions: the Kuiper Belt, which exists beyond Neptune, and the Oort cloud, a distant sphere of icy bodies surrounding the solar system. These areas are thought to be the source of many of the comets that we observe today, and their icy composition suggests that comets are some of the oldest and most primitive objects in the solar system. Comets' origins, their striking tails, and their long, eccentric orbits make them intriguing objects for scientists and space enthusiasts alike. Studying comets helps astronomers learn about the early solar system and the conditions that existed when it was forming. Since comets are essentially time capsules containing materials from the solar system's birth, they provide valuable information about the building blocks of our solar system. These icy bodies are more than just beautiful spectacles in the night sky. They are windows into the history of our cosmic neighborhood. Turning to Mars, one of Earth's closest neighbors, we find a world that has long captured the imagination of scientists and dreamers alike. The red planet, with its arid landscape and thin atmosphere, seems inhospitable at first glance. However, research has revealed a more complex history. Mars once had liquid water flowing across its surface, as evidenced by ancient riverbeds, lake beds, and mineral deposits that could only have formed in the presence of water. This suggests that at some point in its past, Mars had a much warmer and wetter climate, possibly capable of supporting life. The presence of water is one of the key factors that makes Mars so intriguing, as it raises the tantalizing possibility that life may have once existed on the planet, or could even still exist in some form today, perhaps beneath its surface. Mars' thin atmosphere, composed primarily of carbon dioxide with traces of oxygen and water vapor, provides little protection against the harsh conditions of space. It cannot retain heat effectively, leading to extreme temperature fluctuations from day to night. The temperature can vary from relatively warm during the day to freezing cold at night, making it a challenging environment. Another feature of Mars is its frequent dust storms, which can sometimes envelop the entire planet for months. These storms are a testament to the dynamic and unpredictable nature of the Martian environment. Mars' surface is home to some of the most fascinating geological features in the solar system. Olympus Mons, the largest volcano in the solar system, towers over the Martian landscape, providing insight into the planet's volcanic activity. Similarly, the vast canyon system of Valles Marineris stretches for thousands of kilometers, offering clues about the tectonic forces that shape the planet's surface. These geological features suggest that Mars has experienced a turbulent history, with volcanic eruptions and tectonic shifts that have altered its surface over billions of years. Finally, Mars's polar ice caps, which consist of both water ice and carbon dioxide ice, provide further clues about the planet's climate and seasonal changes. These ice caps grow and shrink with the changing seasons, indicating that Mars still undergoes climatic cycles, albeit in a much colder and harsher form than Earth. The presence of these ice caps suggests that Mars may still retain some capacity to store water, further fueling speculation about the planet's potential to support life or human exploration in the future. As we continue to study Mars, we deepen our understanding of planetary evolution, the potential for life beyond Earth, and the future of space exploration. The mysteries of Mars beckon us, challenging our perceptions of what is possible in the quest for life beyond our home planet. The outer planets of our solar system, including Jupiter, Saturn, Uranus, and Neptune, represent a stark contrast to the terrestrial planets like Earth. These gas giants, composed primarily of hydrogen and helium, are much larger than the rocky planets closer to the Sun. Their immense sizes and thick atmospheres set them apart from the terrestrial planets, which Veshwas. The outer planets in our solar system stand in stark contrast to the inner, terrestrial planets. Their vast, gas-filled atmospheres and intricate moonscapes are far removed from the solid, rocky surfaces of the planets closer to the Sun. These gas giants, including Jupiter, Saturn, Uranus, and Neptune, have numerous moons and, in the cases of Saturn and Jupiter, impressive ring systems made of dust, ice, and other particles. Their sprawling rings and numerous moons give these outer worlds an otherworldly feel, as if they are guardians of secrets that lie far beyond our reach. This is very different from the terrestrial planets such as Earth, Mars, Venus, and Mercury, which are primarily composed of rock and metal, with very few moons and no prominent ring systems. The outer planets, however, are more than just distant and fascinating giants. They offer some of the most intriguing scientific questions in modern astronomy. Their moons, particularly those orbiting Jupiter and Saturn, have become focal points for exploration. Among these, Europa, one of Jupiter's icy moons, stands out as an especially compelling object of interest for planetary scientists. Europa is believed to harbor a hidden ocean beneath its thick ice crust, a place where life might potentially exist. Scientists have long speculated that this subsurface ocean could possess the right conditions to support microbial life, just as Earth's own oceans do. To confirm this, missions to Europa aim to study its surface and explore its potential for habitability. One of the primary objectives is to understand the composition of Europa's ocean, determine its chemical properties, and investigate whether it possesses the necessary building blocks of life. This is a crucial step in answering one of the biggest questions in science. Could life exist elsewhere in the universe, under conditions different from those on Earth? In addition to exploring the surface features and the ice sheet covering Europa, scientists are particularly interested in the moon's magnetic field. Europa's interaction with Jupiter's powerful magnetic field can provide essential clues about the moon's internal structure and the thickness of its ocean. By examining this interaction, scientists can better understand how the ocean behaves and whether it could be a suitable environment for life. Another exciting aspect of the exploration of Europa involves studying its geological history. Researchers hope to learn more about tectonic or geological activity on the moon, which could reveal important information about how the icy surface has evolved over time. As Europa's surface undergoes stresses and movements, it may open up new areas where organic molecules essential for life, could exist. In fact, studying the surface and internal structure of Europa may not only provide clues about its potential for life, but also reveal how similar moons around other planets might evolve, potentially leading to life elsewhere in our solar system or beyond. An equally tantalizing feature of Europa is the presence of plumes, geysers of water vapor, and other materials that are occasionally ejected from the moon's surface. These plumes are thought to originate from the subsurface ocean, and if space missions can collect samples from these jets, it would provide direct evidence of the composition of the hidden ocean beneath. Such discoveries would dramatically enhance our understanding of the conditions that might allow life to flourish in environments far removed from the warmth and light of the sun. In exploring Europa, we are not just answering questions about one moon, but also gaining insight into the broader potential for life in our solar system and beyond. These missions are contributing to an expanding body of knowledge about how planets and moons evolve, how their environments change over time, and how life might take root in even the most unexpected places. Recent advancements in astronomy have also reshaped our understanding of the cosmos in ways that were once thought to be the stuff of science fiction. One of the most exciting breakthroughs has been the detection of gravitational waves. These ripples in space-time, caused by cataclysmic events such as the collision and merger of black holes or neutron stars, provide a completely new way of studying the universe. Before the detection of gravitational waves in 2015, scientists had only hypothesized that such waves existed based on the predictions of Albert Einstein's general theory of relativity, which had been proposed over a century earlier. Gravitational waves, in essence, are ripples in the fabric of space-time caused by the acceleration of massive objects. Just like a stone dropped into a pond creates waves that travel outward, massive cosmic events, such as two black holes spiraling toward each other and ultimately merging, create waves that ripple through space-time. These waves travel at the speed of light and carry information about the event that produced them. When scientists finally detected these waves, it was as though they had uncovered the very vibrations of space-time itself, offering a completely new perspective on the workings of the universe. The gravitational waves detected in 2015 came from the collision of two black holes, an event that stretched and compressed everything in its path, including the fabric of space-time. The discovery not only validated Einstein's predictions, but also opened a new chapter in astrophysics, providing scientists with a powerful tool for observing the universe in ways that were previously unimaginable. While traditional telescopes allow us to observe light emitted from distant objects, gravitational waves provide a way to listen to the universe. These waves offer a unique view of the most violent and energetic phenomena in the cosmos, allowing scientists to learn about events that are invisible to optical telescopes. The impact of this discovery cannot be overstated. It is not just a confirmation of a century-old theory, but also a revolutionary breakthrough in how we observe the universe. By detecting and studying gravitational waves, scientists can now explore some of the most extreme events in the cosmos, deepening our understanding of black holes, neutron stars, and the very nature of space and time itself. Another groundbreaking achievement in modern astronomy is the capture of the first ever image of a black hole's event horizon. In a historic moment, astronomers used a network of telescopes around the world to observe and capture the shadow of a black hole located in a distant galaxy. This image provided a visual confirmation of a phenomenon that had been theorized for decades, but never before seen. The image also helped to support the idea that black holes are not just theoretical objects, but are very real, existing phenomena that play a central role in the universe. The discovery of exoplanets, planets that orbit stars outside of our solar system, has also transformed our understanding of the universe. Thousands of exoplanets have been identified, many of them located in their stars' habitable zones, the regions where conditions may be right for liquid water to exist. Some of these exoplanets are surprisingly similar to Earth, raising the tantalizing possibility that life might exist elsewhere in the universe. This discovery has opened up new avenues for research and fueled the search for extraterrestrial life, making the question of whether we are alone in the cosmos more urgent than ever. In addition to these discoveries, scientists have made significant progress in studying dark energy, the mysterious force that is accelerating the expansion of the universe. While much remains unknown about dark energy, new observations are helping refine our understanding of its role in the cosmos. These discoveries inspire not only space agencies, but also the public's imagination, reminding us of the vastness and mystery of the cosmos and our place within it. Quantum physics, the study of the smallest particles that form the foundation of everything in the universe, has also revolutionized our understanding of reality. At the quantum level, particles behave in strange and often paradoxical ways that challenge our traditional ideas of the world around us. One of the most mind-bending discoveries in quantum physics is the concept of entanglement, where two particles become so deeply interconnected that the state of one particle instantly affects the state of the other, no matter the distance between them. This phenomenon has profound implications for how we understand the relationships between objects in the universe. It suggests a level of interconnection that transcends the conventional understanding of space and time, pointing toward a much more unified and interconnected cosmos than we once imagined. As scientists continue to explore the strange and mysterious world of quantum mechanics, they are pushing the boundaries of what we know about the universe and how its fundamental forces interact, reshaping our understanding of reality itself. These discoveries in astronomy, physics, and planetary science push the limits of human knowledge. They ignite the imagination, urging us to ask deeper questions about existence, life, and the cosmos. They challenge us to look beyond our planet and our solar system, to ponder what might lie out there, waiting to be discovered. And in doing so, they inspire the next generation of explorers, scientists, and dreamers who will continue to push the boundaries of our understanding, seeking answers to the most fundamental questions about the universe and our place in it. In the ever-expanding world of quantum physics, the boundaries of our knowledge have been stretched in profound ways, contributing significantly to our understanding of the most enigmatic and intriguing phenomenon in the universe, black holes. For centuries, these cosmic objects were seen as theoretical oddities, their existence speculated but unconfirmed. Today, however, quantum mechanics has provided vital clues to their true nature. The fascinating interplay between quantum mechanics, which governs the smallest scales of matter, and general relativity, which describes the force of gravity, is beginning to reveal the complexities that lie at the very core of black holes. This merging of quantum theory with Einstein's theory of gravity hints at a deeper, more intricate framework of the cosmos, a structure that we are only beginning to understand. It suggests that at the intersection of these two realms, the smallest particles of existence and the vastness of space-time may be connected in ways that transcend our current comprehension. More than just a theoretical curiosity, these quantum insights are reshaping our understanding of the universe itself, unlocking secrets about how the cosmos operates on its most fundamental level. Moreover, the advances in quantum physics have opened up new avenues of exploration in cosmology, shedding light on the origins and evolution of the universe. One of the most groundbreaking implications has been the development of models that describe the early moments of the universe, immediately following the Big Bang. These models, which incorporate quantum effects at the very moment of creation, offer a new way of understanding how the universe expanded from a singularity, a point of infinite density, into the vast expanse we observe today. Through these models, scientists are gaining insights into the conditions that gave rise to the universe's present structure, revealing how matter, energy, and space itself have evolved over the course of billions of years. As we peer deeper into the cosmos, we see that quantum physics does not merely deepen our understanding of matter and energy, but it reshapes the way we view the universe. The interconnectedness of all things is becoming ever more apparent. Every new discovery, every breakthrough adds a new piece to the great cosmic puzzle, urging us to keep exploring the fundamental nature of reality. The universe, in all its complexity, is revealing itself to us in ways we never imagined possible, and this ongoing process of discovery is only beginning. The recent discoveries in astronomy have brought about a profound shift in our understanding of the universe's scale and the vastness of the cosmos. One of the most significant developments in recent years has been the discovery and study of exoplanets, planets located outside of our solar system. With the advent of more powerful telescopes and advanced detection techniques, scientists have identified thousands of these distant worlds. The sheer number of exoplanets discovered suggests that planetary systems may be far more common throughout the universe than previously thought. This realization challenges our traditional view of the cosmos, expanding the universe in our minds and making it seem far more populated than ever before. Yet this is just the beginning. Another significant shift in our understanding came from the precise measurement of the universe's expansion rate, known as the Hubble constant. For years, scientists had measured the rate of cosmic expansion using various methods, but recent data revealed discrepancies when observing the expansion from different distances. This inconsistency challenges our current understanding of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. These discrepancies suggest that there may be unknown factors at play, and that our current models of cosmic expansion may not fully explain the observed behavior of the universe. The exploration of dark energy continues to push the boundaries of cosmological theory, with scientists looking to develop new models to explain these inconsistencies. In addition to the advances in the study of exoplanets and cosmic expansion, the detection of gravitational waves has opened an entirely new window into the universe. Gravitational waves, ripples in space-time caused by events such as the collision of black holes, offer a new method of observing the cosmos. Unlike traditional telescopes that rely on light, gravitational wave detectors measure distortions in the fabric of space-time itself, enabling us to observe phenomena that were once invisible. These waves allow us to probe the universe in a way that traditional light-based astronomy cannot, significantly expanding our view of the cosmos and broadening our understanding of the forces that shape it. One of the most monumental achievements in modern astronomy occurred in 2019, when the Event Horizon Telescope, EHT, captured the first ever image of a black hole at the center of the galaxy M87. This image provided direct visual evidence of a black hole's existence, offering an unprecedented view of one of the universe's most mysterious objects. It also supported long-standing theories about how galaxies evolve around these supermassive black holes, revealing the crucial role they play in shaping the dynamics of galaxies and the overall structure of the universe. This singular image, a blurry but undeniable proof of a black hole's existence, helped bring clarity to the chaotic dance of matter and energy that defines the fabric of our universe. These breakthroughs, however, are not without their challenges. As new discoveries continue to push the boundaries of what we know, our previous models of the universe are being tested, and in some cases, rewritten entirely. Astronomical research is no longer limited to basic observations. It now involves cutting-edge technology that provides clearer, more detailed views of the cosmos. Advanced imaging techniques have revolutionized the field, offering astronomers the ability to study celestial bodies in ways that were once thought impossible. One of the most significant developments has been the advent of adaptive optics, a technology that corrects distortions caused by Earth's atmosphere, allowing astronomers to observe distant stars and galaxies with nearly the same clarity as if they were observing them from space. In addition to adaptive optics, the use of infrared and radio imaging has provided astronomers with new ways to study the universe. These techniques allow scientists to observe objects that are invisible to the naked eye, such as the birthplaces of stars hidden within dense clouds of gas and dust, or the cold remnants of dead stars. By capturing a broader range of wavelengths, astronomers are able to piece together a more complete picture of the universe, unveiling aspects of the cosmos that were previously hidden from view. Moreover, space-based telescopes like the Hubble Space Telescope have transformed our ability to study the universe. Orbiting above Earth's atmosphere, these telescopes provide an unobstructed view of the cosmos, leading to stunning images of distant galaxies, nebulae, and exoplanets. These observations have provided invaluable insights into the formation and evolution of galaxies, the nature of dark matter and dark energy, and the conditions that might allow for the development of life elsewhere in the universe. The rise of digital technology has also played a crucial role in modern astronomy. With vast amounts of data being collected by telescopes and detectors, scientists now rely on automated processes to sift through this data, quickly identifying new celestial objects and phenomena. This data-driven approach has allowed astronomers to conduct more extensive surveys of the sky, leading to discoveries that are reshaping our understanding of the universe. These advancements in imaging technology have not only made astronomical research more precise, but have also expanded the scope of what we are able to observe, allowing us to probe deeper into the mysteries of the cosmos. Looking forward, the field of astronomy is on the brink of even greater advancements. The development of next-generation telescopes promises to open new frontiers in our understanding of the universe. These instruments, capable of detecting even fainter light from distant galaxies and stars, could reveal cosmic phenomena that have remained hidden from our eyes for eons. These new telescopes are expected to provide deeper insights into the origins of the universe, the formation of galaxies, and the potential for life beyond Earth. Another exciting frontier in astronomical research is the ongoing search for extraterrestrial life. Missions to various planets and moons within our own solar system, such as the exploration of Europa, a moon of Jupiter believed to harbor a subsurface ocean, are aimed at uncovering signs of life beyond Earth. Similarly, astronomers are using powerful telescopes to search for biosignatures, chemical signs of life, in the atmospheres of distant exoplanets. The search for life, whether in our own solar system or on planets orbiting distant stars, could fundamentally alter our understanding of life's existence and its potential to thrive in the vastness of the universe. In addition to these explorations, significant progress is being made in the study of dark matter and dark energy. These mysterious components make up much of the universe, yet remain largely invisible and difficult to detect. Researchers are developing new experiments to detect dark matter particles and to better understand the forces that drive the accelerating expansion of the universe. Unlocking the secrets of dark matter and dark energy could lead to a revolutionary shift in our understanding of the cosmos, transforming our theories of physics and the fundamental laws that govern the universe. As the coming decade unfolds, gravitational wave astronomy is poised for a leap forward. New observatories are being built with the capability to detect the faintest ripples in space-time caused by massive cosmic events, such as the merger of black holes. These observatories will provide us with an entirely new way to explore the universe, offering insights into phenomena that are invisible to traditional telescopes. The combination of advancements in technology, exploration, and theoretical research promises to propel us into an exciting new era of discovery. The future of astronomy holds immense promise. As we continue to push the boundaries of our knowledge, we stand on the precipice of a new era in our understanding of the universe. With every new telescope, each new discovery, and each new breakthrough, we are inching closer to answering some of humanity's oldest and most profound questions about our place in the cosmos. The vastness of the universe, once a source of mystery and awe, is now an open book, and we are the ones poised to turn its pages. As we look ahead, we cannot help but contemplate the future of our universe, a universe that is ever evolving, stretching out across an unimaginable expanse. In the distant future, the galaxies we see today will have drifted farther apart, and the stars will have burned out, leaving behind only the cold remnants of what once was. The cosmos will enter a period of quietude, a time when the vibrant glow of galaxies has faded, and the universe will be dominated by black holes, neutron stars, and white dwarfs. This scenario, known as the cosmic dark ages, envisions a universe devoid of the light and life that once defined it. Eventually, these stellar remnants too will grow cold and dim, and the universe may be left in a state of maximum entropy, known as the heat death of the universe. In this distant future, all energy will have been evenly distributed across the cosmos, and no usable energy will remain to fuel further processes or life. While this outcome may seem bleak, it is a testament to the dynamic history the universe once held, an expansive cosmos filled with galaxies, stars, and the potential for life. In the far future, this cosmic history will fade into the quiet emptiness of an ever-expanding universe. Time itself, when viewed on the scale of the cosmos, becomes an even more extraordinary concept. The seconds and minutes that we experience in our daily lives feel fixed, easily measurable. But in the context of the vastness of space, time is a relative construct, influenced by the effects of gravity and speed. When we look at distant stars, the light that reaches our eyes has often traveled across millions, if not billions of years to reach us. This means that when we observe these stars, we are not seeing them as they are today, but as they were in the distant past. In essence, when we look at the night sky, we are looking back in time, peering into the depths of cosmic history. The universe, vast and mysterious, continues to unfold before our eyes, offering glimpses into both its past and its future. In the vast expanse of the universe, time is far from a simple, unchanging backdrop to the drama of celestial events. Instead, it is a deeply complex and fluid concept, one that can bend, stretch, and shift under the influence of gravity and velocity. This phenomenon becomes especially evident near massive objects such as black holes, where time behaves in ways that defy our everyday understanding. The intense gravity of these cosmic giants is so powerful that it distorts the fabric of space-time itself. As a result, time near a black hole slows down relative to an observer far away. This process, known as gravitational time dilation, is a striking manifestation of how the flow of time can differ based on one's location and velocity within the universe. For someone far from a black hole, time may appear to pass as we typically perceive it, while for someone near the event horizon, it might seem to stand still. The closer one is to these objects, the more pronounced the effect, creating a bizarre, almost otherworldly scenario where time itself seems to bend, stretch, and collapse depending on one's proximity. In the grand scheme of the cosmos, this stretching and warping of time due to the interplay of gravity and motion reveals a reality far more intricate than we might have imagined. What we once thought was a steady, uniform passage of time, flowing from past to future in an immutable, linear fashion, has instead turned out to be a variable, flexible dimension that dances in harmony with the forces shaping the universe. As observers in different locations, depending on their movements and gravitational influences, we experience time in radically different ways. The universe, then, is not a mere backdrop to our existence, but an active participant in shaping how we experience the passage of time. It is a constant reminder that time, as we know it, is not a fixed and absolute concept, but rather a dynamic, ever-shifting entity that adapts to the vast cosmic forces at play. This revelation about time does not just have philosophical implications. It challenges our very understanding of existence itself. The fate of the universe is one of the most profound mysteries, and the question of how time will evolve on the grand scale has intrigued scientists and thinkers for centuries. Many have postulated theories about how the universe will end, and one such theory is the Big Freeze. As the universe continues to expand, it becomes increasingly colder, eventually reaching a point where galaxies drift so far apart that they are isolated in an expanse of empty space. Over an unimaginably long period, the stars will burn out, and all that will remain are faint, dying remnants, such as black holes, that will slowly decay over eons. This relentless expansion will lead to an increasingly desolate and frigid universe, devoid of energy, life, and light, a frozen wasteland of unimaginable proportions. However, another theory, known as the Big Crunch, presents an entirely different outcome for the universe's fate. In this scenario, the expansion of the universe eventually slows down due to the immense gravitational pull of matter. As the cosmic fabric begins to contract, everything will begin to collapse toward a single point. galaxies, stars, and even black holes will be pulled back together, and the universe could return to an incredibly hot and dense state, much like the one it existed in at the moment of the Big Bang. This collapse might not only signify the end of the current universe, but could potentially trigger a new cycle, with the possibility of another Big Bang and the creation of a completely new cosmos. Yet, there is also the fascinating possibility of the Big Rip, where the universe accelerates its expansion to such an extreme degree that it tears itself apart. This theory suggests that an enigmatic force known as dark energy, which is driving the accelerated expansion of the universe, could eventually overcome all other forces. As the rate of expansion increases, galaxies, stars, and even the very fabric of matter itself will be ripped apart, each object moving faster and faster away from one another. In the final moments of the Big Rip, only subatomic particles will remain, dispersed and isolated in a cold, empty cosmos, with everything completely torn asunder. Another possible fate is the idea of heat death, where the universe reaches a state of maximum entropy, a point where all energy has become evenly distributed and no processes can continue. At this point, all stars have burned out and no new energy flows. The universe becomes a still, featureless void with no movement or life. The cosmos would reach a state of stasis, a quiet end where everything is uniform and lifeless. Each of these theories, whether it's the Big Freeze, the Big Crunch, the Big Rip, or heat death, paints a unique and haunting picture of the universe's eventual demise. These hypotheses are not just scientific musings, but profound inquiries into the ultimate nature of existence itself, sparking our curiosity and raising fundamental questions about time, life, and the very fabric of reality. As we grapple with these theories, our understanding of time itself has evolved significantly. In ancient times, time was considered a fixed and linear concept. Philosophers and early scientists viewed it as a constant, flowing, unbroken line that moved steadily from past to present to future. This view persisted for centuries, with time being seen as a universal constant, regardless of the events unfolding within it. However, with the advent of modern physics, particularly in the early 20th century, this rigid notion of time began to unravel. Albert Einstein's theory of relativity shattered our simplistic understanding, showing that time is not a fixed entity, but is instead intertwined with space to form the fabric known as space-time. This revolutionary insight showed that the passage of time could be influenced by both speed and gravity. For example, an observer moving at high velocities, approaching a significant fraction of the speed of light, would experience time much more slowly than someone at rest. This discovery upended the classical view of time, replacing it with a more flexible and dynamic understanding. As Einstein's ideas gained acceptance, scientists began to realize that time was not just a passive backdrop to the universe, but an active participant in the unfolding drama of cosmic events. The expansion of the universe, the gravitational warping near black holes, and the profound effects of velocity on time all pointed to one undeniable conclusion. Time is not a universal constant, but a fluid, ever-changing dimension. It can stretch, compress, and shift in response to the forces of the universe. The closer one is to massive objects like black holes, the more time seems to slow down. This effect, known as gravitational time dilation, has been observed in various contexts, where clocks near black holes tick more slowly compared to those far away. These findings continue to intrigue scientists, who are now working to explore the behavior of time in the extreme conditions of space-time, particularly in the context of quantum mechanics. Quantum mechanics, the theory governing the behavior of subatomic particles, introduces yet another layer of complexity to our understanding of time. At the quantum level, time becomes less predictable. Particles exist in a state of uncertainty until they are observed, and this quantum indeterminacy raises fascinating questions about the nature of time. Could time, as we experience it, even exist in a traditional sense at the quantum level? Can we ever truly understand how time behaves in these extreme microscopic realms? These questions represent some of the most profound mysteries of modern physics, challenges that scientists continue to tackle in the hopes of unraveling the deepest secrets of the universe. The journey of discovery regarding time and the cosmos is a story that stretches across millennia. From the simple, linear notions of time held by ancient civilizations to the revolutionary insights of Einstein and the ongoing exploration of quantum mechanics, our understanding of time is far from complete. With each new theory, we uncover more about the intricate, mysterious relationship between time, space, and the vast universe we inhabit. As we look toward the future, we cannot help but wonder how our understanding of time will continue to evolve. Will we ever fully grasp its nature? Will we uncover the ultimate fate of the universe? Only time, however we define it, will tell. The ultimate fate of our solar system, like that of the entire universe, is tied to the life cycle of our sun, the central star that has sustained life on Earth for billions of years. Currently, the sun is in its middle years, steadily converting hydrogen into helium through the process of nuclear fusion. This phase has lasted for around 4.5 billion years and will continue for several more billion years. However, as the sun exhausts its hydrogen fuel, its core will begin to contract under the force of gravity, while its outer layers will expand. This transformation will lead to the sun becoming a red giant. During this phase, the sun will swell to many times its current size, potentially engulfing Mercury, Venus, and possibly even Earth. The intense heat and radiation will likely sterilize any life that might still exist in the inner solar system. Eventually, the sun will shed its outer layers, creating a colorful shell of gas and dust known as a planetary nebula. The remaining core, now a white dwarf, will gradually cool over billions of years, eventually fading into a cold, dark state known as a black dwarf. This end state, though a distant and theoretical one, represents the final, silent death of the sun. It will no longer emit light or heat, leaving the solar system cold and lifeless. The gravitational influence of the sun will also weaken, causing the orbits of the outer planets to shift. They may drift farther into space, and the dynamics of the solar system will alter as the sun evolves. This dramatic transformation is not something that will occur tomorrow or even in the next million years. It is a process that unfolds over a timescale far beyond our human experience, and while it may seem unsettling, it is simply a natural part of the cosmic cycle. The end of our solar system will mark the conclusion of a chapter written in the stars, a process that is as inevitable as it is fascinating. Finally, there is the age-old concept of time travel, which has captivated both scientists and dreamers alike. Rooted in modern physics and extending into the realm of pure imagination, time travel presents an intriguing possibility that time, like space, may be traversable. The foundation for this idea lies in Einstein's theory of relativity, which shows that time is not an absolute constant, but is instead tied to the fabric of space-time. Moving through space can affect how time is experienced. The faster you travel through space, the more slowly time passes for you, relative to someone who remains stationary. This idea is illustrated in the classic example of two twins, one of whom travels to the stars at near light speed, while the other remains on Earth. When the traveling twin returns, they will be younger than their sibling, a direct consequence of how high-speed travel alters the flow of time. This concept of time dilation raises the tantalizing possibility that, in theory, time travel could be achieved by traveling at immense speeds. But even more exotic possibilities exist, such as wormholes. These theoretical constructs could allow shortcuts through space-time, potentially linking distant points in the universe, or even providing a means of traveling back in time. If wormholes exist and could be stabilized, they might not only allow us to move through space, but could also provide a way to move through time itself. However, time travel is not without its complications. The theories that have emerged around the concept of time travel often present paradoxes that challenge our understanding of both physics and the very nature of reality. One of the most famous examples is the grandfather paradox, a scenario in which a time traveler could theoretically go back into the past and alter significant events in such a way that their own existence could be prevented. This paradox raises critical questions about causality, the principle that a cause must precede its effect, and forces us to reconsider the foundational rules that govern how events unfold in the universe. What happens when the past is altered? Can the future be rewritten? These questions are at the heart of ongoing debates in both theoretical physics and philosophical discussions about time. As time travel remains an elusive concept, the exploration of these paradoxes has only deepened our curiosity about the mysteries of time. Current scientific exploration continues to grapple with these enigmas, striving to unlock the secrets of time while confronting the inherent limitations of our understanding. While the idea of traveling through time stirs our imaginations and inspires countless stories, it still resides within the realm of speculation. Yet the very existence of these theories prompts us to ponder the structure of time itself, what it is, how it works, and how it might be manipulated in the future. Even though time travel may not yet be within our grasp, it remains a fascinating subject at the crossroads of physics and human imagination. As humanity's ambition to reach the stars grows ever stronger, emerging technologies in space exploration offer new ways to rethink the concept of time. A key area of focus is the development of propulsion systems capable of drastically reducing travel times. Technologies such as advanced ion propulsion systems and solar sails present exciting possibilities for interplanetary travel. These systems operate on principles vastly different from conventional chemical rockets, offering the potential to propel spacecraft to much higher speeds. In doing so, these advancements could make previously distant planets and moons more accessible, enabling shorter travel times for missions that were once thought to be beyond our reach. For astronauts embarking on these journeys, the experience of time would undoubtedly feel different. As spacecraft move at higher speeds and travel farther from Earth, the flow of time for the astronauts could diverge from that of people remaining on Earth. This phenomenon, known as time dilation, is a direct consequence of the theory of relativity. According to Einstein's equations, time moves more slowly the closer an object approaches the speed of light, and it can be further altered by the presence of massive celestial bodies. For astronauts, this could mean that a journey that lasts only a few years in their frame of reference could be decades, or even centuries, from the perspective of people back home. Such differences in time perception would lead to intriguing and thought-provoking scenarios in which astronauts return from distant missions to find that their friends and family have aged far more than they have. One potential breakthrough lies in the development of faster-than-light propulsion methods, such as the theoretical concept of warp drives. These systems, if they can be developed, would allow spacecraft to travel through space in a way that warps or distorts the fabric of space-time itself, enabling ships to cover vast distances in a fraction of the time it would take under normal conditions. In this scenario, the passage of time for the traveler would be compressed relative to that experienced by those left behind, further emphasizing the interplay between time and space in ways that stretch the imagination. This could lead to mind-bending possibilities, such as astronauts returning from long journeys with far less aging than those they left behind, a true demonstration of time travel within the context of relativity. Advancements in artificial intelligence, AI, are also set to revolutionize the management of time during long-duration space missions. AI-powered systems could optimize mission schedules, ensuring that astronauts' physical and mental health are carefully monitored and maintained throughout their journeys. With the support of AI, astronauts could experience time in a more structured and balanced way, with work and leisure seamlessly integrated into their routines. This optimized time management might not only make long trips feel shorter, but also help astronauts cope with the psychological and emotional challenges that often accompany extended missions in deep space. In this way, AI could play a pivotal role in altering how we perceive and experience time, making the passage of months or years feel more like a continuous and manageable flow of events. Another exciting possibility lies in the role of virtual reality, VR, in time perception during space exploration. VR could be used to create immersive environments that engage astronauts and support their psychological well-being. By offering a virtual escape from the isolation and monotony of deep space travel, VR could help astronauts maintain their focus and keep a sense of connection to Earth, even as they traverse vast interstellar distances. Hours could pass unnoticed as they explore entirely new worlds in digital form, their minds absorbed in simulations of far-off landscapes and adventures. These immersive experiences could provide both entertainment and emotional relief, while subtly altering the astronaut's perception of time itself. As such technologies continue to evolve, they promise to reshape not only how we manage the passage of time, but also how we experience it in its entirety. The intersection of technology and our understanding of time is also evident in the realm of space telescopes. These instruments have transformed our ability to observe distant galaxies, planets, and other cosmic phenomena. By positioning telescopes above Earth's atmosphere, we eliminate the distortion caused by atmospheric interference, which often blurs the clarity of ground-based observations. With this clearer view, scientists are able to capture more precise data and uncover new details about objects that are far, far away. Space telescopes have revolutionized our ability to study the universe across various wavelengths of light, not just the visible spectrum. Some telescopes are capable of detecting infrared light, which reveals cooler, more distant objects such as star-forming regions hidden within dense clouds of gas and dust. Others can focus on ultraviolet light, providing insights into the hottest and youngest stars in the universe. The ability to observe across such a wide range of wavelengths has given astronomers a more complete picture of how galaxies evolve over time. Moreover, space telescopes have granted us a unique opportunity to peer backward in time. Because light travels at a finite speed, when we observe distant galaxies, we are actually looking at them as they appeared millions or even billions of years ago. This ability to look back in time allows scientists to trace the evolution of galaxies, star systems, and other celestial bodies, providing clues about the processes that have shaped the universe over its vast history. As we study these distant objects, we can witness cosmic events such as the birth of new stars, the merging of galaxies, and the interactions between different regions of space. This time travel of sorts has opened a window into the past, enabling us to understand how the universe has grown and changed over the eons. In addition to studying distant galaxies, space telescopes also allow scientists to investigate exoplanets, planets that orbit stars far beyond our solar system. By observing how the light from a star dims as a planet passes in front of it, astronomers can gather valuable information about the planet's size, orbit, and atmosphere. This data is crucial in the ongoing quest to find Earth-like planets that could potentially harbor life. Space telescopes have been instrumental in identifying planets that might resemble our own, allowing us to refine our understanding of what makes a planet habitable and whether life could exist elsewhere in the cosmos. The study of cosmic phenomena, aided by space telescopes, has profoundly advanced our knowledge of the universe. By observing distant galaxies, star systems, and exoplanets with unprecedented clarity, we are painting a more detailed and accurate picture of the universe's past, present, and future. To fully comprehend the cosmos, scientists employ a range of innovative techniques and tools designed to observe and interpret the data collected from distant celestial bodies. The most fundamental of these tools are telescopes, but these are no ordinary instruments. They come in many different forms, each designed to observe a specific aspect of the universe. Optical telescopes, for example, capture visible light and provide us with stunning images of stars, planets, and galaxies. These telescopes rely on lenses or mirrors to focus the light, allowing astronomers to see intricate details that would otherwise remain hidden. In contrast, radio telescopes detect radio waves, longer wavelengths of electromagnetic radiation. These telescopes are vital for studying cosmic phenomena that are invisible to optical telescopes, such as cold gas clouds and faint emissions from distant galaxies. Radio telescopes are also uniquely capable of observing through dust and gas clouds that would obscure visible light, making them essential tools for studying star formation and galaxy dynamics. Moreover, radio telescopes can operate both day and night, making them highly versatile instruments. Together, optical and radio telescopes offer complementary insights into the universe, each revealing different facets of the cosmos. By combining the data from these instruments, astronomers can create a more complete picture of space and the events unfolding within it. This collaborative approach allows scientists to study not only what is visible to the human eye, but also the hidden forces and processes that govern the universe's behavior. One of the most significant recent advancements in astronomical observation has been the development of adaptive optics. This technology is designed to correct the blurring effects caused by Earth's turbulent atmosphere, much like how corrective lenses sharpen vision. By adjusting in real time to atmospheric distortions, adaptive optics enable telescopes to produce sharper images, enhancing the accuracy of measurements and improving our understanding of distant stars, galaxies, and other cosmic bodies. This technology has had particular benefits in the study of exoplanets, which are often difficult to detect due to their faint light compared to the stars they orbit. By using adaptive optics, astronomers can more effectively spot these distant worlds, expanding our knowledge of the diversity of planets in the universe. Adaptive optics has also provided valuable insights into the behavior of galaxies, including the formation of new stars and the movement of celestial bodies within galaxies. By refining our observations, this technology helps astronomers piece together the puzzle of how galaxies evolve over time. It also plays a crucial role in studying phenomena such as supernovae and black holes, allowing us to capture more detailed images and gain deeper insights into some of the most mysterious and extreme events in the universe. In summary, the fusion of advanced technologies in both space exploration and cosmic observation has significantly transformed our understanding of time, space, and the universe itself. From the development of new propulsion systems that could one day make time travel possible, to the advent of space telescopes that provide clearer views of the cosmos, we are witnessing a revolution in our relationship with the universe. As each technological breakthrough unfolds, it not only pushes the boundaries of what we can achieve physically, but also forces us to rethink fundamental questions about time, space, and the nature of reality. The future promises even more exciting advancements, ones that could shape how we explore the cosmos and how we understand our place in the vast, ever-expanding universe. In the ever-expanding field of astronomy, technological advancements continue to unlock new ways of seeing the universe. Among the most groundbreaking innovations, adaptive optics stands out as a transformative tool in the study of distant celestial objects. This technology plays an indispensable role in the realm of spectroscopy, where it allows astronomers to explore the composition of stars, planets, and other cosmic bodies with greater clarity and precision. The ability to obtain clearer spectral data is a game changer, as it provides vital information about the chemical makeup, physical properties, and even the behaviors of distant objects, which are often located millions or even billions of light years away. Through the use of adaptive optics, telescopes are no longer hindered by the blurring effects of the Earth's atmosphere, enabling sharper, more accurate observations that were previously unimaginable. Adaptive optics works by correcting the distortions caused by the atmosphere, which otherwise blur the images captured by telescopes. This enhancement leads to vastly improved image quality, which in turn amplifies the telescope's capacity to detect faint exoplanets, uncover intricate details of distant galaxies, and gain a deeper understanding of the universe's vast structure. Through this technology, astronomers can observe distant stars, nebulae, and other cosmic phenomena with a level of detail that allows them to identify features and characteristics that would otherwise remain hidden. These improvements in optical clarity are not just technical feats. They have revolutionized our ability to explore the cosmos, pushing the boundaries of human knowledge ever further. Spectroscopy, a cornerstone of modern astrophysics, is one of the primary methods by which we unravel the mysteries of the universe. At its core, spectroscopy is the study of how light interacts with matter. As light from stars and other celestial bodies travels through space and reaches Earth, it often passes through instruments known as spectrometers. These devices split the incoming light into its constituent colors, creating a spectrum much like a rainbow. By analyzing this spectrum, scientists can glean invaluable insights into the objects that emit or absorb the light, offering clues about their composition, temperature, density, and motion. Each element in the universe emits and absorbs light at specific wavelengths, much like a unique fingerprint. For instance, hydrogen and helium, two of the most abundant elements in the cosmos, produce distinct absorption and emission lines in the spectrum. These lines appear as dark or bright bands, scattered across the spectrum, signifying the presence of particular elements within the observed celestial object. The intensity of these lines offers additional information about the abundance of each element. A brighter line suggests that a greater concentration of that element is present, while a fainter line indicates a lesser concentration. Moreover, the shape and position of these spectral lines provide critical data about the physical conditions within the star or galaxy being studied. For example, when a star is moving toward Earth, the spectral lines are compressed, shifting toward the blue end of the spectrum, a phenomenon known as blue shifting. On the other hand, if a star is moving away from us, its spectral lines are stretched, shifting toward the red end of the spectrum, a process known as red shifting. These shifts not only reveal the star's motion, but also help astronomers determine its velocity relative to Earth, offering clues about the dynamics of our galaxy and the universe as a whole. Through the detailed study of spectral data, scientists can uncover far more than the basic composition of distant stars. Spectroscopy allows them to explore the physical properties of these celestial bodies, such as temperature, pressure, and even the presence of magnetic fields. It also sheds light on the behaviors of stars and galaxies, allowing astronomers to discern their life cycles, interactions, and eventual fates. In this way, spectrometry is far more than a tool for cataloging the elements present in the universe. It is a gateway to understanding the very processes that govern the cosmos. As our technological capabilities continue to improve, the power of spectroscopy has been enhanced in ways that would have been unimaginable just a few decades ago. The advent of more sensitive and precise spectroscopic instruments has enabled astronomers to study light from increasingly faint and distant objects. For instance, the Hubble Space Telescope has provided spectral data that has led to groundbreaking discoveries, such as the detection of water vapor on exoplanets and the identification of complex organic molecules in distant galaxies. These findings have profound implications, not only for our understanding of the chemical makeup of the universe, but also for the potential for life beyond Earth. In addition to the exploration of distant stars and galaxies, spectroscopy has played a crucial role in understanding the very nature of the universe itself. By measuring the spectral shift of light from galaxies, astronomers have been able to observe the expansion of the universe, and in doing so, they uncovered the mysterious force driving this expansion: dark energy. This discovery has opened new avenues of research into the fundamental forces that shape the cosmos, pushing scientists to reconsider existing theories and develop new models of the universe's evolution. Innovations in spectroscopy have also provided crucial insights into the history of the universe. By studying the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang, scientists have been able to probe the early universe and better understand its formation. These advances have helped answer some of the most fundamental questions in cosmology, such as the origin of cosmic structures and the nature of dark matter. The ability to peer back in time and study the universe's earliest moments is one of the most profound achievements in human history, and it owes much to the power of spectroscopy. As we look to the future, the field of spectroscopy continues to evolve, offering new tools and techniques for exploring the vastness of space. The next generation of telescopes and spectrometers, such as those planned for the James Webb Space Telescope, promise to further expand our understanding of the cosmos. These instruments will enable scientists to study even fainter and more distant objects, providing a clearer picture of the universe's origins and its ongoing evolution. While spectroscopy remains an essential tool in the study of the universe, it is not the only method through which we explore the cosmos. Satellites orbiting the Earth and beyond have become invaluable instruments for monitoring cosmic activity. Equipped with cutting-edge sensors and cameras, these satellites are capable of capturing a wide range of data, from solar flares to the movements of asteroids and comets. By providing continuous coverage of the cosmos, satellites act as vigilant sentinels, alerting us to cosmic events that might otherwise go unnoticed. One of the most crucial tasks of satellites is monitoring the sun, our nearest star. Solar activity, including solar flares and coronal mass ejections, can have significant effects on Earth. These phenomena can disrupt satellite communications, GPS systems, and even power grids. By observing the sun in real time, satellites help scientists predict when such events are likely to occur, providing early warnings that can mitigate their impact. Specialized sensors onboard these satellites can measure magnetic fields and solar particles, offering insights into the sun's behavior and helping to safeguard our technological infrastructure. Satellites also play a critical role in tracking near-Earth objects, NEOs, such as asteroids and comets, which could pose a threat to our planet. By observing these objects and monitoring their trajectories, scientists can assess the risk of potential collisions and develop strategies for mitigating the threat of impact. In the event that a hazardous object is detected, satellites can help guide efforts to deflect or destroy it, ensuring the safety of our planet. Beyond their role in monitoring solar activity and near-Earth objects, satellites also observe distant cosmic events. Equipped with advanced instruments, these satellites are able to collect data on phenomena such as supernova, the birth of new stars, and the interaction of galaxies. By studying these events, scientists gain valuable insights into the life cycles of stars, the formation of galaxies, and the fundamental processes that govern the universe. Satellites also help us study the cosmic microwave background radiation, providing a window into the early universe and offering clues about the origins of the cosmos. In this sense, satellites serve as our eyes in the sky, constantly gathering and transmitting data that deepens our understanding of the universe. Their ability to monitor cosmic events in real time while also protecting our planet from potential threats makes them an indispensable tool for both scientific research and planetary defense. As technology advances, the role of satellites will only continue to grow, allowing us to explore the cosmos in ways that were once the stuff of science fiction. In the realm of space exploration, the concept of faster-than-light travel has long captured the imagination of scientists, engineers, and dreamers alike. While the current laws of physics suggest that traveling faster than the speed of light is impossible, that has not stopped researchers from exploring theoretical concepts that might one day make such travel a reality. One of the most popular ideas is the concept of a warp drive, a theoretical propulsion system that would allow a spacecraft to travel faster than light without violating the laws of physics. The concept involves distorting space-time itself, creating a bubble that would move a spacecraft faster than light while leaving the spacecraft stationary within the bubble. By manipulating space in this way, the spacecraft could theoretically bypass the speed limit imposed by the speed of light. Another intriguing idea is the possibility of wormholes, hypothetical tunnels in space-time that could connect two distant points in the universe. If wormholes exist and could be traversed, they could provide a shortcut between distant regions of space, allowing for faster-than-light travel. While these ideas remain purely theoretical, they represent the cutting edge of our understanding of space-time and the potential future of space exploration. As we continue to push the boundaries of our understanding and capabilities, the possibilities for exploring the cosmos expand, whether through advances in spectroscopy, the use of satellites to monitor cosmic activity, or the exploration of new theories in space travel. Humanity is steadily advancing toward a deeper understanding of the universe and our place within it. Each discovery, each technological breakthrough brings us one step closer to unlocking the mysteries of the cosmos and venturing farther than ever before into the great unknown. However, the stability of such structures, particularly those associated with faster-than-light travel, remains purely theoretical. It hinges on the concept of exotic forms of matter, which, as of today, have yet to be discovered. While these ideas provide a fascinating glimpse into what could potentially be achieved, they are not grounded in any empirical evidence at this time. These hypothetical scenarios, often explored through advanced mathematics and quantum mechanics, push the boundaries of our understanding of space, time, and energy. Quantum mechanics itself introduces additional, mind-boggling phenomena, such as the concept of quantum tunneling. This suggests that under certain conditions, particles can defy the usual laws of physics by crossing barriers that would be insurmountable in our classical understanding of the universe. Though this doesn't apply directly to macroscopic objects like people or spaceships, it still showcases how much of the universe remains unpredictable, operating in ways that challenge conventional expectations. Yet with all this in mind, it is important to recognize that these theoretical possibilities often come with significant challenges. To transform the realm of imagination into tangible reality, we would need to uncover or invent technologies that do not currently exist. At present, there is no evidence or technological foundation that supports the realization of concepts like faster-than-light travel. However, the mere exploration of these ideas opens our minds to the boundless potential of the universe, stimulating the imagination and sparking the curiosity of scientists and dreamers alike. The thought of a future in which humanity can traverse the cosmos, perhaps even at faster-than-light speeds, brings with it the possibility of extraordinary discoveries. While we are far from achieving such feats, the pursuit of these ideas reminds us of the wonders that might await us in the unknown, encouraging us to press forward in our quest for the stars. One such concept that has captured the imagination of both scientists and science fiction writers alike is the notion of wormholes. Wormholes are often envisioned as shortcuts through the fabric of space and time, offering a theoretical means of connecting two distant points in the universe. This concept, rooted in Einstein's theory of general relativity, postulates that space itself can be bent or warped, creating paths that link far-flung regions of the cosmos in ways that seem impossible under the traditional laws of physics. If such wormholes could be stabilized and traversed, they might provide a mechanism to travel to distant stars and galaxies in a fraction of the time that current propulsion methods would allow. However, the practicalities of wormhole travel remain speculative, and the conditions required to maintain such structures, like the presence of exotic matter with negative energy, are still unknown. The allure of wormholes lies not only in their potential for real-world space exploration, but also in their role as a rich source of inspiration for storytelling. In the realm of science fiction, wormholes are often portrayed as cosmic highways that allow characters to leap across vast stretches of space, making interstellar travel seem almost instantaneous. These cosmic tunnels in the world of fiction enable characters to explore new worlds, meet alien civilizations, and venture into the unknown in a manner that defies the limitations of conventional space travel. The concept is often expanded further, blending science and fantasy to include time travel, where a wormhole might not only serve as a conduit through space, but also through time itself. Characters journeying through wormholes could find themselves traveling across different epochs, experiencing history firsthand, or even altering the course of events. This fusion of scientific theory with imaginative possibilities makes wormholes a truly fascinating subject. On the one hand, they challenge our understanding of how space and time function, offering a tantalizing glimpse into how the universe might work on a fundamental level. On the other hand, they inspire creativity and wonder, fueling the imaginations of writers who dream of exploring new worlds and timelines. Whether seen as a scientific reality or a fictional device, wormholes hold a unique place in the human imagination, one that combines rigorous physics with a sense of infinite possibility. They invite us to consider what might lie beyond our current knowledge, offering a potential gateway to both the unexplored corners of the universe and the unexplored depths of our imagination. In a similar vein, the idea of teleportation, while seemingly the stuff of science fiction, is grounded in the principles of quantum mechanics, a field that has reshaped our understanding of the universe in profound ways. At its core, quantum mechanics describes a universe in which particles exist in states of uncertainty, where they can be in multiple places or possess multiple properties at once, a phenomenon known as superposition. Before we observe them, particles do not occupy a single position or possess a single property. They exist in a state of possibility. This bizarre concept forms the foundation for the idea of teleportation. In the simplest sense, teleportation refers to the process of transferring information about a particle's state, its position, velocity, and other properties, from one location to another without physically moving the particle itself. This transfer relies on a quantum phenomenon known as entanglement. When two particles are entangled, they are so intimately connected that the state of one particle will instantly affect the state of the other, no matter how far apart they are. This instantaneous connection, often described as spooky action at a distance, is one of the most perplexing aspects of quantum theory. To grasp this, imagine two identical coins. No matter how far apart they are, flipping one will cause the other to mirror the result immediately, even if they are on opposite sides of the galaxy. In quantum teleportation, the goal is to scan the state of a particle at one location, send that information to another place, and then use this data to recreate the exact state of the original particle in a new location. This process, however, does not transport the physical mass of the object itself, but rather the information about its quantum state. While scientists have succeeded in teleporting very small particles like atoms and photons, the jump to teleporting larger, more complex systems, such as human beings, remains far beyond our capabilities. The challenges are staggering. The sheer amount of information required to describe a human being, the perfect conditions needed for quantum processes to work, and the philosophical questions about identity and continuity of self that arise when considering teleportation on a macroscopic scale. Despite these hurdles, the concept of teleportation continues to captivate the imagination, offering a window into the strange, interconnected world of quantum mechanics. It hints at a future where information could travel instantaneously across vast distances, challenging our fundamental understanding of reality. Interstellar travel, which has long been a subject of speculation and fascination, holds the potential to redefine humanity's future. It represents a bold leap into the unknown, an aspiration to break free from the confines of our solar system and explore the stars. The sheer scale of the universe presents an awe-inspiring challenge, but it also offers the promise of uncovering new worlds, discovering extraterrestrial life, and unraveling the mysteries of the cosmos. As humanity gazes toward the stars, interstellar travel serves as a symbol of our relentless pursuit of knowledge and adventure. It embodies the idea that even in the face of overwhelming challenges, we must strive to push the boundaries of what is possible. The technological advancements required to make interstellar travel a reality are staggering. Scientists and engineers envision spacecraft capable of speeds that are currently unimaginable, capable of traveling vast distances across space in relatively short periods of time. Achieving such speeds would require harnessing energy in new and radical ways, perhaps tapping into the power of fusion or other yet-to-be-discovered energy sources. Additionally, long-term space travel would require developing life support systems that can sustain human life for many, many years, or even centuries, in the harsh vacuum of space. These challenges are not just technical. They also raise profound questions about the nature of time, human endurance, and the limitations of the human body in the extreme conditions of space. At its core, the dream of interstellar travel speaks to our fundamental curiosity about the universe and our place within it. It challenges us to consider the possibility of life beyond Earth, to think about the future of humanity, and to wonder whether our species could one day become a cosmic civilization spread across the stars. The pursuit of interstellar travel could also lead to unprecedented levels of global cooperation as nations come together to pool their resources, knowledge, and expertise in the spirit of exploration. This could foster new forms of international collaboration and understanding, promoting peace and unity as humanity collectively reaches for the stars. Finally, the concept of generation ships. Vast spacecraft designed to carry multiple generations of people on journeys to distant star systems opens up new avenues for exploration and colonization. These ships would be self-sustaining ecosystems capable of supporting human life for centuries as they travel toward distant planets that may offer opportunities for colonization. One of the key challenges faced by generation ships is the need to create a stable, long-term environment that can provide food, water, air, and energy for an entire population. The ship would need advanced recycling systems for air and water, as well as large-scale agricultural facilities to produce food for the passengers. Solar panels or other renewable energy sources might be used to power these systems, ensuring the sustainability of the ship over long periods. Social dynamics aboard a generation ship would also present significant challenges. Living in such a confined space for an extended period could lead to tensions and conflicts, especially as generations grow up without any direct contact with the outside world. Governing such a society, Resolving conflicts and managing limited resources would require careful planning and management. In addition, the lack of interaction with other cultures or external stimuli could lead to cultural stagnation, making education and cultural development on board even more critical. Nevertheless, the concept of generation ships represents an exciting opportunity for humanity to expand into new realms and potentially establish permanent colonies on other planets. Such ships could offer us a way to ensure the survival of the human species, allowing us to adapt and thrive in completely alien environments. Ultimately, the idea of generation ships underscores the resilience of humanity, its ability to dream, innovate, and find solutions to the most daunting challenges. The vastness of space has long captivated humanity's imagination. For centuries, we've dreamed of venturing beyond Earth, looking to the stars for new frontiers. The concept of generation ships, self-sustaining spacecraft designed to carry humans across interstellar distances over generations, offers a vision of space travel that is as ambitious as it is innovative. These ships could be equipped with cutting-edge technology for scientific research and exploration, providing their inhabitants with the opportunity to document and share their findings in ways that could reshape the future of human understanding. Within the confines of a generation ship, a microcosm of humanity could emerge. These ships may not only serve as a vessel to the stars, but also as a means to preserve the cultural heritage and collective knowledge of humanity. As future generations grow up in these artificial environments, they would carry forward the legacies of those who initially set out on the mission, passing down stories, traditions, and discoveries. In this way, generation ships could become self-sustaining communities, focused on maintaining and expanding human civilization, even as they journey toward a new world. Despite their promise, the challenges facing these ships would be immense. The realities of life aboard a spacecraft for centuries, possibly even millennia, pose significant hurdles, from the psychological strain of isolation to the technical difficulties of maintaining and repairing complex systems over long periods of time. Yet, these challenges also present an opportunity to push the boundaries of human ingenuity, to build the tools and strategies that might one day turn the dream of space colonization into a tangible reality. The pursuit of such a venture would not only expand our reach across the stars, but also deepen our understanding of what it means to be human, united in purpose as we traverse the cosmos. One technological advancement that is bound to play a critical role in this journey is virtual reality, VR. For astronauts preparing for long-term space travel, VR offers the potential to simulate the conditions of space, allowing them to experience the environment and challenges they may face, all without leaving Earth. In a fully immersive virtual environment, future space travelers could familiarize themselves with spacecraft systems, practice vital skills, and rehearse emergency procedures in a setting that mirrors the reality of space. A crucial component of VR's role in space exploration lies in its ability to prepare astronauts for the psychological demands of extended missions. Long-term isolation, confinement, and the lack of natural light are just some of the stresses that astronauts would face on these interstellar voyages. VR can simulate these environmental and emotional stressors, allowing astronauts to develop coping strategies. Through immersive experiences, they could learn to manage interpersonal conflicts, work as a cohesive team, and cultivate resilience, all necessary skills for surviving the psychological challenges of space travel. In addition to psychological preparation, VR can also foster collaboration among astronauts dispersed across vast distances. When exploring distant planets or traveling through deep space, communication delays can pose a significant challenge. VR can bridge these gaps by creating shared virtual spaces in which astronauts can interact as if they were standing side by side. This sense of togetherness can enhance communication and promote a stronger sense of community, which is vital for emotional well-being during long journeys. Testing equipment and systems is another critical component of space mission preparation. In the real world, errors in spacecraft systems could result in catastrophic consequences, but VR offers astronauts the chance to practice troubleshooting and repair procedures without the stakes of real-world consequences. Through repeated simulations, astronauts can hone their technical skills, gaining the confidence to address any problem they might encounter in space. With VR's ability to replicate complex systems, astronauts can be prepared for the unexpected challenges of space, ensuring they have the expertise to overcome them. Ultimately, virtual reality represents a powerful tool that can prepare astronauts for the physical, emotional, and technical demands of space travel. By immersing them in meticulously crafted virtual worlds, VR can help ensure that astronauts are ready for the extraordinary experiences that await them among the stars. But space travel is not just about preparing humans for the journey. The idea of manipulating gravity to facilitate space travel is another captivating concept that could revolutionize our approach to space exploration. If we could harness and control gravity, we might unlock new forms of propulsion that could dramatically reduce travel times, both within our planet's atmosphere and across the cosmos. One of the most exciting possibilities is the notion of using gravitational fields for propulsion. Imagine a spacecraft that could generate its own gravity field, allowing it to move through space effortlessly. By bending space around the ship, much like how a massive planet creates a dip in the fabric of space-time, this type of spacecraft could theoretically travel vast distances in a fraction of the time it would take using traditional propulsion methods. If we could create such gravity fields, the potential for interstellar travel would become far more achievable. Another avenue for gravity manipulation lies in the realm of antimatter. Composed of particles that have opposite charges to those found in normal matter, antimatter has the potential to release vast amounts of energy when it encounters regular matter. This energy could be harnessed to create a gravitational effect, which could propel a spacecraft forward. If this energy could be generated and controlled, it might offer a means of gravity-driven travel that allows spacecraft to move more efficiently through space. Alongside these concepts, there are ideas rooted in Einstein's theory of relativity. Some theorists propose that advanced technology could allow us to manipulate the very fabric of space-time itself. By bending or warping space-time, we could create shortcuts between 2 points in the universe, drastically reducing travel times. This concept, often referred to as a warp drive, suggests that by altering our perception of distance, we might be able to achieve faster-than-light travel, one of the most enduring dreams of space explorers. Lastly, there is speculation surrounding the use of exotic materials, such as negative mass or other advanced materials that interact with gravity in unconventional ways. These materials might allow for the creation of regions of space-time with weaker gravitational forces, enabling unique travel methods. Such advancements could make it easier to escape a planet's gravity or even allow for levitation, opening up entirely new possibilities for transportation. While these ideas are largely speculative and rooted in theoretical physics, they represent an exciting frontier of exploration. The manipulation of gravity, whether through artificial fields, antimatter, space-time warping, or exotic materials, could dramatically alter how we think about distance, time, and travel. The journey to turn these theories into reality will be filled with challenges, but the pursuit of such ideas continues to inspire scientists, engineers, and dreamers across the world. As we look to the stars, one of the most transformative forces in space exploration today is artificial intelligence, AI. In the field of astronomy, AI is revolutionizing how researchers process data, make discoveries, and advance our understanding of the cosmos. Traditionally, astronomers would spend countless hours analyzing vast amounts of data from telescopes and simulations of cosmic events. With the help of AI, however, this process has been expedited, and insights that might have previously gone unnoticed are now coming to light. One of AI's most powerful applications in astronomy is image processing. Telescopes can capture enormous quantities of images, often filled with noise or artifacts. AI algorithms can analyze these images much more efficiently than the human eye, quickly recognizing patterns and anomalies. This ability to identify celestial objects such as stars and galaxies, as well as rare phenomena like supernovae, helps astronomers sift through the overwhelming volume of data and focus on the most promising targets. AI is also invaluable in analyzing the immense data sets produced by large-scale sky surveys. With millions of data points to evaluate, AI can categorize and classify these points, making it easier for astronomers to identify events of particular interest, such as gravitational waves or the signs of exoplanets orbiting distant stars. This accelerated data processing not only helps researchers make discoveries faster, but also enhances their ability to predict astronomical events, such as asteroid approaches or solar flares, which could have significant implications for life on Earth. In addition to aiding in the analysis and monitoring of space data, AI plays a key role in simulating cosmic events. By using AI in simulations, researchers can create more accurate models of galaxy formation, black hole dynamics, and other phenomena, enabling a deeper understanding of the universe's evolution. As AI continues to evolve, it is transforming not just how astronomers conduct research, but also what is possible within the field. The collaboration between human ingenuity and artificial intelligence is opening new frontiers in space exploration that were once considered beyond our reach. Furthermore, AI is reshaping how we navigate and control spacecraft. Traditionally, spacecraft relied heavily on human input and pre-programmed commands to operate. However, AI is now enabling spacecraft to make decisions autonomously, analyzing data from sensors and instruments in real time to adjust course, avoid obstacles, and optimize mission parameters. This is particularly beneficial for missions to distant planets, where communication delays between Earth and spacecraft can be significant. Imagine a spacecraft on its way to Mars navigating an unexpected obstacle without waiting for instructions from mission control. AI would allow the spacecraft to adapt to the situation in real time. Trajectory optimization is another critical area where AI is making an impact. Using advanced algorithms, AI can calculate the most efficient path for a spacecraft, taking into account factors like fuel consumption, gravitational influences from other planets, and time constraints. This ensures that space missions are completed with minimal energy expenditure, maximizing the spacecraft's operational lifespan and expanding its capabilities. AI also plays an essential role in monitoring spacecraft health. By continuously analyzing data from onboard systems, AI can detect anomalies and potential failures before they become critical issues, helping engineers address problems proactively. This predictive maintenance approach ensures that spacecraft remain operational throughout their missions, even in the harsh conditions of deep space. The ability to process and analyze vast amounts of data is another area where AI is transforming space missions. Spacecraft generate enormous quantities of data, from images of distant galaxies to readings from scientific instruments. AI can quickly sift through this data, identifying patterns and extracting valuable insights more efficiently than human analysts could. This accelerates the research process, allowing scientists to make faster discoveries in astrophysics and planetary science. In the ever-expanding frontier of space exploration, where human ingenuity and the unknown intersect, the integration of artificial intelligence AI is poised to revolutionize how we navigate and survive in the vast, inhospitable environment of outer space. Space missions, especially those with long durations, such as journeys to Mars, present challenges that go beyond the physical. Fatigue, stress, and isolation are constant companions to astronauts as they venture farther from Earth. In such scenarios, AI has the potential not only to provide crucial technical support, but also to preserve the mental well-being of astronauts, enhancing both their productivity and psychological health. Imagine the setting: a crew of astronauts far beyond the Earth's protective atmosphere, in the midst of a Mars-bound mission. The journey is long, often stretching over several months or even years, with limited contact with family or Earth-bound colleagues. The overwhelming isolation, coupled with the high-pressure environment, creates a breeding ground for stress, fatigue, and even mental health struggles. In this context, AI can serve as a much-needed source of companionship and emotional support. By providing astronauts with virtual companionship, AI can engage them in conversation, offer entertainment, and help alleviate feelings of loneliness. Think of AI not just as a machine, but as a reliable companion that can read the mood, offer soothing dialogue, or even generate a bit of humor to lighten the mood. Its ability to act as a constant presence helps to preserve the astronauts' psychological resilience, ensuring they can maintain focus and calm despite the isolation of space. But AI's contributions don't end with emotional support. As missions grow in complexity, so does the demand for scientific discovery. The deployment of AI in space missions could dramatically shift the landscape of research. AI could handle vast amounts of data gathered from a variety of sensors, analyzing it in real time and making adjustments to experiments without human intervention. This ability to adapt instantly to new information has the potential to accelerate discoveries in ways previously unimaginable. Imagine a space station conducting an experiment on the effects of microgravity on plant growth. As new data streams in, AI systems could automatically adjust environmental controls, ensuring the experiment continues seamlessly without the need for astronauts to micromanage every detail. The efficiency with which AI can handle such tasks would significantly free up astronauts to focus on higher-level problem-solving and exploration. Moreover, in cases where astronauts face multiple challenges simultaneously, AI could operate critical equipment remotely. This capability would allow astronauts to multitask, efficiently managing various operations without being physically present at each station. Whether it's adjusting life support systems or fine-tuning scientific instruments, AI can shoulder many of the routine tasks, providing astronauts with the bandwidth to focus on more complex decisions. As we look further into the future, AI's role in space exploration becomes even more expansive. In missions involving autonomous spacecraft, AI could take over navigational and piloting duties. The ability to pilot a spacecraft through space, especially under unforeseen circumstances, requires not only precise calculations, but also the capacity to make quick decisions in the face of uncertainty. Here, AI excels. Equipped with sensors, advanced algorithms, and the ability to adapt to changing conditions, AI could respond to emergencies with remarkable speed and accuracy. Imagine a scenario in which an autonomous spacecraft on a journey to an asteroid encounters a rogue space debris field. AI would immediately calculate the best course of action to avoid collision, alter the spacecraft's trajectory, and relay updates to the crew, all in the blink of an eye. In emergency situations, such as a life-threatening system malfunction or a sudden need for evacuation, AI would take charge of directing the crew through evacuation procedures, ensuring that the emergency protocols are executed without hesitation. This future vision of space exploration, where AI and human intelligence coexist and complement each other, is becoming increasingly plausible. By relieving astronauts from routine tasks, increasing safety, and enhancing scientific productivity, AI is set to become an indispensable tool in making space travel more efficient, sustainable, and safer than ever before. But AI's influence isn't just limited to human-crewed missions. In the realm of space telescopes, AI is already making groundbreaking contributions. Space telescopes gather massive amounts of data from distant celestial bodies, ranging from far-off galaxies to the closest planets. The sheer scale of this data makes manual analysis an insurmountable task for human researchers. Here, AI shines. Advanced algorithms can sift through petabytes of information, recognizing patterns in light signatures and identifying celestial objects like stars, planets, and asteroids. AI's ability to detect these objects, some of which may be faint or obscured by cosmic dust, has dramatically increased the speed and accuracy of astronomical discoveries. Consider the task of identifying exoplanets orbiting distant stars. AI can analyze the subtle dimming of a star's light caused by a planet passing in front of it. By processing this data at a pace and precision far beyond human capability, AI can identify potential exoplanets, narrowing down the list for astronomers to investigate further. This capability isn't just a matter of speed, it's a matter of accuracy. AI can be trained to recognize light signatures corresponding to specific elements, allowing scientists to learn about the composition of stars or the atmosphere of far-off exoplanets. In this way, AI amplifies our ability to understand the universe's fundamental properties. AI also excels in predicting future celestial events. By analyzing historical data, AI can detect trends and make forecasts about cosmic phenomena like supernova or the trajectories of asteroids. These predictions not only assist in preparing for future observations, but also help us understand the dynamics of space itself. For instance, knowing the potential path of an asteroid could allow scientists to develop strategies for deflection or early detection systems, minimizing any potential threats to Earth. Furthermore, the power of machine learning, a subset of AI, allows these systems to evolve and improve over time. As AI processes more data, it refines its algorithms, becoming better equipped to tackle new challenges and provide even more accurate predictions. In this new age of space exploration, AI is transforming how we process and interpret data from the cosmos. It is enabling deeper insights, faster discoveries, and more accurate predictions, opening new frontiers of understanding in the universe. However, the growing role of AI in space exploration also raises a host of ethical questions. As autonomous systems begin to play an increasing role in critical space missions, we must address concerns related to decision-making authority. Who is responsible if an autonomous system makes a mistake that leads to mission failure or human harm? In the absence of human oversight, these questions become complex. The challenge is further compounded by the fact that AI's decisions may not always align with human ethical norms. How do we ensure that AI operates in a manner that is consistent with the values of safety, fairness, and justice? Another issue is the potential erosion of human expertise. As AI takes on more and more responsibilities, there is a risk that astronauts and scientists may become overly reliant on these systems, diminishing their ability to solve problems or handle emergencies independently. This could have long-term implications for human space exploration, as skills critical to navigating unpredictable situations could be lost over time. AI's integration into space missions also introduces the risk of bias. AI systems, after all, learn from data. If the data they are trained on contains biases, whether from human developers or historical trends, these biases can be carried forward into AI's operations. This could lead to unintended consequences, such as misinterpretation of data or unfair prioritization of certain tasks over others. Moreover, AI's involvement in space exploration also raises environmental ethical concerns. Autonomous robots, for instance, could potentially introduce Earth's microorganisms to other planets, contaminating pristine ecosystems. This issue touches upon a broader question. Should we treat extraterrestrial environments with the same level of ethical consideration as we do Earth's? Perhaps the most significant ethical challenge is the potential militarization of AI in space. As space becomes increasingly accessible, there are concerns about the weaponization of autonomous systems, either by governments or private entities. Could space become the next frontier for military conflict? The role of AI in warfare, whether in space or on Earth, poses a profound question about how these technologies will shape international relations and security. Finally, as AI systems grow increasingly sophisticated, we must confront the philosophical question: do advanced AI systems deserve rights or consideration for their well-being? If AI reaches a level of autonomy and intelligence comparable to humans, should we consider their welfare in the same way we do our own? This question touches upon the very nature of life and intelligence, forcing us to redefine what it means to be sentient or conscious. As we continue to push the boundaries of space exploration, the integration of AI presents both immense opportunities and profound ethical dilemmas. While AI's potential to enhance our ability to explore and understand the universe is undeniable, it is crucial that we engage in thoughtful, responsible discussions about its role. The decisions we make today will shape not only the future of space exploration, but also the values that guide humanity as we venture further into the cosmos. Space exploration is an arena where the synergy between humans and artificial intelligence AI is becoming ever more crucial. AI is poised to be an indispensable partner for astronauts, enhancing their capabilities and ensuring that the limited time they spend on distant worlds is used to its fullest potential. One of the primary ways AI can assist is by acting as an advanced research assistant. Space missions often involve gathering vast amounts of scientific data, such as samples from distant planets or moons. Once collected, AI algorithms can analyze this information almost instantaneously, identifying patterns, anomalies, and correlations that might otherwise take humans years to detect. Furthermore, AI can propose hypotheses and recommend further experiments, which ensures that astronauts' precious time is used as effectively and purposefully as possible. Time is of the essence on long-duration space missions, where every moment counts. The advanced data processing power of AI can vastly speed up research processes, enabling astronauts to pivot and adjust their objectives based on new findings in real time. This dynamic capability creates a feedback loop that enhances the mission's productivity, allowing for more in-depth exploration and faster decision-making. AI does not simply analyze data. It provides astronauts with actionable insights, transforming them from passive observers into active problem solvers. Additionally, AI plays a critical role in monitoring the health and well-being of astronauts, an often overlooked but vitally important aspect of space exploration. Space missions expose astronauts to a wide range of potential health risks, such as prolonged radiation exposure, muscle atrophy, bone density loss, and other risks inherent to extended periods in microgravity. AI systems can continuously analyze astronauts' health data, such as heart rate, blood pressure, oxygen levels, and other vital signs. If any irregularities are detected, AI can alert astronauts immediately, allowing them to take preventative measures before health issues escalate into critical conditions. By continuously monitoring their physiological status, AI ensures that astronauts are not only productive in their research, but also safe and healthy, reducing the risks that often come with venturing into the vast, hostile environment of space. AI's assistance also extends to managing operational tasks that are essential for maintaining the spacecraft and mission objectives. The environment of space is unforgiving, and even small malfunctions can lead to catastrophic failures. AI systems are designed to detect and address technical problems before they develop into emergencies. Whether it's managing fuel systems, optimizing energy use, or diagnosing equipment failures, AI can act as a safeguard, preventing issues that would otherwise require human intervention. In doing so, it frees astronauts to focus on the more complex, high-level tasks of scientific research and exploration. The collaboration between human astronauts and AI does not simply enhance space missions' operational efficiency. It also plays a key role in safeguarding astronauts' well-being. By improving problem-solving capabilities, managing day-to-day operational tasks, assisting in scientific research, and monitoring health, AI serves as a powerful and reliable partner in space. This partnership creates a harmonious environment in which both the cognitive strengths of humans and the computational power of AI work together toward the common goal of space exploration. As this collaboration deepens, space missions will undoubtedly become more efficient, cost-effective, and most importantly, safer for the brave individuals exploring the final frontier. The influence of science fiction on space exploration cannot be overstated. Throughout history, works of fiction have shaped our vision of space travel, sparking the imagination of not only scientists and engineers, but also the general public. These stories often paint ambitious and sometimes seemingly impossible scenarios, yet they serve as a powerful motivator for real-world scientific inquiry. Early science fiction novels laid the groundwork for the notion of space travel, with authors like H.G. Wells and Jules Verne inspiring generations of researchers to push the boundaries of what was once thought possible. For instance, Verne's From the Earth to the Moon was one of the earliest works to bring the idea of lunar exploration to the public consciousness. His depiction of a moonshot, although fantastical at the time, motivated engineers and scientists to think about the mechanics of space travel more seriously. Similarly, science fiction has also opened the door to the idea of extraterrestrial life, which has spurred countless scientific endeavors aimed at searching for life beyond Earth. Through works like Carl Sagan's Contact or films such as Close Encounters of the Third Kind, science fiction has raised the question of whether we are alone in the universe. These speculative ideas have had a real-world impact, leading to missions that seek to explore planets and moons in our own solar system for signs of life, such as the Mars rovers and the search for biosignatures in the atmosphere of Venus. Moreover, science fiction has had a profound effect on the development of new technologies. The concept of AI, robotics, and even terraforming were once relegated to the realm of speculative fiction. Yet, these ideas have inspired innovations in robotic space missions, artificial intelligence, and even concepts for future human habitation of other planets. The portrayal of artificial intelligence in stories like 2001, A Space Odyssey and The Hitchhiker's Guide to the Galaxy has influenced the development of real-world AI systems that help manage spacecraft, assist astronauts, and even perform complex scientific analyses. Beyond just inspiring technological advancements, science fiction often presents important ethical dilemmas about the future of space exploration. These narratives question the potential consequences of colonizing other planets, the ethics of interacting with extraterrestrial environments, and humanity's responsibility in space. Such discussions help shape the policies and guidelines that govern space exploration today, ensuring that future missions are conducted responsibly and sustainably. The cautionary tales presented in science fiction compel us to consider the broader implications of our actions as we extend our reach into the cosmos. In a sense, science fiction bridges the gap between what we imagine and what we can achieve. It challenges us to think beyond our current limitations and inspires the next generation of scientists, engineers, and astronauts to pursue bold, ambitious goals. These stories not only entertain us, but also fuel the curiosity and creativity that are essential for advancing our understanding of the universe. They provide a framework for scientists to explore new possibilities, new technologies, and new frontiers. The stories we consume today shape the reality of tomorrow's space exploration. The connection between literature and technological innovation is long-standing. Throughout history, many groundbreaking inventions and discoveries were inspired by the pages of science fiction novels. One notable example is the invention of the submarine. Long before the first actual submarines were built, Jules Verne's 20,000 Leagues Under the Sea depicted Captain Nemo's futuristic underwater vessel. This imaginative concept captured the public's imagination and spurred engineers to pursue the design and construction of real submarines, eventually making deep-sea exploration possible. Similarly, Arthur C. Clarke's 2001 A Space Odyssey introduced the concept of space stations and AI long before they became realities. The novel and its subsequent film adaptation sparked widespread interest in space technology and influenced the design of real-life space stations such as the International Space Station. Clarke's vision also set the stage for the development of sophisticated artificial intelligence systems, which are now an integral part of space missions. Another visionary work, H.G. Wells' The Time Machine, imagined the concept of time travel, which, though still a theoretical idea, inspired many physicists to think more deeply about the nature of time and space. Wells's creativity fueled discussions in theoretical physics, leading to new ideas about the fabric of the universe, the possibility of time dilation, and the nature of black holes. William Gibson's Neuromancer also contributed to the field of technology in a major way. His depiction of cyberspace, a digital landscape where individuals could interact with one another and with computers, laid the groundwork for the development of virtual reality. Today, virtual reality is used in a wide range of applications, from gaming to training simulations, and continues to evolve as technology advances. These examples show that science fiction does more than just entertain us. It serves as a powerful source of inspiration for real-world technological and scientific advancements. Creative thinking, often portrayed in the form of imaginative works, challenges the status quo, propelling humanity to overcome new obstacles and explore new frontiers. In the realm of space exploration, the portrayal of space in films and television has played a crucial role in shaping public perception and interest. Space movies offer majestic visuals of distant galaxies, thrilling space battles, and breathtaking views of the cosmos that spark curiosity and inspire audiences to learn more about the real universe. For many, these cinematic portrayals of space make the abstract concept of the universe more tangible and relatable. Movies like Star Trek or Interstellar depict characters facing challenges in space, allowing viewers to empathize with the astronauts' struggles, triumphs, and personal journeys. These emotional connections help transform space exploration from a distant, intimidating endeavor into a thrilling and human pursuit. Moreover, science fiction films often introduce viewers to scientific concepts that may be unfamiliar or not widely understood. Ideas like black holes, wormholes, or the potential for extraterrestrial life are presented in ways that make these concepts accessible to the general public. Even though filmmakers take creative liberties, these movies often use real science as a foundation, which encourages audiences to explore what is scientifically accurate and what is speculative. However, not all portrayals of space exploration are accurate. Some films sensationalize or distort scientific facts for the sake of entertainment. These inaccuracies can lead to misconceptions about the nature of space travel, gravity, or the physics of the universe. Despite these flaws, the influence of space cinema is undeniable. It sparks curiosity, which often leads viewers to seek out more accurate information through books, documentaries, and scientific resources. Ultimately, space cinema does more than just entertain. It serves as a powerful medium for shaping societal narratives about exploration and discovery. These films urge society to consider what lies beyond our planet and inspire future generations to pursue careers in science, technology, and space exploration. Through the lens of cinema, space is no longer just a vast, empty void, but a frontier full of potential and discovery. Creative thinking is and always will be a crucial element in overcoming the myriad challenges of space exploration. The unknown nature of space presents countless obstacles, some of which require entirely new, untested solutions. Engineers and scientists often find themselves facing problems that traditional methods are ill-equipped to solve. In these instances, creativity becomes a lifeline, helping them design spacecraft that can withstand the harsh conditions of space, develop life support systems that ensure astronaut survival, and build advanced technology capable of exploring far-off worlds. The challenges of space exploration are immense, but with imagination, determination, and collaboration, the possibilities are endless.